Let's start the new topic that is again one important topic from which questions are frequently asked. And this particular topic is used in your organic chemistry as well. The topic name is dipole moment. Now, my dear students, what is dipole moment basically? Before talking about the term dipole moment, we should exactly know what a dipole is, right? So what is a dipole? My dear students, whenever you have got two equal and opposite charges, whenever you will see two equal and opposite charges separated by certain distance, the system of equal and opposite charges, the system containing equal and opposite charges separated by certain distance, the system of equal and opposite charges separated by certain distance is something which you call as dipole, Now, my dear students, for a dipole, we define a term dipole moment. For a dipole, we define a term dipole moment. And this dipole moment is represented by this particular symbol, which is pronounced as nu. Dipole moment. How do you define this dipole moment? My dear students, dipole moment is defined as the product of charge and the distance between the charges. Product of charge and distance between the charges. It gives me the value of what? It gives me the value of dipole moment. Well, this particular dipole moment, it is a vector quantity. It is a vector quantity whose direction in chemistry is taken from positive to negative. Whose direction in chemistry is taken from positive to negative. Or you can say from less electronegative element to more electronegative element. Okay. For example, you have got a dipole over here. For this particular dipole, I can define the dipole moment, which is going to be the product of charge and distance over here. And the direction of dipole moment is going to be from positive to negative. This is the direction of dipole moment over here. My dear students, the unit of this particular dipole moment, if you talk about the unit of this particular dipole moment, it's SI unit. SI unit of dipole moment is d by, which is represented by d. Okay. For example, I'm taking a molecule over here like HCl. Let's say it's one molecule over here, HCl. Dear students, you know chlorine is more electronegative than that of hydrogen. If chlorine is more electronegative, it's going to attract the bonded pair of electron towards itself, due to which it gets delta negative, it gets delta positive, right? Now you tell me, do we have two equal and opposite charges separated by certain distance? Absolutely. So this particular molecule is behaving like a dipole, right? If I ask you, what will be the direction of dipole moment for this particular molecule? It will be from less electronegative element to more electronegative element, positive to negative. Okay? Number one. Number two, I'm writing one particular statement over here. Lone pair also contributes. Lone pair also contributes towards the dipole moment. Lone pair also contributes towards the dipole moment. And let me tell you, its direction is from, or let me write it like this, its direction is taken towards the lone pair. Its direction is taken towards the lone pair. Now, what does it mean? What does this particular statement mean? It's important. Have a look. For example, I'm taking one molecule NH3 over here. NH3. This is one molecule which I've taken over. NH3. My dear students, if I ask you, how many valence electrons nitrogen has? If I ask you how many valence electrons nitrogen has, you will say it has got 5 valence electrons. 1, 2, 3, 4, and 5. Perfect. Now there are 3 hydrogens over here. So these are 3 hydrogens which are attached to nitrogen. Perfect. These are 3 hydrogens which are attached to nitrogen. Now, my dear students, first of all, if you talk about this particular bond between nitrogen and hydrogen, since we know nitrogen is more electronegative, so it's going to attract the bonded pair towards itself, due to which nitrogen gets delta negative and hydrogen gets delta positive. So, my dear students, this particular bond, is it behaving like the dipole? Yes. So, it will be having definitely a moment whose direction is from positive to negative, right? Similarly, this particular bond, its direction will be positive to negative. This particular one, positive to negative. Now, over here, you have got a lone pair on nitrogen as well. And let me tell you, lone pair also contributes towards the dipole moment. Yeah? Lone pair also contributes towards the dipole moment. And the direction of moment due to lone pair is towards the lone pair. So, how many vectors do we have here? 1, 2, 3, and 4. This is the moment vector due to this particular bond. This is the moment vector due to this particular bond. This is the moment vector due to this particular bond. And this is the moment vector due to the lone pair. So do remember, lone pair also contribute towards the dipole moment. And its direction is taken from, its direction will be always towards the lone pair. As simple as that. Okay, this is one more important statement. Well, after writing this particular statement, there are few more things which I want to discuss about dipole moment to you. And then I'll make you understand what all these things exactly means. See guys, some important terminology, some important things related to dipole moment. Point number one. The first point is, if the net dipole moment of the molecule comes out to be 0, if the net dipole moment of the molecule comes out to be 0, we call that particular molecule as the non-polar molecule. We call that particular molecule as the non-polar molecule. Point number one. Point number two. If the net dipole moment of the molecule comes out to be non-zero, we call the molecule as the polar molecule. So based on the net dipole moment, we classify molecules into 2 types. Polar molecule, non-polar molecule. If the net dipole moment of the molecule is 0, the molecule is supposed to be non-polar. And if the net dipole moment of the molecule is non-zero, the molecule is supposed to be polar. Let's take certain examples. See guys. For example, I have got BeCl2. Okay. If you have a look at the structure of BeCl2, this is Be, this is one chlorine on this side, this is one more chlorine on this side, right? Now, my dear students, if you look at this particular bond between beryllium and chlorine, which one is more electronegative? It is chlorine which is more electronegative. So it will attract the bonded pair towards itself, due to which this particular chlorine will get delta negative and beryllium at the same time will get delta positive. Now talk about this particular bond. Chlorine more electronegative. So this is delta negative, this is delta positive. So my dear students, do you see over here we got 2 dipoles. This is one dipole. This is one more dipole. Perfect. Right? The direction of dipole moment due to this particular dipole, it is from positive to negative. And due to this particular dipole, it's again from positive to negative. So do you see 2 equal and opposite moments, right? Which get cancelled out over here. So I must say net dipole moment of the molecule is 0. And if the net dipole moment of the molecule is 0, should I be calling this particular molecule as polar or non-polar? So this particular molecule is non-polar. Well, if I ask you, are the bonds polar? The bonds here are polar, but the net dipole moment of the molecule is 0. Bonds here are polar, but the net dipole moment of the molecule is 0. Yeah? The overall molecule is non-polar, but the bonds are polar. I hope this is clear to everyone. Yeah? Perfect. Now, my dear students, one more important thing. For example, you have got carbon dioxide, right? Let's say you have got carbon dioxide. And I'm sure you know the structure of carbon dioxide. This is carbon, this is double bond O, this is double bond O. Now, my dear students, have a look. If you talk about carbon and oxygen, which one is more electronegative? It's oxygen, right? It is oxygen. Do you know oxygen is more electronegative than that of carbon? Absolutely. So bonded pairs will shift towards oxygen, due to which oxygen gets delta negative, carbon gets delta positive. Now, due to this particular bond, again oxygen gets delta negative, carbon gets delta positive. Now, my dear students, over here again we got two dipoles, right? Perfect. So can I say the direction of dipole moment due to this particular dipole is from positive to negative? And similarly over here, it's again going to be positive to negative. So again we have got equal and opposite dipole moments. Again you have got equal and opposite dipole moments, right? So they'll get cancelled out. I would say net dipole moment of the molecule is 0. So this particular molecule overall is supposed to be non-polar. Well, no doubt the bonds are polar, but the overall molecule is non-polar. I hope this is clear, right? Yeah? Perfect. Now, my dear students, one more thing over here. For example, you have got HF, one simple molecule, HF you have. Perfect. Chlorine is more electronegative, so this is delta negative, this is delta positive. So the direction of dipole moment will be in this direction, right? So if I ask you whether the net dipole moment of the molecule is 0 or non-zero, it is non-zero. So this molecule overall is going to be polar in nature, right? The molecule is polar in nature. The overall molecule is polar in nature. Now, there are a few shortcuts which I would want you guys to remember for now. I'm going to give you their explanations as well when I'll teach you valence shell electron pair repulsion theory, VSEPR. But right now, I want you guys to remember those things first of all. My dear students, there is a particular type of question asked. Whether the molecule is polar or non-polar. Whether the molecule is polar or non-polar. Do remember one important thing which I'm going to tell you. But I'll be explaining that point in VSEPR, not here. But you take a note of it right now. Do remember, whenever you have got a molecule in which the central atom has got no lone pair. In which the central atom has got no lone pair. Number one. Number two, all the terminal atoms are same. All the terminal atoms are same. Number three, the molecule has got regular geometry. The molecule has got regular geometry. Do remember, if a molecule satisfies these three conditions, do remember the net dipole moment of the molecule will be taken as 0 and the molecule is going to be non-polar in nature. For example, whenever you see the molecule of the type AB2L0, AB3L0, AB4L0, AB5L0, AB6L0, L0 means 0 lone pair on the central atom, right? Then you have got AB4L2, then you have got AB2L3. Whenever you see the molecules of these type, do remember, you need not to check anything. You'll directly say these molecules are non-polar in nature. These molecules are non-polar in nature. Their net dipole moment is 0. For example, I'm giving you the molecule like this, CH4. I'm giving you the molecule like this, CH4. I'm giving you the molecule like this, CH4. Now, dear students, if you talk about carbon, how many valence electrons carbon has? Carbon has 4 valence electrons. Carbon is forming 4 bonds. So all the 4 valence electrons are utilized to form 4 sigma bonds. So there'll be no lone pair left on carbon. So no lone pair on carbon. Perfect. How many bonds it is forming? 4 bonds, 4 sigma bonds. So if I ask you about the type of the molecule, let the central atom carbon be represented by A. How many bond pairs it's forming? 4 bond pairs. How many lone pairs carbon has? 0. Is the molecule of the type AB4L0? Yes, molecule is of the type AB4L0. So directly you will say this particular molecule, its net dipole moment is 0 and this molecule is non-polar in nature. Right? Yeah? Perfect. Well, all these things in detail, I'll let you know when I'll be teaching you VSCPR. Right now, I would just want you guys to take a note of these things. That's all. Nothing else. Okay? Perfect? Perfect? Or some of you, they might have studied already VSCPR, right? So let me give you one more example. Anyways, I'll be teaching all this in detail when I'll be teaching VSCPR, okay? For example, you have got molecule like this. For example, you have got SF6. SF6, okay? SF6. Or you have got XeF4. XeF4. Well, my dear students, how many sigma bonds are formed? 6. Sulfur had 6 valence electrons, and all the 6 valence electrons are utilized to form 6 sigma bonds. There is no lone pair, right? So let the central atom be A. There are 6 sigma bonds. There is no lone pair. AB6L0 type. So net dipole moment 0, right? Xenon over here, it will be having 2 lone pairs. So 4 sigma bonds, 2 lone pairs of the type AB4L2. Again, AB4L2 comes in this category, right? Its net dipole moment will be 0. So it's going to be again non-polar in nature. Yeah? Perfect. I hope this is clear. Now, let's try to do certain questions so that all these things, they properly become clear to you. Okay? Have a look. Let's start with the third question. Let's start with the third question. You have got HF, HCl, HBr, HI, right? Okay. My dear students, look at the electronegativity difference between hydrogen and fluorine. Can I say the electronegativity difference between fluorine and hydrogen is more than that of the electronegativity difference between hydrogen and chlorine? Right? If the electronegativity difference between H and F is more, that means more charges will be on the atoms. And more the charges means more the dipole moment. So the dipole moment order is going to be this. Simple. You just have to check the electronegativity difference. Wherever the electronegativity difference is more, dipole moment is going to be more. Except certain cases, which I'll let you know. Okay? Look at the second one. Carbon attached with chlorine. Chlorine is more electronegative. It will attract the bonded pair. So delta negative, delta positive. Look at this one. Delta negative, delta positive. Dipole, dipole. Dipole moment direction in this way, dipole moment direction in this way. So you have got 2 bond moments over here. So net dipole moment. This is a vector, this is a vector. Going in the same direction. So net dipole moment will be in this way. Perfect. Net dipole moment is going to be in this way. Look at the other one. TCl. Delta negative, delta positive. So again, dipole moment direction, right? This is going to be delta negative, delta positive. Dipole moment direction. Equal and opposite bond moments over here. They'll cancel out. So net dipole moment of this molecule over here is going to be 0, right? So among these 2 molecules, which one has got more dipole moment? It's going to be the first one. The second one has got 0 dipole moment. Yeah? Simple. Look at the first one, NH3 and NF3. So let me write NH3 over here and let's compare its dipole moment with NF3. So my dear students, first of all, nitrogen, it is attached to 3 hydrogen atoms. It is attached to 3 hydrogen atoms, and on nitrogen, there is a lone pair. Similarly, this is NF3. Nitrogen, it's attached to 3 fluorine atoms, and on nitrogen, there is a lone pair. Right? Now, my dear students, lone pair also contributes towards the dipole moment, and its direction is towards the dipole moment. Its direction is towards the dipole moment. Now, look at this particular bond, nitrogen, hydrogen. Nitrogen is more electronegative. So, it will attract the bonded pair, delta negative, delta positive. So, due to this particular bond, it is going to be this way. Due to this particular bond, in this way. Due to this particular bond, in this way. Perfect. Now look at nitrogen-fluorine bond. Fluorine is more electronegative. So fluorine will attract the bonded pair towards itself, due to which fluorine gets delta negative, nitrogen gets delta positive. So positive to negative. Positive to negative. Positive to negative. My dear students, just have a look carefully. All these 4 bond moments, they are almost in similar direction. They're almost in same direction. But over here, one is going upwards and other 3, they are diverging downwards. So where will cancellation of bond moments happen? What are these bond moments? These are vectors basically. So can I say cancellation of vectors will take place here in this scenario? And in this particular scenario, no cancellation is going to take place. All the vectors are pointing almost in the similar direction. And over here, 3 vectors are pointing almost downwards and 1 vector is pointing upwards. So cancellation of vectors will take place here. So where will be the net dipole moment more? Net dipole moment will be more in case of NH3 because there is no cancellation of bond moments in NH3, whereas there is cancellation, there is some cancellation of bond moments in NF3. I hope this is clear to everyone. Yeah? If this is clear to everyone, let's have a look on one more. Let's have a look on one more question. Now, my dear students, understand properly. I'm sure every one of you would have studied vectors properly. Yeah? Right? Rajwal, I'm teaching you bonding right now. I'm teaching you something dipole moment and you're asking me isomers. Oh, this is irrelevant. All right. My dear students, look at these two molecules. These three molecules over here. CH3. This is CH3. Now you tell me, CH3, whether it is electron donating or electron withdrawing. CH3 is electron donating. So this CH3, it will push the electron density towards the ring. It is electron donating. It will push the electron density towards the ring. If it is pushing the electron density, it will get delta positive. Over here, you can write delta negative. So the direction is from positive to negative. Over here, the direction is from positive to negative. Equal and opposite bond moments, net dipole moment is 0. Net dipole moment in this particular case is going to be 0. Perfect. Look at the second one. Electron donating. They'll push the electron density, right? Positive, negative. So bond moment direction in this way, bond moment direction in this way. Now, my dear students, you can shift the vectors as well, just to get the resultant. One vector is pointing downwards. One vector is pointing downwards. One vector is pointing downwards, right? Another vector is pointing in this way. What is the angle between them? Angle between them is 120. Angle between them is 120, right? Now look at this one. This is positive, negative, right? Positive, negative, right? Shift the vectors. If I write this particular vector over here and this particular vector in this direction, the angle between them is 60. Do you know, smaller the angle between the vectors, maximum will be the resultant, right? Smaller the angle between the vectors, more will be their resultant. So over here, the net dipole moment is 0. Now among these two, where will be the resultant more? Wherever angle is less, resultant is going to be more. So I would say 3 is going to have maximum dipole moment followed by 2, followed by 1. I hope this is clear. I hope this is clear. Right? Now look at the other example. CH3, it is electron donating. NO2, it is electron withdrawing. Okay? If CH3 is electron donating, it will push the electron density in the ring. So it will get delta positive and over here delta negative. So vector will be in this direction, positive, negative. Now NO2 is electron withdrawing. It will withdraw the electrons. So it will get delta negative, here delta positive. So positive to negative. Now shift the vectors. One vector is pointing downwards. Another vector is pointing in this way. Perfect. What is the angle between them? Angle between them is 120. Perfect. Now look at the next example. This is positive to negative, right? This is positive to negative. Shift the vectors. One vector is pointing downwards. Another vector is pointing in this way. So angle between them is 60, right? Look at this one. Positive to negative. And this positive to negative. Both the vectors are pointing downwards, right? Angle over here is 0. Angle over here is 0 degree, right? Smaller the angle between the vectors, more is going to be the resultant. Where is the resultant maximum here? I'll say at 3 resultant will be maximum, followed by 2, followed by 1. So net dipole moment is going to be maximum in 3, followed by 2, followed by 1. I hope this is clear again to everyone. Yeah? Perfectly done? If this is perfectly done, what do you think about these examples? In the example number first over here, do not get confused. Do not get confused in the example number 7 over here. Normally if you see, just a second guys. Just a second. Just a second. Okay. Okay, let me write it over here. You have got CH3F. You have got CH3Cl. You have got CH3Br. You have got CH3I. Perfect. These are few molecules which I have mentioned over here. Yeah. These are few molecules which are mentioned over here. Now understand. Understand properly. CH3F. That means this carbon is attached with 3 hydrogens and 1 fluorine. So there is a bond between carbon and fluorine. There is a bond between carbon and chlorine. There is a bond between carbon and bromine. There is a bond between carbon and iodine. Right? Now, my dear students, what do you think? Electronegativity difference between carbon and fluorine is more than that of electronegativity difference between carbon and chlorine, due to which the charges on carbon and fluorine will be more than that of charges on carbon and chlorine. And more the charges means more the dipole moment. So as per the charge factor is concerned, this has to be the dipole moment order. This has to be the dipole moment order. As per the charge factor is concerned, this has to be the dipole moment order. But if you remember, dipole moment, how did we define? It is the product of charge and distance. More the charge, more the dipole moment. But distance also is there, right? And this is the case where distance dominates over charge. Now, as per distance factor, let's see what should be the dipole moment. More the distance, more the dipole moment. See, the distance between C and F is less than that of the distance between C and Cl. So if I compare these two molecules, as per distance, distance between C and Cl is more than that of distance between C and F. So what is the order as per distance? Order as per distance is 2 should have more dipole moment than 1. As per charge factor, 1 should have more dipole moment than 2. As per distance factor, 2 should have more dipole moment than that of 1. And this is the case wherein distance dominates over charge. Distance factor dominates over the charge factor. And eventually, after seeing both, what is the final order of the dipole moments? The dipole moment order is going to be 2, then 1, then 3, then 4. This is the actual order of the dipole moments over here. I hope this is clear to everyone. Yeah? Yeah? Perfect. And this is the only question wherein you have to see the distance factor. All the other questions, you will see the charge factor. You will see the electronegativity difference factor. More the electronegativity difference, more is going to be the dipole moment in all the other cases. I hope this is clear, right? Okay, for example, you have got H2O and H2S. Where do you see the dipole moment more? H2O or H2S? Quickly. The bond is between O and H. The bond is between S and H. Electronegativity difference between oxygen and hydrogen is more than that of electronegativity difference between hydrogen and sulfur. More the electronegativity difference, that means more is the charges on the atoms, and hence more is going to be the dipole moment. I hope this is clear. Right? Okay. NH3PH3. Nitrogen and hydrogen. Phosphorus and hydrogen. Electronegativity difference between nitrogen and hydrogen is more than that of phosphorus and hydrogen. So more the electronegativity difference, more is going to be the dipole moment. I hope this is clear. Then you have got H2O and NH3. Tell me, where is the dipole moment more? Quickly in the charts. The bond is between oxygen and hydrogen. The bond is between nitrogen and hydrogen. Oxygen-hydrogen electronegativity difference is more than that of nitrogen and hydrogen. Due to which, this is going to be the dipole moment. Perfect. And my dear students, one last question. H2O and HF. The bond is between oxygen and hydrogen. Okay. Here the bond is between hydrogen and fluorine. So electronegativity difference between H and F is more. So this should be the dipole moment order. But as per your NCERT mentions it like this. So you have to remember this order only. Actually, HF should have more dipole moment than that of H2O. Right? That's the actual molecule. That's the actual answer. HF should have more dipole moment than that of H2O. But your NCERT mentions H2O to have more dipole moment than that of HF. So you are going to remember it directly. Right? You are going to remember it directly. Perfect. I hope this is clear to everyone. Yeah? Okay. Look at this question. Guys. Let's try to solve this. These are 4 molecules which are given. 1, 2, 3, and 4. We have to arrange them on the basis of their dipole moments. What do you think? What do you think? Quickly, what do you think? Understand. Chlorine is electronegative, then that of chlorine. It is electron withdrawing, so it will withdraw the electrons. So fluorine will get delta negative, this carbon will get delta positive. So the bond moment direction is in this way, right? Let's assume the magnitude of this vector is x. Let's assume the magnitude of this vector is x, right? Similarly, magnitude of this vector will be also x, and magnitude of this particular vector, it's also going to be x. Now, my dear students, if you look at this particular vector and this particular vector, what is the angle between the two? This is one vector whose magnitude is x. This is one more vector whose magnitude is also x. So, two vectors at an angle of 120. That means the resultant should be in this direction. And two vectors of equal magnitude at an angle of 120. The resultant is also x. So, resultant of this particular vector and this particular vector will be in this way, which will be whose magnitude will be also x. So, in the same direction, you have now x and x. So, the net dipole moment, its magnitude will be 2x. Its magnitude will be 2x, right? Look at this one. This is x, for example. This is x. And this is x. I'm just writing positive to negative, okay? Positive to negative. Now, my dear students, understand. This particular vector is upwards. This particular vector in this way. So, these two are same. These two are the vectors of equal magnitude at an angle of 120. So, the resultant has to be in this direction. At an angle of 120 means that means the resultant magnitude should be also x. Now, this is x, this is x. They'll cancel out. So, I would say the net dipole moment of this particular molecule has to be 0. Simple. Now, my dear students, look at this one. Positive to negative, positive to negative, positive to negative. So, this one directly gets cut and net dipole moment is going to be x. Perfect. Look at the last one. Positive to negative, positive to negative. If this is x, this is also x, cancelled out. So, net dipole moment of this molecule is also 0. Perfect. Now, arrange them. Arrange them, my dear students. Arrange them. So, we have got how many molecules with 0 dipole moment? Second and 4. Second and 4 have got 0. Which molecule has got maximum? First molecule has got maximum, followed by third. Then you have got 2 and 4, which have got 0 dipole moments. So, this is the order of the net dipole moment for this particular question if it is asked. I hope this is clear to everyone. I hope this is clear to everyone. Yeah? Okay. One more question I'm giving you. Let me see if you can solve this one or not. See, guys. This is chlorine on this side, chlorine on this side. Let me know in the chats whether the net dipole moment of this molecule is 0 or not. Quickly. Quickly. Quickly, guys. Okay, look at the first one. Chlorine more electron withdrawing, right? So delta negative, delta positive in this way. Over here in this way, cancelled out. So net dipole moment of this particular molecule will be 0, right? Look at this one. No doubt, OH, OH, OH and OH. Now you must be thinking, since two OH groups are at position 1 and 4, right? So they should cancel and its net dipole moment should be 0 as well. But that's not the case. This particular molecule, its net dipole moment is non-zero. Even this particular molecule, its net dipole moment also is non-zero, right? For example, if this is the structure, O and H, look at this bond, O and H. Oxygen is more electronegative. So delta negative, delta positive. In this way, delta negative, delta positive. In this way, do you see these two cancelling? These two are not cancelling each other. So net dipole moment of this molecule has to be non-zero. Even this one, S and H, they won't cancel. So net dipole moment has to be non-zero. So these things you have to remember, my dear students. These things you have to remember. Whenever you talk about dipole moments, these are few examples which you have to take into consideration. Okay, perfect. The question which was asked in NEET 2020, what do you think about this one? What do you think about this one? Which of the following set of molecules will have zero dipole moments? Zero dipole moments. Quickly. Quickly, guys. Over here, you have got hydrogen fluoride, HF. HF does not have zero dipole moment, so this cannot be the answer. Right? NF3. We saw NF3 few minutes back. It has got net dipole moment, so this cannot be the answer. Ammonia, NH3. NH3 has got dipole moment. We saw it few minutes back. This cannot be the answer. Right? So option C is the one which is correct. Yeah? This sort of equation you should be able to solve from now onwards. I hope all this is clear to you. Even if you want to have a look at their structures, you can check it out. These are the structures from which you can easily tell. See guys, this is one moment at an angle of 120. So resulted in this way. So resulted in this way. So this and this get cancelled. Net dipole moment is 0. And everywhere net dipole moment is 0. So these are the molecules whose net dipole moment is 0 basically. Okay. Perfect. Now, my dear students, let's start with one of the most important theories of the chapter, that is valence bond theory. So, what all things this valence bond theory tells us? First of all, whatever I've taught till now, is every single thing clear? Whatever I've taught, I've started everything from basics itself, right? As if you have never studied the chapter before. So you tell me in the chats whether every single thing is clear till here or not. Let me know quickly in the chats with the thumbs ups at least. Quickly. I want everyone to say it. Everyone, quickly. Quickly, guys. All right, people. So let's move on then. Let's get going. Let's start with something called as valence bond theory. One important theory this is, okay? So understand it properly. So first of all, what kind of information this theory gives us? My dear students, let me tell you, valence bond theory, it explains the formation of covalent bond. Valence bond theory is going to let you know how exactly covalent bond is formed. Valence bond theory is going to let you know how exactly covalent bond is formed between two atoms, right? Now, as far as this particular theory is concerned, the first important point of this theory, a covalent bond is formed by the overlap of atomic orbitals of the bonding atoms. In order to show the overlap, the bonding atoms must come close such that their orbitals can overlap. My dear students, understand. Whenever a bond has to be formed between two atoms, let's say this one atom, this one more atom, a bond has to be formed, a covalent bond has to be formed between these two atoms. First of all, in order to form a covalent bond, the bonding atoms, they must approach each other. They must come closer. Why should they come closer? So that their atomic orbitals, they can penetrate into each other. And let me tell you, penetration of atomic orbitals of bonding atoms into each other, that is something which you call as overlapping. So what is overlapping? Overlapping is simply defined as the penetration. It is simply defining as the penetration of atomic orbitals. Of bonding atoms. Of bonding atoms into each other. This is something which you call as overlapping. Now this overlap we have to discuss in detail. I just gave you the idea of what overlap is. So just one thing which you have to remember. Whenever a covalent bond has to be formed between two atoms, two bonding atoms, they should approach each other, they should come closer so that their atomic orbitals will merge into each other, so that their atomic orbitals will penetrate into each other, and penetration of atomic orbitals of bonding atoms into each other, that's something which you call as overlap. That's something which we call as overlap. And my dear students, what this theory says, a covalent bond is formed by the overlap of atomic orbitals into each other. So whenever you see atomic orbitals of two bonding atoms overlapping, just remember, covalent bond will be formed at that point of time. Due to overlapping only, covalent bond is formed, as per this particular theory, right? As per this particular theory. And in order to show overlap, the bonding atoms should come closer. Now, my dear students, for example, if I talk about the bonding atoms, let's say this is one bonding atom whose nucleus is this. And this is the electron, for example, of this particular bonding atom. Let's say you have got one more bonding atom whose nucleus is this. And this is the electron of this particular bonding atom. Now, in order to form a bond, they should come closer so that their atomic orbitals will penetrate into each other, right? But before talking about that, let me tell you, when these bonding atoms will approach each other, let's exactly get to know what kind of forces will exist between the two. Let's see what kind of forces arise when these two bonding atoms will approach each other. My dear students, first of all, this is the electron. Can I say there is force of attraction between the nucleus and this particular electron in this direction? You know it. Similarly, this particular nucleus, it will be pulling its electron towards itself, right? Perfect. Can I say at the same time, this particular nucleus will be attracting this particular electron towards itself? Absolutely. This particular nucleus, it will be attracting this particular electron towards itself? Absolutely. Yeah. Right? Now, dear students, one more thing. This is the nucleus, this is the nucleus. Can I say there will be repulsions between these two nucleus as well? Right? Like charges, repulsions. Electron, a repulsion as well. So, can I say when the atoms approach towards each other, two types of forces, they come into play. Attractive forces and repulsive forces. Two types of forces come into play. One is attractive forces, another one is repulsive forces. Attractive and repulsive forces. When the atoms approach each other, two types of forces arise, attractive and repulsive. My dear students, few things I would want to tell you. Attractive forces, they try to increase the stability of the system. They try to increase the stability of the system. Attractive forces, they stabilize the system. Repulsive forces, they destabilize the system. They destabilize the system. Why is that? Why is that? One thing which every one of you must be knowing. Stability is inversely proportional to energy. More the energy possessed by the system, lesser is going to be the stability. Less the energy possessed by the system, more is going to be the stability. So, lesser the energy in the system, more stability. More energy in the system, less stability. Now, I have already mentioned one thing before. Due to attractions, energy is released. Due to attractions, energy is released. My dear students, due to attractions, energy is released. If energy is released, the system will be having less energy after the release of energy. And if the system has less energy, its stability will be more. So I'll categorically say attractive forces, they try to stabilize the system. Whereas if I talk about repulsive forces, due to attractions, energy is released, the energy possessed by the system becomes low, due to which stability increases, right? If I'm releasing energy, so the amount of energy with me, that decreases with time, correct? Simple. And due to repulsions, energy of the system increases. And if the energy of the system increases, stability decreases. So attractive forces, they stabilize the system. Repulsive forces, they destabilize the system. Point number one. Point number two, my dear students, which I would want to share with you. What is that? Let's have a look. Understand. For example, I have got two atoms. These are two atoms right now, okay? And I'm assuming that these two atoms are right now at infinite distance apart. These two atoms are right now at infinite distance apart. Let me tell you, when the atoms will be at infinite distance apart, force of attraction between them will be 0, right? So right now the atoms are at infinite distance apart. So force of attraction between them must be 0. Now guys, when these atoms will start coming closer, what will happen? Distance between them will decrease. If the distance is decreasing, that means force of attraction will be increasing. Imagine that this is a positive charge, this is a negative charge. Imagine that as if this is positive charge, this is negative charge, right? They are initially at infinite distance apart. Force of attraction between them has to be 0, right? Now, they start approaching towards each other. Distance between them is decreasing. Force of attraction is increasing. Force of attraction is increasing. Force of attraction is increasing. There will be a scenario when the atoms will be at maximum closest distance. There will be a scenario when the atoms will be at maximum closest distance. And when the atoms will be at maximum closest distance, at that point of time, force of attraction between the atoms will be maximum. Force of attraction between the atoms will be maximum. And at that point of time, whatever is the distance from the center of one atom to the center of another atom, that distance is something which you call as bond length. So over here, basically, a molecule has got formed. Over here, a molecule has got formed. That's why the force of attraction between the atoms right here is maximum, right? So the distance between their centers is going to be the bond length. Perfect? Right? I hope this is clear. Guys, who is this? Who are these people who are spamming? Let me just block them just a second. This one is gone. Who was this? Rao Saab, who is this? No. Gone. They are done and dusted. Okay. Perfect. So I hope you got this particular point. When the atoms were at infinite distance apart, force of attraction between them was 0. Now the atoms are coming closer. Distance between them is decreasing. Force of attraction is increasing. Now there will be a scenario when the atoms will be at maximum closest distance. At that point of time, force of attraction between them will be maximum, right? That means a molecule has got formed over here. Initially the atoms were far, now they're coming closer. Over here, molecule has got formed, right? Force of attraction between the atoms is maximum, and the distance between them is something which I call as bond length. My dear students, just tell me one thing, one important thing. If I want these atoms to come a little more closer, do remember, repulsive forces will start there. So, can I simply generalize a statement that attractive forces, they are long-range forces. Attractive forces, they are long-range forces, right? They arise at greater distances. Whereas if I talk about repulsive forces are short-range forces. Repulsive forces are short-range forces. Repulsive forces are short-range forces, right? Repulsive forces arise when the distance is very, very, very small. Attractive forces arise when the distance is large, right? So repulsive forces, they are short-range forces, whereas attractive forces, they are long-range forces. Attractive forces exist at larger distances. Repulsive forces exist at very smaller distance. I hope this is clear. Now, if this is clear to everyone, let's try to analyze and understand a graph over here. But before talking about the graph, this is the point. When the atoms approach, two types of forces will arise. One is attractive force, one is repulsive force. Due to attractive force, what happens? Attractive force stabilizes the system, right? Increase the stability of the system, right? Whereas repulsive forces, they decreases the stability of the system. And stability, that's inversely proportional to energy. You know it. Perfect. And attractive forces are long range, whereas repulsive forces are short range. Perfect. If it is clear, then there is one graph which is really, really very important. What is that? That is the graph between potential energy and internuclear distance. Try to understand this particular graph. This is important, guys. You have to understand this. You have to understand this particular graph. Okay? See. Try to understand this particular curve carefully. What is happening to this here? Okay. This y-axis, it represents the potential energy of the system. Potential energy of the system, which I'm representing with U. And this particular axis, it represents internuclear distance, which is represented by R. Internuclear distance, which is represented by R. Try to understand what exactly I'm going to say. My dear students, just one thing which you need to analyze over here. What is that particular thing? If I start from this particular point, what are the coordinates of this point? This is the origin basically. This is the origin. Its coordinates are 0, 0, right? So R value over here is 0. R value is tending towards 0, right? So the distance between the atoms is tending towards 0. That means atoms are very, very, very close. When you move far, that means R value is increasing. Internuclear distance between the atoms, that's increasing. That's increasing. That's increasing, right? So over here somewhere, can I say there will be R tending towards infinity also? Somewhere there will be R tending towards infinity. That means that point will represent when the atoms are at infinite distance apart. I'm assuming the atoms are at infinite distance apart. So I'm starting from here somewhere, right? Atoms are at infinite distance apart. And you know, when the atoms are at infinite distance apart, force of attraction between them is 0. Force of attraction between them is 0. Now, come from right to left. If you are coming from right to left in this direction, R value is decreasing. That means if R is decreasing, internuclear distance is decreasing. That means atoms are coming closer. If atoms are coming closer, distance between them is decreasing. Force of attraction is increasing. Energy is released. Energy with them, that decrease with time. That decrease with time. Right? If you move from positive towards negative, if you move from right to left, that means R value is decreasing. Atoms are coming closer. Distance between them is decreasing. Force of attraction is increasing. If the force of attraction is increasing, energy is continuously released by the system. So energy possessed by the system, that decrease with time. So energy possessed by the system, that decrease with time. So it is decreasing with time. Energy possessed by the system, that is decreasing with time. Correct? For example, this is the minimum value of energy of the system. This is the minimum value of energy of the system. Minimum value of energy of the system means the system is maximum stable. Minimum value of energy means the system is maximum stable. When is the system maximum stable? When the force of attraction between the atoms will be maximum. So this is the point at which the force of attraction between the atoms is maximum. That means the atoms are right now at maximum closest distance. The atoms are right now at maximum closest distance, which tells you that the force of attraction between the atoms is maximum. And whatever is the distance at this point, whatever is the distance between the two, between the nuclei of these two atoms, that's something which you call as bond length. Perfect? That's something which you call as bond length. Now, my dear students, if you want these atoms to go a little more closer, what will happen? Repulsive force will increase. And repulsive forces, what do? They tend to increase the energy of the system. So if I want these atoms to come a little more closer, if I move further in this direction, if I decrease the value of R a bit further, that means I want these atoms to come closer. So distance between them is decreasing, but now repulsive force will start, and repulsive forces will tend to increase the energy of the system. So this is how the graph looks like. This is the minimum value of energy. And at the minimum value of energy, the system is considered to be maximum stable. The system is considered to be maximum stable. I hope this is clear to everyone. At the same time, my dear students, the distance from here to here is something which you call as bond energy. Perfect? It's called as bond energy. The amount of energy which is needed to break 1 mole of bonds, basically. That's something which I'll discuss afterwards. Leave that part aside. Yeah? Over here, we have got one important point to discuss. What is that? At this particular point, if I want you guys to draw a tangent, can you draw a tangent at this point? Yes, you can. This is the tangent, right? If I ask you, what is the slope of the tangent at this point? Slope of the tangent at this point is 0, basically. right? Slope of the tangent at this point is 0. How can we represent that mathematically? Slope of the tangent at a point that is represented by dy by dx. But along y-axis you have got u, along x-axis you have got r. Can I say at this particular point, du by dr value is coming out to be 0? What does that mean? That means the slope of tangent at a point on potential energy versus internuclear distance curve, right? So at this particular point, when the energy of the system is minimum, right? When the molecule formation has taken place, when the force of attraction between the atoms is maximum, right? When the distance between the atoms is what we call as bond length, at this particular point, du by dr, this value has to be 0. Right? At this particular point, du by dr value has to be 0. Now, my dear students, if you got to know this particular point, how can we relate it with the questions? How can we relate it with the questions? I'm going to give you one question so that you can understand and analyze it properly. See, one simple question I'm giving you. The variation of potential energy with R between two atoms A and B. This is the variation of potential energy with R. Calculate the bond length. Calculate the bond length. My dear students, when we need to calculate bond length, at the point of bond length, that means atoms are at maximum closest distance. Energy of the system is minimum. At that point, du by dr value has to be 0, right? So I got to know one important thing. Du divided by dr value has to be 0. Then only I can calculate the bond length, right? Perfect. Now guys, understand. Du by dr. That means you have to differentiate this u with respect to r. Now differentiate it. Differentiate this u with respect to r. So I'll be writing du divided by dr. Du by dr will be equal to, it is basically going to be 6r raised power minus 2, or let me write it like this first of all, just a second. Ur is equal to, it is 6r raised power minus 2 plus 3r plus 2. Correct? Now differentiate it. Du divided by dr is equal to, it's going to be 6 as such, x raised power n is x nx n minus 1, right? So it's going to be minus 12 r raised power minus 3 plus this is going to be 3, that's it. Now du by dr value, this has to be 0. So I would say minus 12 r raised power minus 3 is equal to minus 3. So minus minus cancel. If minus minus cancel, you got to know r raised power minus 3 is equal to 3 divided by 12. 3 divided by 12 is 1 by 4. So r raised power minus 3 is equal to 1 by 4. Perfect. R raised power minus 3 is equal to 1 by 4. Right? So that's it. You can get the value of r from here. Correct? Perfect. So my dear students, the final answer of this particular question, that is done now, right? That is done. So this r, can't you solve this after? Okay, r raised power minus 3 is basically 1 by r. 1 by r cube. 1 by r cube is equal to 1 by 4. If you take the reciprocal, r cube is equal to, r cube will be equal to 4 after taking the reciprocal. If you take the cube root on both the sides, r will be equal to 4 raised power 1 by 3. Let's assume r is to be calculated in angstroms. So this is the answer of the question, right? This is the answer of the question. This is the bond length between A and B. Perfect. Right? So I hope if a question is asked from the curve, you can easily solve it. Just one simple statement that at the bottom, the slope of the tangent is 0. That's all. I hope this is perfect. Now guys, basically what we are doing, we are trying to understand, we are trying to study valence bond theory now, right? Valence bond theory, what it says, it explains how covalent bond is formed. And how covalent bond is formed by when the atomic orbitals of the bonding atoms, when they overlap. What is overlap? Penetration of atomic orbitals of bonding atoms into each other. That's something which we call as overlap. And due to the overlapping, what happens? Covalent bond formation takes place, right? Covalent bond formation takes place. Perfect. Now exactly we are going to discuss this overlapping in detail. What is overlapping? Penetration of atomic orbitals into each other. That's something which you call as overlapping, right? This is something which I have to tell you in detail in some time. Before that, let me tell you the rules for overlapping. Whenever two atomic orbitals overlap, whenever two atomic orbitals of two bonding atoms overlap, it leads to the formation of covalent bond. And strength of the covalent bond strength of the covalent bond that depends on the extent of overlap. More the overlap happening between the atomic orbitals, stronger is the bond. Remember this. What is the reason? You'll get the idea in some time. You'll get the idea in some time. Right? Greater the extent of overlap between the atomic orbitals, do remember, more will be the strength of the bond. One point which I would want you guys to remember. And after the overlapping is done, the electron density, it will arrange itself in such a way that it comes under the influence of both the nuclei. What does that mean? For example, this is the atomic orbital 1. This is one more atomic orbital, right? This is atomic orbital of one bonding atom. And this is atomic orbital of one more bonding atom. Let's say they're approaching towards each other and they're overlapping. They overlapped like this. This is how overlapping took place. For example, just to make you understand, I'll be teaching you this in detail in some time, right? Over here, can I say overlapping has happened? Penetration of atomic orbitals into each other, due to which what happened? Covalent bond formation takes place. Now, my dear students, this electron density, it arranges itself in such a way that it comes under the influence of both the nuclei. So final, as a resulting shape of the molecular orbital will be like this. A resulting shape, this is the nucleus, this is one nucleus, this is one more nucleus, and electron density has arranged in such a way that it came under the influence of both the nuclei. Right? This is the statement which I'm talking about. Yeah? This is the statement which I'm talking about. Right? Now guys, before understanding all these things in detail, this was just the overview of the things. Before understanding these things in detail, let's try to go for the types of overlap, from which you can understand exactly how this overlapping exactly happens. Right? Perfect. So my dear students, we have got two things over here. Overlap is of two types. One is called as axial overlap. One is called as parallel overlap. What is axial overlap? Axial overlap happens between the atomic orbitals along the axes. Do remember, due to axial overlap, always sigma bond formation takes place. The bond which gets formed due to axial overlapping, that's called as sigma bond. In case of parallel overlapping, what happens exactly? In case of parallel overlapping, atomic orbitals, they overlap by keeping their axes parallel. And do remember, due to parallel overlapping, which type of covalent bond is formed? Either pi bond is formed or delta bond is formed. Right? Covalent bonds are basically of many types. One is called as sigma bond, one is called as pi bond, one is called as delta bond. Due to axial overlapping, always sigma bond formation takes place. Due to parallel overlapping, always pi bond takes place or delta bond can take place. Now let's understand properly in detail how these sigma and pi bonds, they are being formed. So first of all, I am marking the heading over here as axial overlapping. This is the first type of overlapping which we are going to discuss. Axial overlapping. So my dear students, in case of axial overlapping, what happens? I'll say atomic orbitals penetrate into each other along the axes. And let me tell you, due to axial overlapping, what happens? Due to axial overlapping, always, which type of covalent bond is formed? Sigma bond is formed. Sigma bond is one type of covalent bond, basically. Now, let's try to understand how this axial bond formation, how this axial overlapping happens. My dear students, the first type of axial overlapping, which I'm going to discuss with you, that's what I'm calling SS overlap. SS overlap. What does that mean? That means the s orbital of one atom and s orbital of one more bonding atom, they are going to come closer. They'll do the head-on overlapping. Axial overlapping is also called as head-on overlapping. It's also called as head-on overlapping as well. Now have a look. SS overlapping. Let's assume this is the s orbital of one atom and this is s orbital of one more atom. Okay, perfect. S orbital of one atom, s orbital of one more atom. Let's assume this is the internuclear axis, which is generally taken as z-axis. Z-axis is generally taken as internuclear axis. Okay, let me write it over here so that I get space. This is z-axis, which is my internuclear axis over here. Now these atomic orbitals, what do they have to do? If I ask you whether these atomic orbitals are approaching along the axis, yes. So what kind of overlap they'll do? They'll do the head-on overlap. They'll do the head-on overlap. They'll do the axial overlap. My dear students, now this axial overlap, it can happen in two ways. It can happen in two ways. Understand? I'm going to give some signs over here. Let me write positive over here. Let me write positive over here. These are not the charges. These are not the charges. These are not the charges. What is the significance of these signs? You'll get the idea in some time. Let me tell you two things can happen over here. Either positive overlap will happen or negative overlap will happen. Always remember, a bond is formed always by the positive overlap. Through negative overlap, bond is not formed. Positive overlap, it leads to the formation of bond. It leads to the formation of bond. Which bond I'm talking about? Formation of covalent bond. Positive overlap. Negative overlap, it does not lead to the formation of bond. Okay? My dear students, now the point is, how can I show whether the overlap happening between the two is positive or not? That's why I've given the signs over here. This is positive, this is positive. If I'm keeping same sign, it represents positive overlap. It represents positive overlap, or you call it as in-phase overlap as well. You call it as in-phase overlap as well. Now, they're going to overlap. Now they are going to overlap, right? This is positive, positive, right? Now, my dear students, what has happened exactly? If I ask you what has happened, penetration of atomic orbitals into each other, right? Axial overlap, head-on overlap. It leads to the formation of what? It leads to the formation of sigma bond, right? It leads to the formation of what? It leads to the formation of sigma bond. So over here, which bond got formed? Sigma bond got formed. And how does it look like? The electron density will arrange in such a way, that it comes under the influence of both the nuclei, right? So final representation of it will be like this. Okay, this is the electron density, which came under the influence of both the nuclei. And which bond got formed? It is basically the sigma bond which got formed by the head-on overlap. Okay, so this was SS positive overlap. Now, if I ask you how to show SS negative overlap, then you just have to change the sign. If this is positive, you have to show it as negative. Okay, you have to show it as negative. So positive, negative. Perfect. Opposite signs. So you call it either as negative overlap, or you call it as out of phase overlap. And due to negative overlap or out of phase overlap, covalent bond formation, that does not take place. Okay, so this was your SS positive overlap, SS negative overlap. Second, that is SP overlap. From the name itself, you can understand this. One of the s orbital of one atom and p orbital of one more atom, they are going to penetrate into each other. Let's assume this is s and this is p of one more atom. Let's say this is positive, this is negative. So which overlap this is? First of all, is it the axial overlap? Yes, this is the axial overlap. They are going to penetrate into each other along the axis. This is the head-on overlap. And same sign on same side. So first of all, it is the head-on overlap. It is the in-phase overlap, or you call it as a positive overlap. Due to which, is this axial overlap? Yes, this axial overlap. Axial overlap leads to the formation of sigma bond, right? It leads to the formation of sigma bond. So this is the common electron density over here. This is something which you call a sigma bond over. This is sigma bond, right? If you want to show the negative overlap, out of phase overlap, this is in phase overlap, right? This is in phase overlap. Now out of phase overlap. This, for example, positive. This is negative. This is positive. Opposite sign on same side. Opposite sign on same side. You call it as negative overlap, or you call it as out of phase overlap, which does not lead to the formation of any covalent bond. Perfect. Then, talking about the third overlap, third axial overlap, that is PP overlap. PP axial overlap. I'm just talking about axial overlap right now. Okay? I'm just talking about the axial overlap right now. Let's assume this is your PZ. Let's assume this is p orbital of one more atom. These are two bonding atoms. Basically, they're p orbitals. They're approaching towards each other, and they're approaching along the axes. Right? Let me give the signs as well. Let's say this is negative. Let's say this is positive. Let's say this is positive. Let's say this is negative. First of all, tell me whether this is axial or parallel. This is head-on overlap, axial overlap. It will lead to the formation of sigma bond. So sigma bond will get formed. Whether they will show positive overlap or negative, it's going to be positive overlap, or you can call it as in-phase overlap. This is in-phase overlap. And how exactly the molecular orbital looks like? It will look like this. Have a look. This is showing negative. This one is negative, and in the middle, this is positive, right? This is positive in the middle. So, due to axial overlapping, what happens? Due to axial overlapping, what happens? Sigma bond gets formed. So, it's again a sigma bond, which got formed by positive overlap between PZ and PZ. Let's say this was PZ orbital. Let's assume this was one more PZ orbital, right? If I want you guys to show the negative overlap, you can do that as well, right? You just have to change the sign. Let's call this positive. Let's call this as negative. Let's call this as negative. This as positive. Opposite sign on same side. So this is what you call as out of phase overlap, or you call it as negative overlap. Negative overlap or out of phase overlap. And negative or out of phase overlap, it does not lead to the formation of bond. I hope this is clear. I hope this is clear. Yeah? Perfect. Now, my dear students, you got to know, due to axial overlapping, sigma bond formation takes place. Perfect. Now we have to understand the parallel overlapping. Now we have to understand the parallel overlapping. Parallel overlap. Through parallel overlap, which bond gets formed? Either pi or delta. Majority of the times it's going to be pi bond. Through parallel overlapping, pi bond gets formed, right? Perfect. The first example which will exactly show us how pi bond gets formed through the parallel overlap. Case number 1. Now I'm only going to show the positive overlaps. I'm not going to show the negative overlaps. That's understood now, right? Okay. So first of all, PP parallel overlap. PP parallel overlap. In this particular overlap, the axes have to be parallel. Let's say this is p orbital of one atom. This is one more p orbital of one atom. These are the axes which I'm talking about, right? Now, my dear students, these atomic orbitals of two bonding atoms, they are going to come closer, right? With their axes parallel. So this kind of overlap is something which I'll be calling as parallel overlap. Now, since I have to show positive overlap, let's give them the sign. This is positive, this is negative. This is positive, this is negative. Same sign on same side. So I'll be calling it as in-phase overlap, positive overlap, right? In-phase positive. In-phase positive. Now, imagine as if when they approach each other, the lobes bend towards each other. Imagine as if the lobes have bent towards each other, like this. Imagine as if the lobes have bent towards each other. So what has happened? This is the overlap over here. This is the overlap over here. Perfect. And this particular overlap is something which I call as parallel overlap. And through parallel overlapping, which bond gets formed? It is basically the pi bond which has got formed over here. It is basically the pi bond which has got formed over here. And finally, how do I represent it? See finally. This is the electron density over here, and this is the electron density, so I'll be representing it like this. This is the electron density, and this is the electron density, right? My dear students, in the middle, if you observe things in the middle, there is basically one plane. There is basically one plane. So basically there's a plane, it is a plane, and if this is a plane, above which there is electron density, and below which there is electron density. On this plane, there is no electron density. On this plane, there is no electron density. And that plane on which there will be no electron density, you'll be calling that plane as a nodal plane. So how many nodal planes are here? There is one nodal plane. Okay. Which bond got formed over here? This is something which I call as pi bond. Now, which pi bond this is? This is something which I call as p-pi bond. This is something which I call as p-pi bond. I hope this is clear. Yeah, I hope this is clear. NP represents nodal plane. Okay, this was the first type of parallel overlap, PP overlap. Now, second is PD parallel overlap. PD parallel overlap. PD parallel positive overlap I'm showing. Okay, by the way, if you have to show the negative overlap, then this is positive, this is negative. Make this negative, this positive. Opposite sign on same side. Negative overlap, which does not lead to the formation of bond. Right? Okay. Now try to understand one more thing. Now it's going to be PD overlap. For example, this is the p orbital, positive, negative. Now d orbital of one more bonding atom. This is the d orbital of one more bonding atom. Give the signs. I have to show the positive overlap. If this is positive, this has to be positive. If this is positive, this is negative. Negative, negative. And this has to be positive. Perfect. Right? Now, this is again going to be what? This is again going to be a parallel overlap. And parallel overlap leads to the formation of what? Pi bond. And how the overlap looks like? See, this was your P. And this D would have penetrated like this. It would have penetrated like this. This is the common electron density over here. This is the shared electron density over here. Perfect. So this particular bond over here I'll be calling as p-pi d-pi bond. Right? Were they in phase or out of phase? This was in phase overlap. This was positive overlap. This was positive overlap. And this was parallel overlap as well. And due to parallel overlapping, which bond is formed? It is basically the pi bond which gets formed over here. Right? It is the pi bond which gets formed over here. So this is p-pi d-pi bond. Now, talking about the third overlap. The third overlap is going to be d-pi d-pi overlap. Or I'll be calling this as two-lobe interaction. I'll be calling it as two-lobe interaction. Okay. My dear students, let's assume this is the d orbital of one atom. And over here, I've got one more d orbital of one more bonding atom. So I've got two bonding atoms whose d orbitals I've taken into consideration. Okay. Whose d orbitals I've taken into consideration. Let me call this as positive. So this has to be negative. Let me call this as negative. So this has to be positive. Right? If this is positive, this should be positive as well. This should be negative. If this is negative, this has to be negative. This has to be positive. Just to show the positive overlap. Right? Now, my dear students, these lobes are going to interact. Parallel overlapping this again. And parallel overlapping, is it positive parallel? Yes, this is positive overlap. This is again in phase overlap. This is again in phase overlap. And due to this in phase overlap, due to this parallel overlap, first of all, what happens? Pi bond formation takes place. Right? Pi bond formation takes place. So it's going to be like this. Right? You can give the signs as well. This is the common electron cloud over here. So since it was the parallel overlap, so pi bond got formed. Since two lobes have interacted, that's why you call it as two-lobe interaction. At the same time, this pi bond which got formed by the parallel overlap, this is something which I call as d-pi d-pi overlap. So d-pi d-pi bonding. One is p-pi p-pi bond, one is d-pi d-pi bond. One was p-pi d-pi. Now after this, one last, that is something which I call as, which is again d-pi only. It's again d-pi d-pi only. Basically, I should write dd overlap. I'm writing d-pi d-pi, right? So this is not going to be two-lobe now. It's going to be four-lobe interaction. It's going to be four-lobe interaction. How it looks like. So one of the d orbitals of one bonding atom, positive, negative, negative, positive. One more d orbital of one more bonding atom. So I've got two bonding atoms who are supposed to form a bond basically, right? who are supposed to form a bond. Perfect. Now these two orbitals, they overlapped like this. They overlapped like this. Perfect. Now these two orbitals, they are not going to overlap like this. They'll overlap one over the other. One over the other. If they overlap one over the other, that means this particular lobe is going to overlap with this one. This particular lobe is going to overlap with this one, right? Similarly, this lobe is going to interact with this one, and this lobe is going to interact with this one, right? This particular interaction is called as four-lobe interaction, due to which bond is formed? It is going to be delta bond which gets formed due to four-lobe interaction over here. I hope this is clear to everyone. So quickly in the chats if it is clear. Quickly in the chats if all the things are clear till here. Quickly, people. Wait, Prajwal, I'll show you the oxygen molecules as well. Just wait. Don't jump. I'll show you the formation of oxygen, nitrogen, everything. Just wait. Do not be smart. Your teacher is smarter. Okay, let's move on. I hope all these things are clear. All right, guys, just a second. All right, few more basic things which you need to know. We are going to compare now the strength of pi and sigma bond. Let's try to understand the strength of pi and sigma bond. My dear students, do remember sigma bonds are stronger than that of pi bonds. What is the reason why sigma bonds are stronger than pi bonds? There are many reasons. There are many reasons. First reason is, that's very simple. That is about the extent of overlap. Extent of overlap, extent of actual overlap, that is greater than that of extent of parallel overlap. Actual overlap leads to the formation of sigma, parallel overlap leads to the formation of pi. If extent of actual overlap is more, extent of actual overlap is more, right? You know, strength of bond. Strength of bond, that is directly proportional to extent of overlap. More the extent of overlap, stronger is going to be the bond. If the extent of overlap in actual is more, that means the bond which gets formed here, that will be stronger. That will be stronger, right? That will be stronger. This is one factor by means of which you can explain why sigma bonds are stronger than pi bonds. The reason is extent of overlap in actual is more than that of extent of overlap in parallel overlap. Yeah? Number two, there is one more reason. That is energy factor. This is overlap factor. Second reason is energy factor. Energy factor also tells us why exactly your sigma bonds are stronger than that of pi bonds. How exactly? For example, let's say this is the sigma bond over here. Right? This is the sigma bond, which is formed by the direct head-on overlap. Okay? Now, over here, for example, let's say this was PP overlap, so let's make it like this. Let's make it like this. This was PP overlap, for example. PZ overlap, something like that. This was the actual overlap through which sigma bond got formed. Now, what about the pi one? Pi overlap looks like this. Sideways overlap looks like this. Your pi bond looks like this. Perfect. In between, there's the nodal plane. This is the nucleus. This is the nucleus. Right? Now, my dear students, if this is the nucleus, for example, if this is the nucleus, between these nucleus, this is the nucleus of one atomic orbital. This is the nucleus of one atom. This is the nucleus of one more atom. Now, these atomic orbitals came, right? They merged into each other, right? They formed a molecular orbital. This is, for example, a molecular orbital. This is the nucleus. This is one nucleus. This is one nucleus. This is one nucleus. This is one more nucleus of this molecular orbital. Now, as you can see, between these two nucleuses, what do we have? We have got electron density. We have got electron density. So I would say these two nucleuses, they are not in direct contact. There is electron density in between. But look at these two nucleuses. Is there any electron density in between? No, it's a nodal plane on which electron density is 0. Right? There is no electron density in between. Now imagine where will be the repulsions between the nucleus more. Over here, this electron cloud, it is becoming a shield. It is becoming a shield towards the repulsions between these two nuclei. Right? Over here, there is no shield towards the repulsions. So repulsions between the nuclei will be more here. More the repulsions, more the energy, less the stability. Less the stability means lesser is the strength of the bond. Right? So do remember, strength of sigma bond is greater than that of strength of pi bond due to energy factor as well. Perfect. Over here, there is no electron density in between. There is electron density. Perfect. There is electron density. So repulsions will be more in the second case. Repulsions more, stability less. Right? Energy more. Perfect. Energy more, stability less means energy more, stability less. Stability less means strength of this bond is less than that of strength of this particular. I hope this is clear to everyone. Now guys, if this is clear, do remember these basic points. These basic points are used to solve some questions. Look at this particular statement. For the same energy shell, axial overlap. For the same energy shell. For example, you have got 2s, they are doing the axial overlap, right? Then you have got 2s, 2p, axial overlap. 2p, 2p, they are, for example, doing the axial overlap, right? For the same energy shell everywhere is same. Energy shell everywhere is same. Whenever energy shell is same, extent of overlap between 2p, 2p, between p and p in general is more than that of sp overlap, is more than that of ss overlap. But which overlap I'm talking about? I'm talking about axial overlap. I'm talking about axial overlap, right? I'm talking about axial overlap. So for the same energy shell, axial overlap between PP is more than that of SP, which is more than that of SS. And you know, more the extent of overlap, more is the strength of the bond. Perfect. So you get a question based on the bond strength. One of the bond is formed by 2p, 2p overlap. One more bond is formed by 2s, 2p axial overlap. One more bond is formed by 2s, 2s axial overlap. Which bond is stronger? It is the bond which is formed by 2p, 2p axial overlap that will be stronger. Right? That is the reason why I'm giving you this. Okay? And one more statement. If the orbitals are of different shells, then the lower energy orbitals, they produce more effective overlap. If the orbitals are of different shells, for example, S and S, this is 1, this is 2. So these orbitals, I mean 1s, 2s, 1s, 1s. Right? Similarly over here, 2p, 3p, 2p, 2p. Where is the extent of overlap more? It is simple. Lower energy orbitals, they produce more effective overlap. Where do you see the lower energy orbitals? Lower energy orbitals are here. 1s, 1s. Over here there is 2s. 1s, 1s. Lower energy orbitals. Okay? Right here, lower energy orbitals. 2p, 2p. Lower energy orbitals, they produce more effective overlap. Right? Do remember this thing as well. This will be used afterwards. Similarly, when you compare the strength of pi bonds, this is, by the way, this is something which I was talking about strength of sigma bonds. Perfect? I was talking about the axial overlap. I did not talk about the parallel overlap yet. I was talking about the axial overlap. Yeah? So, strength of pi bonds. Strength of pi bond is inversely proportional to internuclear distance. More the internuclear distance, lesser is going to be the strength of the pi bond. Similarly, this is one more order which I would want you guys to remember. 2p pi, 2p pi, strength is maximum, followed by 2p pi, 3d pi. Then you have got 2p pi, 3p pi. Then you have got 3p pi, 3p pi. This is one more order from which questions will be directly asked. I'll be giving you questions in some time. This is one more order which you have to remember. This is one more order which you have to remember. Right? This is one more order which you have to remember. This is important. And one more simple thing. For example, there is a triple bond between A and B. There is a triple bond between A and B. Do remember, the one bond will be sigma and the other two bonds, they'll be pi. They'll be pi. 1 sigma and 2 pi. Let's say there are 4 bonds between 2 atoms. Let's assume there are 4 bonds between 2 atoms. Let me tell you, one of the bond will be sigma. So it's 1 sigma. There'll be 2 pi also. There'll be 2 pi also. And one more will be delta. There is 1 delta as well. So 1 sigma, 2 pi and 1 delta. Right? Do remember always sigma bond formation takes place first. Sigma bond formation takes place first. Sigma bond formation takes place first. And after that, pi bond is formed. Followed by pi bond. Followed by pi bond. Do remember, between two atoms, sigma bond is formed first. After that, pi bond is formed. Okay? At the same time, guys, at the same time, there is one molecule, that is C2 molecule. This is something which I'll be teaching you in molecular orbital theory. In C2 molecule, let me tell you, both these bonds, these are pi bonds only. It is not one sigma and one pi. Both these bonds are pi bonds only. There are two pi bonds in C2. There are only two bonds and both the bonds are pi. Why is it? The answer you'll be getting in molecular orbital theory. Right? The answer you'll be getting in molecular orbital theory. Perfect. Now, guys, there is one more statement which I would want to share with you. Right? Carbon, double bond carbon, you have seen many a times. Right? Silicon, double bond silicon, it is rarely found. What is the reason? What is the reason? Because this pi bond over here, it is basically 2p pi, 2p pi pi bond. Right? It is found by 2p pi. It is found by 2p and 2p. By parallel overlapping of 2p and 2p. Whereas this particular pi bond, it has to be formed by 3p and 3p parallelly. And you know, extent of overlap, or few minutes back I told you, strength of 2p pi 2p pi is greater than that of strength of 3p by 3p pi. Right? Due to which strength of 2p by 2p pi is greater than that of strength of 3p by 3p pi. That's why this particular bond is stable. Right? So this particular carbon double bond carbon is frequently seen, whereas this is rarely observed. Right? Whereas this is rarely observed. My dear students, all these things, all these overlaps which I told you, let me try to show all these overlaps in the form of molecules now. Now this is going to be something important which you have to remember. Yeah? Have a look, people. For example, I'm taking one molecule as F2. I've got F2 molecule. Let me exactly show you how the formation of F2 takes place. How this F2 molecule is formed. Yeah? How this F2 molecule takes place. Have a look properly. Understand. My dear students, you have got two fluorine atoms. First of all, let's say this is one fluorine atom and this is one more fluorine atom. These are two fluorine atoms which I took. If I ask you what is the outermost configuration of fluorine, it is going to be 2p5. Outermost configuration of fluorine, it's going to be 2p5. Okay? It's going to be 2p5. Now, dear students, let me show you how this 2p5 exactly looks like. Let me show you how this 2p5 exactly looks like. So there'll be basically three orbitals here. Similarly, there'll be three orbitals here, right? This is 1, 2, 3, 4, and 5. Similarly, this is 1, this is 2, this is 3, this is 4, this is 5. Now, I have to show you how these two F atoms will combine. They lead to the formation of F2 molecule. They'll form a molecule. Okay? Perfect. Now, have a look. Let me first of all call this as 2px. Let me call this as py. Let me call this as pz. Similarly, let me call this as px. Or just wait. Just wait. Let me call this as pz. Let me call this as px. Let me call this as py. Similarly, let me call this as pz. Let me call this as px. Let me call this as py. So what exactly is going to be happening? Have a look. If you look at this particular configuration, there are three p orbitals. One is pz, right? Let's assume this is your z-axis. So it is going to be your pz carrying one electron. Pz is carrying one electron. Perfect. Pz is carrying one electron. Now similarly, px is carrying two electrons. This is for example your px. It's carrying two electrons. Similarly, you have got py as well. Which is again carrying two electrons. Perfect. Again carrying two electrons. One electron, two electrons, and two electrons. Similarly, my dear students, look at this fluorine. Look at this particular configuration. Pz carrying 1. Pz carrying 1. So I would say this Pz of another fluorine will come from this side and will do the overlap. Which overlap it is? It is head-on overlap. So sigma bond has got formed. Sigma bond has got formed. Now, my dear students, look at other things as well. Px is carrying 2. So this is Px, which is carrying 2 electrons. And similarly, there is Pz as well, sorry, Py as well, which is carrying 2 electrons. Let's assume that this is your Py over here, right? So look at this particular overlap. Is this head-on overlap or this is parallel overlap? This is head-on overlap, this axial overlap, which leads to the formation of what? It leads to the formation of sigma bond. So this is how your F2 molecule exactly looks like. This is how F2 molecule exactly looks like. Perfect. So how do I represent it? This is F, this is one more F. Perfect. This is F, there's a single bond and there is one more F. I hope all these things are clear to you. This is how your F2 molecule is formed. Yeah? Is it clear, people? Quickly once, let me know in the chats. Who is this nonsense Murtaza Nazir? Bro, why are you spamming? These type of people never qualify the examination, I'm telling you. Okay? I mean, from some other channel they are studying, they're coming here to spam. What is the logic? Nonsense. You tell me the logic why you're coming here. Are you the paid user? Is someone paying you to, spam all this? Nonsense. You should have been in front of me. Okay, so this is how F2 molecule formation takes place, and this is how your valence bond theory. This is how your valence bond theory, it explains the formation of F2 molecule. Yeah? Perfect. Similarly, let me show you how exactly O2 molecule formation takes place. Let's see how O2 molecule formation takes place as per VBT. Now you should be able to know exactly how O2 molecule formation takes place. Understand properly what I'm going to say. My dear students, understand. In order to form an O2 molecule, let's say this is one oxygen atom, this is one more oxygen atom. Now these two oxygen atoms, they'll approach each other, right? Their atomic orbitals will overlap. They lead to the formation of bonds. You know that. Now, first thing, if I ask you, what is the outermost configuration of this oxygen? This is 2p4. What is the outermost configuration of this oxygen? This is again 2p4. Correct? You must be knowing this. Now, how do I mention this 2p4 configuration? And how do I mention this 2p4 configuration? Understand properly what I'm going to say. This is important. Okay? So, these are first of all 3 p orbitals. Again, these are 3 p orbitals. 2p4 configuration. This is 1, this is 2, this is 3, this is 4. Similarly, this is 1, this is 2, this is 3, and this is 4. Correct? As simple as that. Now, my dear students, let me call this as Pz, let me call this as Px, let me call this as Py. In the similar way, let me call this as Pz, let me call this as Px, let me call this as Py. Perfect. Now, how they exactly look like. If I talk about this particular oxygen, if I talk about these 3 orbitals, one is your Pz. Let me assume this is your Pz, carrying 1 electron, right? Px, let me assume this is Px, carrying 1 electron, right? And this is Py. Let me assume this is Py, carrying how many electrons? Carrying 2 electrons, correct? Let me give you different shades of these orbitals so that you can understand this. So that there won't be any sort of doubt at all. Okay, so one is your Pz, Px, and Py. In the similar way, one more oxygen atom. If I talk about its Pz would have come from this side and done the axial overlap, right? So over here, which bond got formed? It is sigma. So sigma bond got formed. After that, my dear students, have a look. Px is carrying 1 electron. So this is, for example, Px carrying 1 electron. And similarly, there is Py as well, which carries 2 electrons. This is Py, which carries 2 electrons. Now, if I ask you one simple thing over here, Py is carrying 1 electron, Px is carrying 1 electron, even this Px is carrying 1 electron. Their x's are parallel. So can I say they'll show the parallel overlap here, and parallel overlap leads to the formation of what? It leads to the formation of pi bond. So how exactly you are going to represent it? This is one oxygen atom, this one more oxygen atom. Oxygen, oxygen. A sigma bond got formed first, and after that a pi bond got formed. So this is how your O2 molecule exactly looks like as per valence bond theory. Right? Right, people? One last example I'll take. Okay, last example is N2 molecule. N2 molecule. So this is something which you should know now. If I talk about the configuration of nitrogen, it is 2p3 configuration. One more nitrogen, it has got 2p3 configuration. Perfect. So just make the diagram over here. 2p3, 2p3. Correct? 1, 2, and 3. Similarly, this is 1, 2, and 3. Let me call this as px. Let me call this as py. And let me call this as pz. In the similar way, this is px. This is, for example, py. This is pz. Now, my dear students, have a look. Look at these 3 p orbitals. This is, for example, your pz carrying 1 electron. Right? This is, for example, your px carrying 1 electron. This is, for example, your pz carrying 1 more electron. Perfect. Now, similarly, look at this particular nitrogen which has got these 3 p orbitals. Again, pz, py, px. This is pz, right? Overlap leads to the formation of sigma. Perfect. Then you have got px. This is your px. This is a px carrying 1 electron. And then you have got pz, which is also carrying 1 electron. Pz is also carrying 1 electron. So overlap between two. This is parallel overlap. In the similar way, I must say, just a second. This is the overlap. This is the parallel overlap between these two. And apart from that, there will be parallel overlap between these two as well, because their axes, they are parallel. These are parallel, so parallel overlap. These are parallel, so parallel overlap. So how do you represent it? This is one nitrogen atom. There you have got one more nitrogen atom. These are 2 nitrogen atoms. First, sigma bond got formed, and after that, 2 pi bonds got formed. This is one more. So this is your N2 formation as per your valence bond theory. I hope this is clear to everyone. Yeah? Perfect. Is it clear, people? Is it clear, people? Perfect, guys. So with this, your valence bond theory is over. I think this much is enough for today. In the next session, there are 3 topics left now. One is hybridization, one is valence shell electron pair repulsion theory, and one is molecular orbital theory, right? And some bond parameters as well. That's something which we shall be discussing on Saturday. Coming Saturday, day after tomorrow, Saturday 5 p.m. I'll take one more session, which is going to be chemical bonding part 2, in which we'll be finishing this particular chapter. And we'll do all the PYQs which have been asked from this particular chapter as well. I hope whatever I've taught in this particular session, everything is clear, right? That's great, Zad. Well, Zad was my last year's YouTube student. He used to follow me, I remember. Glad that you are in NIT Nagpur. Glad about that. All right, guys. Chalo, I'll see you day after tomorrow then. So day after tomorrow, we'll complete this chapter. We have got 3-4 topics left. So let's try to complete them. Okay? Chalo, guys. Take care. God bless you all. See you in the next session. Perfect. So, my dear students, the first topic which I'm going to cover right now, let me exactly first of all tell you what is the need for hybridization. Before talking about the term hybridization, let's exactly get to know why do we need this particular concept? Why do we need the concept of hybridization? Let's get to know about that first of all, so that you'll get the exact idea of why we are using it and where do we use it and how do we use it. Okay, so need for hybridization. Why do we need the concept of hybridization? Before talking about the need of hybridization, in the last session we discussed valence bond theory, right? And as per valence bond theory, we got to know how covalent bonds are formed. I hope you remember, covalent bonds are formed by the overlapping of atomic orbitals into each other, right? Due to overlapping of atomic orbitals, right? That is something which leads to the formation of covalent bond. That can be sigma, that can be pi, that can be delta bond, right? Depending on which type of overlapping is happening basically. Is it axial overlapping? Is it parallel overlapping? All those things we have discussed in detail. Perfect. At the same time, one important thing I told you in the last session, strength of a bond is directly proportional to the extent of overlapping. I hope you remember that. I'm writing the same statement over here. Strength of a bond is directly proportional to what? It is directly proportional to extent of overlapping. More the overlapping, more is going to be the strength of the bond. Stronger is going to be the bond in short. This is something which we discussed in the last session as per VBT is concerned, right? Now, my dear students, let's get to know what was the need for hybridization. Why do we want to introduce this concept? To make you understand this particular thing, I'm going to take one molecule, that is CH4. The most common molecule which all of you must be knowing, methane, CH4, right? Dear students, if I ask you, which is the central atom over here in CH4? It is carbon, which is the central atom. I would want you guys to write the outermost configuration of carbon. If I ask you what is the outermost configuration of carbon, you'll say the outermost configuration of carbon is 2s2, 2p2. This is the outermost configuration of carbon. Perfect. If you exactly want to represent it, this is how you represent it. This is 2s containing 2 electrons, and this is 2p, which contains exactly 3 orbitals, and it contains 2 electrons as well. Perfect. This particular configuration of carbon, I'm calling it as the ground state electronic configuration of carbon. This is the ground state electronic configuration of carbon. Perfect. Now, my dear students, if I ask you, how many bonds carbon is forming over here? Carbon is forming exactly 4 bonds. Carbon is forming exactly 4 bonds. And how many unpaired electrons do we have here as per this configuration? As per this configuration, we have got 2 unpaired electrons. Now, my dear students, if carbon has only 2 unpaired electrons, then as per VBT, it should only form 2 bonds. As per VBT, it should form 2 bonds. But carbon over here, actually, how many bonds it's forming? It's forming 4 bonds, right? Carbon is actually forming 4 bonds. But as per VBT is concerned, since it has 2 unpaired electrons, so it should form only 2 bonds. But actually, it's forming 4 bonds. So what should happen? What should happen? I must say, over here, we should have 4 unpaired electrons. So in order to get 4 unpaired electrons, what is going to happen? I'll say excitation will take place. One of the electron from 2s will shift into 2p, right? Excitation takes place. And after the excitation is done, now check the excited state configuration of carbon. This is the excited state configuration of carbon. Now, my dear students, if I ask you how many unpaired electrons now carbon has, now it has got 4 unpaired electrons. So now it can form 4 sigma bonds as per VBT. Now it can form 4 bonds as per VBT, right? Now, dear students, if I ask you which orbital exactly this is the 2s orbital of carbon. This particular one, it is 2p, for example, 2px of carbon. This is 2py of carbon, and this is 2pz of carbon. Perfect. So over here, you have got 4 unpaired orbitals, right? Out of those unpaired orbitals, one of the orbital is 2s, and the other 3 are 2p. Perfect. Now, my dear students, as you can see, carbon is forming bond with hydrogen. It's forming bond with 4 hydrogen atoms. If I ask you, what is the outermost configuration of hydrogen? You should be knowing this. It is 1s1. It is 1s1, right? Hydrogen has got this unpaired electron. This is 1s1 configuration of hydrogen. Perfect. So can I say one of the s orbital, the s orbital of one of the hydrogen, the s orbital of one of the hydrogen will come from this side and will, or let me write it like this. I'll say this 1s orbital of hydrogen will come from this side, will start doing the overlap with this 2s of carbon. Similarly, one more 1s orbital of another hydrogen is going to come from this side, will start doing the overlapping. Similarly, one more 1s orbital of one more hydrogen, one more 1s orbital of one more hydrogen. So overlapping has happened over here. Perfect. So dear students, due to overlapping, what happens? So first of all, this is the 2s orbital of carbon and this is the 1s orbital of hydrogen. They are overlapping. And SS overlapping leads to the formation of sigma bond. So this is the sigma bond which is getting formed over here. Similarly, SP overlapping, one more sigma. SP overlapping, one more sigma. SP overlapping, one more sigma. So how many sigma bonds are being formed over here? Say 4 sigma bonds are being formed. 4 sigma bonds are being formed. But my dear students, if you notice one thing, out of the 4 sigma bonds, one of the sigma bond is formed by SS overlap. All the other 3 sigma bonds are formed by SP overlapping. If I ask you, will the extent of overlapping be same between SS and SP? Is the extent of overlapping between SS and SP same or different? It's absolutely different. And if the extent of overlapping is different, I'll say strength of these sigma bonds will be different, right? Because one sigma bond is formed by SS overlapping. Another sigma bond is formed by SP overlapping. So I would say if I compare these two bonds, since the extent of overlapping is different, so strength of bond will be different. And if strength of bond is different, let me tell you, strength of bond is inversely proportional to bond length. Stronger the bond, lesser the bond length. Stronger the bond, lesser the bond length. If my dear students, strength of bond is different, so I must say these 2 sigma bonds which are being formed over here, should they have same bond length or different bond length? As per this concept VBT, these 2 sigma bonds, they should have different bond lengths. Perfect. So as per VBT, since carbon is forming 4 bonds, as per VBT, the bond lengths over here between carbon and hydrogen, should they be same or different? They are supposed to be different. But experimentally, it was observed that all the bond lengths, all the CH bond lengths, experimentally it was observed that all the CH bond lengths in case of methane, experimentally was observed to be same. Experimentally, it was observed that all the CH bond lengths in case of methane, they are same, right? VBT could not explain why in case of methane, all the 4 CH bond lengths are same. As per VBT, these bond lengths should be different, right? But experimentally, it was observed that all the bond lengths are same. Perfect. And VBT could not explain exactly why all the 4 bond lengths are, why the bond lengths in case of methane, they are different. Now to explain why all the bond lengths in case of methane are same, explain that one more concept was introduced. That is what you call as hybridization. Exactly, I hope you got to know what was the need of hybridization. As per BBT, all the 4 bond lengths should be same. Sorry, all the bond lengths, the bond lengths in case of CH4, they should be different. Perfect. Because they are formed by different overlappings as per VBT. But experimentally, it was observed that all the bond lengths are same. So to explain why all the bond lengths in methane are same, a new concept of hybridization was introduced, right? Quickly, let me know in the chats if all the things are clear till here. Quickly, let me know in the chats if all these things are clear till here. Quickly, people, quickly. Quickly let me know in the chats with the thumbs ups, everyone. Yeah? So if you got to know the need of hybridization, then it is the time to discuss hybridization. One of the interesting topics of chemical bonding. Yeah? One of the interesting topics and one of the scoring topic as well, because question is asked almost every year from this concept, hybridization. So let's get to know what this hybridization exactly is all about. My dear students, the first point related to hybridization, I'll first write few points, then I'll make you understand one by one. Okay? First thing, hybridization, it is a theoretical concept. It is a theoretical concept. That means this hybridization, it does not have any experimental background. It is a complete theoretical concept, right? Complete theoretical concept. It does not have any experimental background. Now, what this hybridization says? Hybridization, as per hybridization is concerned, what happens in hybridization? My dear students, atomic orbitals of a particular atom, atomic orbitals of a particular bonding atom, they intermix. What happens in hybridization? Intermixing of atomic orbitals of a particular bonding atom that takes place. And due to the intermixing of atomic orbitals, what exactly takes place? New orbitals are formed. Due to the intermixing of atomic orbitals of a particular atom, some new orbitals are formed, which are basically identical in all the respects. Identical in shape, identical in energy, identical in size, right? So I'll say identical in all respects. So the new orbitals which are formed due to the intermixing of atomic orbitals of a particular atom. Due to intermixing, what happens exactly? Due to intermixing, new orbitals are generated, and those new orbitals, they are identical in all the respects, be it energy, be it shape, be it size. And my dear students, those new orbitals which are formed due to the intermixing of atomic orbitals of a particular atom, those new orbitals are what you call as hybrid orbitals. Those are what you call as hybrid orbitals. So basically, what happens exactly? What happens? I would say hybridization is nothing. It is just the intermixing of atomic orbitals of a particular atom, right? Intermixing of atomic orbitals of a particular atom. What happens due to the intermixing? Due to intermixing, new orbitals are generated, and those new orbitals, they are identical in all the respects, be it energy, be it shape, be it size, and those new orbitals are what you call as hybrid orbitals. Now the point is, how do you represent a hybrid orbital? A representation of hybrid orbital, my dear students. This is how you represent the hybrid orbital. One lobe is bigger in size and one lobe is smaller. This is how you represent the hybrid orbital. This is the hybrid orbital over here. Perfect. This is the hybrid orbital. Right, people? Now, at the same time, one more thing. Before going into the details of hybridization, let me tell you a few more important things about hybridization. Hybridization only takes place at the time of bond formation. At the time of bond formation. So whenever an atom has to form a bond, at that time only you'll considering hybridization. So hybridization, it takes place only at the time of bond formation. Hybridization does not take place in an isolated atom. For example, I've got carbon with me. Let's say carbon does not have to form any bond. So you are not going to discuss hybridization in this carbon, right? Perfect. Because hybridization is the concept which is used only at the time of bond formation. Okay? Perfect. So let me write this particular statement as well. Hybridization has no physical significance. Hybridization has no physical significance for isolated atoms. Now, my dear students, Once the intermixing of atomic orbitals is done, once the new orbitals are formed, once the hybrid orbitals are formed, what happens after that? What happens after that? After that, my dear students, let me tell you, these hybrid orbitals containing electrons, they arrange themselves in such a way that there are minimum repulsions between them. Once hybrid orbitals are generated, the hybrid orbitals, they arrange themselves in such a way that there are minimum repulsions between them, right? So I must say hybrid orbitals containing electrons arrange themselves in such a way that there are minimum repulsions between them. Because lesser the repulsions, maximum the stability. Lesser the repulsions, more the stability. So once the hybrid orbitals are generated, the hybrid orbitals containing electrons, they arrange themselves in such a way that there are minimum repulsions between them. Okay, perfect. Dear students, one more thing about hybridization, then we'll see exactly how it's calculated, what kind of shapes are generated, all those things we'll see. Okay, just one more point. Dear students, since I told you, the hybrid orbitals containing electrons, they arrange themselves in such a way that there should be minimum repulsions between them. Okay, now one more thing. If you ask me which all orbitals participate in the intermixing, which all atomic orbitals can participate in the intermixing, let me tell you, completely filled orbitals, half filled orbitals, as well as vacant orbitals. All these orbitals can participate in the intermixing. All these orbitals can participate in the intermixing. All these orbitals can participate in the intermixing. And once hybrid orbitals are generated, hybrid orbitals, they arrange themselves in such a way that there are minimum repulsions between them, right? Once that part is done, after that, these hybrid orbitals, they start overlapping. They start overlapping with the atoms of different, with the orbitals of different atoms, right? Once these hybrid orbitals are generated, right? These hybrid orbitals, they'll start overlapping with either the atomic orbitals of different atoms or hybrid orbitals of different atoms. So once hybrid orbitals are generated, these hybrid orbitals are going to overlap with either the atomic orbitals of different atoms or the hybrid orbitals of different atoms, right? And let me tell you, overlapping of hybrid orbitals, it always leads to the formation of sigma bond. Overlapping of hybrid orbitals, it always leads to the formation of sigma bond. Except benzene, wherein hybrid orbitals overlap and they lead to the formation of pi bond. This is the only exception here. Okay. Now, my dear students, all these things we are going to apply in the examples. I hope all these things are absolutely clear to everyone till here. Okay. Perfect. Now it's time for the examples, but before going into the examples, before applying the concept of hybridization in the examples, before talking about the geometry of the molecules, I would like to share some more things with you. And what are those things? Let's have a look. My dear students, there is one special method by means of which we can calculate hybridization. That's what you call a steric number method. Steric number method. This is the method by means of which we can check the hybridization of different atoms in a molecule. Okay, understand properly. Let me first of all tell you steric number. When you talk about steric number is equal to the number of sigma bonds which the central atom forms, the number of lone pairs which the central atom has. Sigma bonds which the central atom forms and the number of lone pairs which the central atom has. Okay. Now, dear students, based on steric number, we can talk about the hybridization. remember a few things. Do remember, if the steric number comes out to be 2, if the steric number comes out to be 2, the hybridization involved is going to be sp. The hybridization involved is going to be sp, right? And in case of sp hybridization, let me tell you, the geometry is supposed to be linear. The geometry is supposed to be linear. So I would say geometry in case of sp hybridization is supposed to be linear. Point number 1. Point number 2. If the steric number comes out to be 3, the hybridization involved is going to be sp2, and the geometry involved is going to be trigonal planar. It's going to be trigonal planar, right? Similarly, my dear students, if the steric number comes out to be 4, the hybridization involved is going to be sp3, and the geometry involved is going to be tetrahedral. The geometry involved is going to be tetrahedral, right? Perfect. Similarly, my dear students, if the steric number comes out to be 5, the hybridization is going to be sp3d, and the geometry involved is going to be trigonal bipyramidal. Trigonal bipyramidal. Similarly, if the steric number comes out to be 6, the hybridization involved is going to be sp3d2, and the geometry involved is going to be octahedral. It's going to be octahedral. And my dear students, if the steric number comes out to be 7, the hybridization is going to be sp3d3, and the geometry involved is going to be pentagonal bipyramidal. It's going to be pentagonal bipyramidal, right? These are few things which you have to remember first of all. Apart from that, there are some more things as well. When you talk about the tetrahedral geometry, when you talk about sp3 hybridization, which all orbitals participate in the hybridization? It is one of the s orbital and 3 p orbitals. So I would say s orbital plus px plus py plus pz. These are the orbitals which have participated in the intermixing, right? Similarly, in sp3d hybridization, which all orbitals have participated in the intermixing? It is s plus px plus py plus pz plus dz square, right? These are the atomic orbitals which have participated in the intermixing, right? And then only you can say sp3d hybridization has taken place. Perfect. In case of sp3d2, which all orbitals participate? S plus px plus py plus pz plus dz square plus dx square minus y square. These are the orbitals which have participated in sp3d2 intermixing, right? And similarly, in sp3d3, it's going to be s plus px plus py plus pz plus dxy plus dz square plus dx square minus y square. These are the orbitals which actually participate in sp3d3 intermixing. I hope all these things you guys are going to remember from now onwards. My dear students, apart from that, have a look. First of all, I told you, if the steric number is 2, the hybridization involved is going to be sp. The hybridization involved is going to be sp. Perfect. Let me tell you, in case of sp, the geometry is going to be linear. Geometry is going to be linear, and at the same time, bond angle will be 180 degree. After a few minutes, you'll get to know exactly how this bond angle comes out to be 180. Right? After a few minutes, just wait for it. Similarly, if the steric number is 3, hybridization is sp2. It is going to be trigonal planar. Let me tell you, the bond angle in this particular case, it's going to be 120 degree. Right? It's going to be 120 degree. In the similar way, if the steric number is 4, hybridization is sp3. It's going to be tetrahedral. And the bond angle in this particular case is going to be 109 degree 28 minutes. Perfect. Similarly, if the steric number is 5, hybridization sp3d. Geometry trigonal bipyramid. Perfect. Now over here, there are few types of bonds in case of sp3d. Let me tell you, my dear students, over here in case of trigonal bipyramidal geometry, we can have different bond angles. The bond angle between equatorial and equatorial bond. What are equatorial bonds? You'll get the idea in some time. First, take a note of everything, right? First, take a note of everything. The bond angle between two equatorial bonds in case of sp3d hybridization, it's going to be how much? It's going to be 120. It's going to be 120. At the same time, bond angle between axial and equatorial bond, it's going to be 90 degrees. How come exactly? You'll get the idea in some time. First, again, I'm telling you, take a note of all these. Okay? Between two equatorial bonds, it's going to be 120. Between axial bond and equatorial bond, it's going to be 90 degrees. Right? At the same time, if you ask me, what is the bond angle between axial and axial over here? Bond angle between axial and axial over here is going to be 180. Between two axial bonds, the bond angle is going to be 180. You'll visualize all these things in some time. Okay? Now, similarly, if the steric number is 6, hybridization is going to be sp3d2. Geometry is going to be octahedral. What all bond angles are involved here? Let me tell you, the bond angle between equatorial and equatorial, in this particular case, that's going to be 90. The bond angle between axial and equatorial, that's again going to be 90. The bond angle between axial and axial, that's going to be 180. These are the different types of bond angles over here in case of what? In case of octahedral geometry. Perfect. Now, dear students, there is one more and the last one, that is steric number 7. Steric number 7 means sp3d3, right? sp3d3. What kind of bond angles are observed over here? Let me first of all tell you, between two equatorial bonds, the angle will be 72 degrees. Between axial and equatorial, it's going to be 90 degrees. Between axial and axial, it's going to be 180. Now, my dear students, all these things which you have taken a note of, let's try to understand all these things in detail. Okay, let's try to understand all these things in detail. And dear students, one thing which I forgot to write over here. What is that? Since I told you, in case of hybridization, what happens? Intermixing of atomic orbitals takes place, due to which new orbitals are formed. And those new orbitals, they're identical in all the respects. Those new orbitals are what you call as hybrid orbitals. Let me tell you one more thing. Number of atomic orbitals which are participating in intermixing, is always equal to the number of hybrid orbitals formed. So, for example, if two atomic orbitals are participating in the intermixing, that means only two hybrid orbitals will be formed. If three atomic orbitals are participating in the intermixing, that means three hybrid orbitals will be formed. I hope all these things are clear. Now, let's try to understand all these things in the form of examples so that you can visualize all these things properly. Okay? The first example which I'm taking into consideration, guys, now you have to understand and focus. Till now, whatever I was telling you, that was something which you had to remember. Now, all the things which I've told you, I'm going to apply all those things in these perfect examples. Try to understand step by step what exactly I'll be doing. My dear students, the first step which I'll be doing over here, what is that going to be? Let's have a look. Just a second. First of all, locate your central atom. This beryllium is your central atom. If I ask you, how many valence electrons this beryllium has? This beryllium has got hydrogen, helium, lithium, beryllium. It has got 2 valence electrons, right? It has got 2 valence electrons. Now, my dear students, how many bonds this beryllium is forming? Or if I ask you, how many surrounding atoms are there with beryllium? There are 2 surrounding atoms. Do remember, the number of surrounding atoms is equal to the number of sigma bonds. Number of surrounding atoms is equal to the number of sigma bonds, right? Number of surrounding atoms is equal to the number of sigma bonds, right? Now, dear students, beryllium had 2 valence electrons. It had 2 valence electrons and it is forming 2 sigma bonds. That means whatever valence electrons beryllium had, all those valence electrons beryllium has exhausted while forming 2 bonds, right? In order to form 1 sigma bond, beryllium will be utilizing 1 electron, 1 more sigma bond, 1 more electron, 2 valence electrons it had, and it has, utilized both the valence electrons for bonding. So, will there be Any lone pair on beryllium? There will be no lone pair on beryllium. Lone pair is 0. Now, my dear students, you got to know the number of sigma bonds and lone pairs for beryllium. Can you calculate the steric number? What is steric number? Steric number is sigma plus lone pair. Sigma plus lone pair. So 2 plus 0 comes out be 2. If 2 plus 0 comes out be 2, what has to be the hybridization? Hybridization has to be sp. Right? If the hybridization has to be sp, what has to be the geometry as per hybridization? The geometry as per hybridization should be linear. The geometry as per hybridization should be linear. Now let's try to understand and analyze this a bit more in detail. Let's see exactly how the formation of BeCl2 takes place. My dear students, first of all, beryllium, write its outermost configuration. It is hydrogen, helium, lithium, beryllium. So it is 2s2, 2p0. This is the outermost configuration of beryllium. Perfect. Now, my dear students, have a look. Is this the ground state or excited state of beryllium? This is the ground state. This is the ground state configuration of beryllium. This is the ground state configuration of beryllium. So first of all, excite one electron over here. When you excite one electron, I'll say the new configuration becomes like this. This is the new configuration. Should I be calling this as ground state or excited state? This is the excited state configuration. This is the excited state configuration, right? Now, dear students, understand. Which type of hybridization this beryllium is showing? It's showing sp hybridization. That means, what does it mean exactly? It simply tells you one of the s orbital and one of the p orbital. One of the s orbital and one of the p orbital of beryllium has participated in the intermixing. Now, these two atomic orbitals, they are going to intermix, right? So, how many atomic orbitals are intermixing? 2. If 2 atomic orbitals are intermixing, it will lead to the formation of 2 hybrid orbitals, right? Number of atomic orbitals intermixed is equal to the number of hybrid orbitals formed. Since 2 atomic orbitals are intermixing, so I must say 2 hybrid orbitals would have got formed, right? So, my dear students, after the intermixing is done, I must say 2 hybrid orbitals have got formed over here. I will be calling this particular hybrid orbital as sp hybrid orbital. Even this is also called as sp hybrid orbital. Perfect. So 2 hybrid orbitals have got formed. Perfect. Right? Now, my dear students, one more thing. How this hybrid orbital got formed? When one of the s orbital and one of the p orbital, they intermixed basically. So can I say this particular hybrid orbital is formed when s orbital and p orbital intermixed? So can I say this hybrid orbital will be definitely having some s character as well as some p character? So the first thing which I'll ask you over here, what is the percentage of s character in case of sp hybrid orbital? How do you calculate it? So first of all, percentage of s character in sp hybrid orbital. Tell me how many s orbitals participated in the intermixing? 1 divided by. Tell me how many total orbitals participated? 2 multiplied by 100. The value comes out be 50. So I would say this particular sp hybrid orbital will be having 50% s character. If there is 50% s character, that means automatically percentage of p character will be also 50. Right? What is the percentage of d character here? D character is not involved at all. D character is not involved. So percentage of D character over here is 0. Yeah. Perfect. So my dear students, what happened till now? If I ask you what happened till now, what happened till now? I must say 2 atomic orbitals, they intermixed. They led to the formation of 2 hybrid orbitals. Now, my dear students, these hybrid orbitals, they are going to arrange themselves in such a way that there should be minimum repulsions between them. So how they are going to arrange themselves? So that there will be minimum repulsions. Let's say this is one of the hybrid orbital, right? And this is, for example, one more hybrid orbital. Perfect. So these hybrid orbitals containing 1 electron, they arrange themselves in such a way that there are minimum repulsions between them. Right? Right? Minimum repulsions means maximum stability. Perfect. Now, my dear students, what is going to happen after this? Since hybrid orbitals are formed, perfect. Now, these hybrid orbitals, they will overlap. They will overlap with what? See, beryllium is forming bonds with chlorine. right? Beryllium is forming bonds with chlorine. If I ask you what is the outermost configuration of chlorine, you'll say 3p5 is the outermost configuration of chlorine. 3p5. If you exactly write it, it's 1, 2, 3, 4, 5. So over here you have got 1p orbital, which is unpaired. So I would say one of the unpaired p orbital from chlorine, one of the unpaired p orbital from chlorine will come from this side. One of the unpaired p orbital, pure p orbital of chlorine will come from this side and will do the overlap. One more p orbital of one more chlorine will come from this side and will do the overlap. So what happened exactly? What happened exactly? Do you check it? What happened? Can I say axial overlapping, which leads to the formation of sigma bond. So I must say one of the sigma bond got formed here and one more sigma bond got formed here. And this particular sigma bond is formed when pure p orbital of chlorine overlapped with sp hybrid orbital of beryllium. So this sigma bond is formed when sp hybrid orbital of beryllium overlapped with the pure p orbital of chlorine. So this is spp overlapping. Similarly, this particular overlapping is again spp overlapping. spp overlapping. Now you tell me, is the overlapping same in both the cases? Overlapping is same. And if the overlapping is same, that means the extent of overlapping is same. If the extent of overlapping is same, I'll say strength of bond will be same. Strength of both these bonds will be same. And if the strength of both the bonds is same, what does that mean? That means both the bond lengths will be same. I hope this is absolutely damn clear to you. So this is your beryllium. This is one chlorine and this is one chlorine. And what is the bond angle over here? I must say 180 degrees the bond angle. I hope all these things are absolutely damn clear to you. Quickly in the chat with the thumbs up. Yeah? I hope you got the concept of what this hybridization exactly is all about. I'll take one more example so that it'll be absolutely damn clear to you. Let's have a look. Now I'll be a little quick, right? Since this was the first example, so I was teaching very slowly, step by step, right? Now we'll be a bit quick. Okay, let's solve this one slowly. After this, other examples will be solved quickly, okay? So guys, first thing, what is my central atom over here? It is boron, right? How many valence electrons boron has? Tell me how many valence electrons boron has. Hydrogen, helium, lithium, beryllium, boron. Atomic number 5. So 2, 3. So 3 valence electrons it has. 3 valence electrons. How many surrounding atoms? 3 surrounding atoms. And you know, the number of surrounding atoms is equal to number of sigma bonds. So 3 valence electrons, and it has utilized all these 3 valence electrons to form 3 sigma bonds. So how many lone pairs on boron? No lone pair on boron. Calculate the steric number. Steric number is nothing, it is sigma plus lone pair. 3 plus 0 comes out to be 3. So hybridization has to be sp2. So as per this particular hybridization, what should be the geometry? As per hybridization, it's supposed to be trigonal planar. It's supposed to be trigonal planar, right? Now let's try to analyze this. Now, dear students, if I talk about the central atom boron, hydrogen, helium, lithium, beryllium, boron. So the outermost configuration has to be 2s2, 2p1. 2s2, 2p1. Let me exactly write it. This is 2s2. And my dear students, this is 2p1. Perfect. This is the ground state configuration. Right? The excited state configuration. So one of the electron will shift here. When the electron shifts here, the excited configuration looks like this. This is the excited state configuration. What is the hybridization involved? It's sp2. So one of the s orbital and 2p orbitals, they have intermixed. They have participated in the hybridization. So I would say 3 atomic orbitals are intermixing. So number of atomic orbitals intermixed is equal to the number of hybrid orbitals formed. So this one hybrid orbital, this one more, and this is one more. What do I call each hybrid orbitals as? Each hybrid orbital will be called as sp2 hybrid orbital. Perfect. If I ask you, what is the percentage of s character in sp2 hybrid orbital? In one of the sp2 hybrid orbital, what is the percentage of s character? You'll say only one of the s orbital is participating, divided by total 3 are participating, multiplied by 100. 33% S character. So what is the percentage of P character then? 100 minus this, approximately 66%. Percentage of P character will be approximately 66%. I hope this is clear. Yeah, I hope this is clear. Now at the same time, how many hybrid orbitals got formed? I must say 3 hybrid orbitals got formed. Now these 3 hybrid orbitals, they are going to arrange themselves in such a way that there should be minimum repulsions and maximum stability. And how exactly you guys are going to arrange these 3 hybrid orbitals? Have a look. This is one of the hybrid orbital. This is one more hybrid orbital. And this is one more hybrid orbital, right? Each hybrid orbital containing one electron. Each hybrid orbital containing one electron, right? Now these hybrid orbitals, they are going to overlap. They are going to overlap with what? See, you have got 3 fluorine atoms. You have got 3 fluorine atoms. What is the outermost configuration of fluorine? It is 2p5. It is 2p5, right? 1, 2, 3, 4, and 5. This particular atomic orbital of fluorine is unpaired. So I must say one of the unpaired p orbital of one fluorine atom. One of the unpaired p orbital of one fluorine atom will come from this side and we'll do the overlap. Similarly, one more will come from this side, we'll do the overlap. Right? Similarly, one more will come from this side and we'll do the overlap. Perfect. If I ask you which type of overlap this is basically sp2p overlap. This is sp2 of boron and pure p of fluorine. Similarly, this is again sp2p overlap. Similarly, this is again sp2p overlap. Perfect. Is this axial overlap or parallel overlap? This axial overlap, right? This head-on overlap. And head-on overlap always leads to the formation of sigma bond. So this is one sigma bond which got formed, one more sigma bond, one more sigma bond. Perfect. Since overlapping is same everywhere. If the overlapping is same, that means extent of overlapping is same as well. And if the extent of overlapping is same, that means bond strength will be same. If the bond strengths are same, that means bond lengths will be same. As simple as that. Right? So how do you make it exactly? This is boron. This is boron. This is one of the fluorine from this side. One of the fluorine from this side. And one more fluorine from this side. This is your trigonal planar geometry. This is your trigonal planar geometry. Now, if I ask you, what is the bond angle over here? What is the bond angle over here? It's absolutely going to be 120 degree. Perfect, which I told you already. In case of sp2, the bond angle is going to be 120. Clear, people? Is this clear to everyone? Is this clear to everyone quickly? Quickly let me know. Is this absolutely clear? Say yes or no in the chats. Everyone in the chats, quickly. Everyone in the chats, quickly. I want everyone to say it. Yes or no. Yes or no. Perfect. Now let's take the example of CH4. Let's exactly see how it gets formed. Let's take the example of CH4. See guys, first thing, valence electrons of carbon, 4. How many sigma bonds? 4. 4 valence electrons, 4 sigma bonds. 0 lone pair. Steric number, 4 plus 0, 4. Hybridization, sp3. Geometry predicted through hybridization, tetrahedral. Correct? Tetrahedral. Now guys, look at carbon. Outermost configuration of carbon, 2s2, 2p2. How does it look like? 2s containing 2 and 2p containing 2 electrons as well. Is this ground state or excited state? This is ground state. Okay, let's exactly see the excited state of carbon. One of the electrons shifts. So I must say, this is the excited state of carbon. This is the excited state of carbon. Now, which hybridization is being involved? sp3. So one of the s orbital and 3p orbitals. So one of the s orbital and 3p orbitals. They have intermixed, and the number of atomic orbitals intermixing is equal to number of hybrid orbitals formed. So how many hybrid orbitals are formed there? 1, 2, 3, and 4, right? Each hybrid orbital I'll be calling as sp3 hybrid orbital. If I ask you, what is the percentage of s character in case of sp3 hybrid orbital? How many s orbitals are involved in the hybridization? 1. Total, how many orbitals are involved? 4. Multiplied by 100. The value comes out to be 25%. So 25% is the s character. Similarly, how much is the percentage of p character? It's going to be 75%. Well, after this, how many hybrid orbitals got formed? 4 hybrid orbitals. Now, my dear students, these 4 hybrid orbitals, they are going to arrange themselves in such a way that there should be minimum repulsions between them. So this is one of the hybrid orbital. One more hybrid orbital. One more hybrid orbital. And one more hybrid orbital. So these 4 hybrid orbitals containing one electron each, they have arranged themselves in such a way that there are minimum repulsions between them. Now, my dear students, what exactly is going to happen? Since carbon is forming bonds with hydrogen, right? And hydrogen configuration, that's 1s1. So I'll say one of the s orbital of hydrogen will come from this side and will do the overlap. One more from this side, overlapping done. One more from this side, overlapping done. One more from this side, overlapping done, right? So which type of overlapping this is? I'll say this is sp3s overlapping. This is sp3s overlapping. This is also sp3s, sp3s, sp3s. And hybrid orbitals, they always lead to the formation of sigma bonds. So all the 4 bonds are basically your sigma bonds. All the 4 bonds are basically your sigma bonds. Correct? All the 4 bonds are sigma bonds, which are formed by sp3s overlapping. So everywhere overlapping is same. If everywhere overlapping is same, what does that mean? Strength of bond, strength of all the 4 bonds will be same. And if the strength of all the bonds is same, what does that mean? All the bond lengths in case of CH4 is same. Now tell me whether hybridization explained the same bond lengths in CH4 or not. Say yes or no in the chats. Say yes or no in the chats. This particular geometry is what we call as tetrahedral geometry. Perfect. And this particular bond angle, right? It's going to be 109 degree, 28 minutes. Yeah. Is it clear, people? Quickly, quickly, quickly. It should be clear. Yeah. Perfect. Moving on. This was sp3. Moving on to sp3d. Moving on to sp3d. Have a look. Look at this particular scenario. Phosphorus is the central atom. How many valence electrons phosphorus has? Phosphorus belongs to nitrogen family, and nitrogen family has got 5 electrons in its valence shell. So it has got 5 valence electrons. How many surrounding atoms? 5. Number of surrounding atoms is equal to the number of sigma bonds, right? Perfect. Now people, 5 valence electrons, 5 sigma bonds. So there is no lone pair on phosphorus, right? Steric number, sigma plus lone pair, 5. Hybridization, sp3d. Geometry predicted through hybridization, trigonal bipyramidal. Trigonal bipyramidal, right? Now look at its formation, and there are few things which are important, right? Understand. If I talk about phosphorus, what is the outermost configuration of phosphorus? It is going to be 3s2, 3p3. Correct? Phosphorus belongs to nitrogen family. Nitrogen has got 2s2, 2p3. So phosphorus just comes below it. So it has to be 3s2, 3p3. Yeah? So this is 3s containing 2 electrons. And my dear students, this is 3p containing 3 electrons. If I ask you, will there be 3d as well? Absolutely, there will be 3d, but that will be containing 0 electrons. 3d is containing 0 electrons. So I'm not showing 3d over here. Or let me show 3d also. Right? 5 orbitals of 3d. Now, is it the ground state or excited state? This is the ground state. So make it into excited state. So one of the electron will be shifted here. So I must say this is 1 electron. This is 1, 1, 1, and one more electron has shifted into D. Right? One more electron has shifted into D. Now let me see if you remember or not. Which orbital this is? This is S, Px, Py, Pz. Which D orbital this is? In case of sp3d, I already told you, it is dz square, right? If this is S, this is Px, this is Py, this is Pz, then this has to be dz square, right? So my dear students, it is showing the hybridization of sp3d. So I must say s orbital, these 3p orbitals and this d orbital, they will intermix. Since 5 orbitals are intermixing, which will lead to the formation of 5 sigma bonds. Sorry, which will lead to the formation of 5 hybrid orbitals. So these are the 5 hybrid orbitals which we have. Now you can easily calculate. Okay, if I ask you what is the name of this hybrid orbital, the name of each hybrid orbital is going to be sp3d hybrid orbital. If I ask you what is the percentage of s character involved in sp3d orbital, how many s orbitals? One s orbital is participating, divided by total how many? 5 multiplied by 100. That is going to give you the percentage of s character. Percentage of p character. How many p orbitals? 3 divided by total 5 multiplied by 100. Percentage of d character. How many d orbitals? 1 divided by 5 multiplied by 100. I hope you're getting it. Now, dear students, there is something important now. Since we have got 5 hybrid orbitals, now these hybrid orbitals, they are going to arrange themselves in such a way that there are minimum repulsions and maximum stability between them. Now, how they are going to arrange? See, this is one of the hybrid orbital. One more hybrid orbital. One more hybrid orbital. So these 3 hybrid orbitals, they are present in the same plane. They are present in the same plane. These 3 hybrid orbitals, they are present in the same plane, right? They are present in the same plane. Now, my dear students, 2 hybrid orbitals are left. 2 hybrid orbitals are left. Perfect. One will be above the plane and one will be below the plane. One above the plane, one below the plane, right? So this particular one, this one and this one, they are present in the same plane. One is above the plane and one is below the plane, right? One above the plane, one below the plane. Perfect, right? Now, dear students, what is going to happen exactly? I'll say, now exactly, I'm not going to show the p orbital of chlorine coming. I'll directly tell you, one of the chlorine will come from this side, one from this side, one from this side, one from this side, one from this side. So how many bonds got formed? I'll say 5 bonds got formed. 5 bonds got formed, out of which 3 are in one plane, one above the plane, one below the plane. As simple as that, right? So which kind of overlap this will be? This is sp3d and pure p orbital of chlorine, right? The overlap here is sp3d. sp3d hybrid orbital of your phosphorus is overlapping with pure p orbital of chlorine everywhere, which leads to the formation of 5 sigma bonds, because hybrid orbitals, they always form the sigma bonds, right? Except benzene. Okay, how do I represent it? This is phosphorus. This is one of the chlorine. This is one chlorine here. This is one chlorine here. All these 3 atoms of chlorine, including phosphorus, they are present in one plane. They are present in one plane. Perfect. They are present in one plane. And my dear students, have a look. One chlorine is above the plane and one chlorine is exactly below the plane. Perfect. One chlorine is above the plane, one chlorine is exactly below the plane. I hope you can visualize it properly. I hope you are visualizing it properly. So 3 bonds in one plane, one above the plane, one below the plane. Perfect. Now, my dear students, if you join it like this, if you join the axial atoms with the equatorial atoms, what kind of shape did you get over here? This particular shape is what you call as trigonal bipyramidal shape. This is what you call as trigonal bipyramidal shape. And my dear students, look at these particular bonds. This particular bond, this particular bond, and this particular bond. These 3 bonds, they are present in the same plane. And I'll be calling these bonds as equatorial bonds. These are called as equatorial bonds, right? And the 2 bonds, one above the plane, one below the plane. These are what I call as axial bonds, right? So red colored lines are your equatorial bonds and yellow colored lines are your axial bonds. Perfect. There are a few things which I told you in the beginning. If I ask you, what is the angle between this axial and this equatorial? It is 90. This axial, this equatorial, 90, right? So this axial is making 390 degrees over here. 190, one more 90, one more 90 with this. Perfect. And similarly, if you talk about this particular chlorine, this axial bond, it's again forming 390 degrees over here. I hope you are visualizing. Since these 3 bonds, they are present in same plane, right? One bond is perpendicular to it. One bond is perpendicular to all the 3 bonds which are present in the equatorial plane. Yeah. So if I ask you, how many 90-degree angles are being formed here? If you ask me, how many 90-degree angles are formed here? Quickly let me know in the chats. I want to see whether you are able to visualize it properly or not. This particular axial bond, it is forming 390 bonds. One with this, and one with this. And similarly, this particular axial bond, it is also forming 390 degrees. One with this, and one with this. Perfect. So there are 690-degree angles which are being formed over. Yeah? There are 690-degree angles. Perfect. If I ask you, how many 120-degree angles are there? How many 120-degree angles are there? 120-degree angles are there between the equatorial ones. This equatorial, 120. This and this, 120. This and this, 120. So three 120-degree angles. Right? Perfect. If I ask you, what about this axial and this axial? This axial and this axial, it is 180. It is 180. Perfect. So three types of bonds are here. Exactly. पटेल साहब ये हिंदी चैनल नहीं है, चैनल का नाम पढ़ो, यहाँ पे लिखा है अनअकैडमी नीट इंग्लिश. कदे भी बहुत देखे मैंने, बट आप जैसा कोई. Okay? I'm supposed to teach in English. Quickly, let me know in the chats if all these things are clear. Quickly, people, in the chats. Done? Is this clear to everyone quickly? One more important thing. This particular axial bond length in case of trigonal bipyramidal geometry. Do remember one more thing. Axial bond length is greater than that of equatorial bond length. These are equatorial bond lengths, right? This is axial bond. Axial bond length will be greater than that of equatorial bond lengths. Why is that? Because this particular chlorine, it will be experiencing repulsions from the equatorial chlorine atoms. Similarly, this particular chlorine, it will be experiencing repulsions from the equatorial chlorine atoms. Due to which what will be happening? Due to which, I must say, the axial bond length will be greater than that of equatorial bond length. So take a note of that point as well. Okay? Axial bond length is greater than that of equatorial bond length. Equatorial bond length. In case of which geometry? In case of trigonal bipyramidal geometry. Hope this is also clear to everyone. Perfecto? Alright, so this was your PCl5 geometry, right? I mean, this was your sp3d geometry. Now let's have a look on sp3d2. Perfect? So we will have a look on this particular thing as well. My dear students, if I ask you, how many valence electrons sulfur has? Sulfur belongs to oxygen family, and oxygen family has got 6 valence electrons. So you have got 6 valence electrons. How many surrounding atoms? 6. The number of surrounding atoms is equal to the number of sigma bonds. So 6 sigma bonds. How many lone pairs on sulfur? 0 lone pair. Steric number 6 plus 0. That's 6. Hybridization sp3d2. Geometry has to be. The geometry has to be octahedral. Right? Now let's try to understand how this particular molecule gets formed. So first of all, if I talk about sulfur, sulfur comes in oxygen family. Oxygen has got the outermost configuration of 2s2, 2p4. So this will be having 3s2, 3p4. 3s2, 3p4. This will be 3d0. Perfect. This will be 3d0. Try to understand now. This is 3s containing 2 electrons. This is 3p containing 4 electrons. This is 3d containing 0 electrons. First of all, what is going to happen? One of the electron will get excited to here, and one of the electron will excite, for example, till here. So what is the excited state configuration? This is how your excited state configuration looks like over here. This is how your excited state configuration exactly looks like. Now, the hybridization is sp3d2. So s, d3 and d2. And you know exactly which d orbitals are participating here. dx square minus y square and dz square. Already, that's something which is mentioned. So, over here, how many atomic orbitals are intermixing? 6 atomic orbitals. So, how many hybrid orbitals I'll be getting? 1, 2, 3, 4, 5, and 6. So I've got 6 hybrid orbitals. Each hybrid orbital I'll be calling as sp3d2 hybrid orbital. Each hybrid orbital I'll be calling like this. sp3d2 hybrid orbital. Now, dear students, percentage of s character, I'm sure you can easily calculate now. Now, apart from that, all these 6 hybrid orbitals, they'll arrange themselves in such a way that there should be minimum repulsions between them. So this is one of the hybrid orbital, for example. One more hybrid orbital. One hybrid orbital. One more hybrid orbitals. So these 4 hybrid orbitals, they are present on the same plane. They are present on the same plane, right? Apart from that, there are 2 more hybrid orbitals left. One will be above the plane, and one will be below the plane. And each hybrid orbital is containing 1 electron each. Each hybrid orbital is containing 1 electron each. Perfect. Now, my dear students, there are 6 fluorine atoms. So I must say, one of the fluorine will come from this side. It is basically the p orbital of fluorine which is coming, or the overlapping, right? On every side, fluorine will come and do the overlap. So first of all, which type of overlap this is? This is again sp3d2 and p orbital. sp3d2 with pure p orbital of fluorine, right? This is the overlap happening everywhere. And you know, hybrid orbitals, they always lead to the formation of sigma bonds. So how many sigma bonds are being formed? 6 sigma bonds. So how do you represent it? This is, for example, sulfur. This is 1 fluorine, 1 more fluorine, 1 more fluorine, and 1 more fluorine. So first of all, let me tell you, these 4 fluorine atoms, including sulfur, they are present on the same plane. They are present on the same plane. So these bonds over here, this particular bond, this one, and this one, and this one, these are your equatorial bonds here. These are your equatorial bonds. There is 1 fluorine which is present above the plane, and there is 1 fluorine which is present below the plane. Right? And my dear students, if you join the axial atoms with the equatorial atoms, if you join the axial atoms with the equatorial atoms, what kind of geometry do you get? You get one octahedron type geometry. So this kind of geometry is what you call as octahedral geometry. Perfect. So this is your S sub 6. Yeah. Is this clear? Is this clear, people? Quickly in the chats. Okay, one question I'm going to give you. That is something which you will tell me in the comment section. How many total 90 degrees are being formed over here? How many total 90 degrees are being formed? And how many total 180 degrees are being formed? That is your homework question. If you were unable to solve that, I'll let you know in the next session. How many 90 degrees? What do you think? How many 90 degrees and how many 180 degrees are there? You are going to tell me that in the comment section of this particular video. Okay? Right? All right, this is something which you will be letting me know in the comment section. Okay, if you were unable to do it, then do mention in the comments. I'll pin it in the comment section of the video once the video ends. Okay. Now at the end, we have got IF7. So again, I'm not going to teach this in detail, this sp3d3 and how it exactly looks like. At the end, I'm going to show you that. This is I, one of the fluorine, one more fluorine on this side, one fluorine, and one more fluorine. So it's a pentagon over here, right? One fluorine above the plane, one fluorine below the plane, right? So this is IF7 and it clearly resembles with what? It resembles with pentagonal bipyramid. Pentagonal bipyramid, right? So this is pentagonal bipyramidal structure, right? And at the same time, something which I already mentioned, the angle between this and this will be 72 degrees. The angle between axial and equatorial that you already know, that will be 90 degrees. That's something which we already know. Right? Perfect. Perfect. Nothing else you have to know about this, I have said. Now, guys, there are a few examples. Right? There are a few examples. Let me see if you can solve them or not. Let me give you certain examples so that it'll be absolutely clear to you. For example, I'm writing over here as water, H2O. Tell me the hybridization and geometry of oxygen in the chats right now. Okay, H2O. For example, you have got NH3. You have got NH3. Okay. For example, you have got, let's say you have got, carbon dioxide. Carbon dioxide. For example, you have got I3 negative. For example, you have got SF4. Let's say you have got XeO2F2. Right? XeO2F2. These are some basic examples which at least you should know now. Say guys. First of all, oxygen is a central atom. How many valence electrons it has? 6. Surrounding atoms 2. Number of surrounding is equal to sigma. So 6 valence electrons, out of which 2 are used. So 4 valence electrons are left as such on oxygen in the form of 2 lone pairs. So sigma 2 lone pairs 2. Steric number is 4. Hybridization is sp3. Geometry predicted through hybridization, that is tetrahedral. Geometry predicted through hybridization, that's tetrahedral, right? Simple. Look at this NH3. Valence electrons of nitrogen, 5. Sigma bonds, 3. Lone pairs on nitrogen, 1. Because 5 valence electrons, 3 are being utilized. So 2 electrons will be left in the form of a lone pair. Steric number again, 3 plus 1, 4. Hybridization, sp3. Geometry predicted through hybridization, that's tetrahedral. Right? That's tetrahedral. Now look at carbon dioxide. This is carbon. How many valence electrons? 4. Perfect. How many sigma bonds? How many sigma bonds? 2 sigma bonds. Number of surrounding atoms. Now you know oxygen is divalent. It's forming 2 bonds. It's forming 2 bonds. So carbon over here will be forming 4 bonds. Right? 2 with each oxygen. 4 bonds. That means carbon is utilizing all these 4 electrons to form 4 bonds. So lone pairs are 0 with carbon. If lone pair is 0, steric number is sigma plus lone pair. 2. Hybridization is sp. The geometry predicted through hybridization, that is linear. Done. Look at I3 negative. If you talk about I3 negative, well, you must be confused in this. Can't I write I3 negative in this format? I2 negative? Same thing. Now iodine, how many valence electrons it has? 7. There is a negative charge. So 7 plus 1 makes it 8. Right? How many surrounding atoms? 2. So sigma bonds 2. Out of 8, 2 are being used. So 6 will be left as such in the form of how many lone pairs? 3 lone pairs. So there are 3 lone pairs. If I ask you about steric number will be 3 plus 2, 5. Hybridization, sp3d. Geometry predicted through hybridization, trigonal bipyramidal. Geometry predicted through hybridization. All these things you should know now. SF4. Over here you'll be getting 4 sigma bonds, 1 lone pair. Steric number will be 5. Hybridization again is sp3d. Geometry predicted through hybridization. You can easily know. Yeah. Same goes with XeO2F2. See, this example I'll show. Xenon. It has got 8 valence electrons. Surrounding atoms are 4. So sigma bonds are 4. Sigma bonds are 4. Right? Now, my dear students, one important thing. See, xenon is attached to 2 oxygen atoms and 2 fluorine atoms. Since oxygen is divalent. So xenon will be forming in total 4 bonds with oxygen. 1 double bond. Right? 4 bonds with oxygen and 2 bonds with fluorine. 2 bonds with fluorine. 1 with 1 fluorine, 1 with 1 more fluorine. So 4 plus 2 comes out to be 6. So xenon is utilizing 6 electrons. 6 of its valence electrons. It had 8 valence electrons, out of which 6 are being utilized. So 1 electron pair is left as such in the form of a lone pair. So again, steric number is 5. If the steric number is 5, hybridization has to be sp3d. Perfect. Is it clear? Is it clear, people? All right, few more things which you need to know. Well, my dear students, there is some basic thing which I'm sure every one of you would be knowing. How do you predict hybridization through structures? This is carbon, single bond carbon. And these are 3 hydrogen atoms on this side. And these are 3 hydrogen atoms from this side. This is something complete basics which every one of you, I'm sure, would be already knowing. Perfect. If I ask you what is the hybridization of this particular carbon, check it. Use the steric number method again. Carbon has got 4 valence electrons, right? So 1, 2, 3, 4. It is utilizing all the 4. So 0 lone pair. How many sigma bonds it's forming? 1, 2, 3, 4. So it's forming 4 sigma bonds. It's forming 4 sigma bonds. No lone pair. Steric number 4. Hybridization sp3. Right? Similarly, this carbon also will have hybridization sp3. Okay, tell me about this one. How many sigma it's forming? 1 is sigma, 2 sigma, 3 sigma. So 3 sigma it's forming. How many valence electron it's utilizing? 4. So all the 4 valence electrons are gone. Lone pair 0. Steric number 3 plus 0 comes out to be 3. Hybridization has to be sp2. Similarly, this will be also sp2. And at the same time, this will be sp and this will be also sp. This is something which all of you must be knowing easily, right? Similarly, when it comes to, for example, NH3, you know NH3 structure, right? This is the structure of your NH3. So 1 sigma, 2 sigma, 3 sigma. 3 sigma and 1 lone pair. Steric number 4. Hybridization directly sp3. So hybridization can be calculated with the help of structure as well. I hope it is clear to everyone. I hope it's clear to everyone. Now, dear students, one more example, one last example of hybridization, and then we'll be moving into VSEPR, valence shell electron pair repulsion theory. But before that, one last example, which is important. Let's exactly see how carbon dioxide gets formed. You already know the structure of carbon dioxide. I'm showing its formation through hybridization. Okay. Now, dear students, valence electrons with carbon are 4. Surrounding atoms are 2, therefore sigma bonds are 2. But carbon is attached to 2 divalent atoms, right? So carbon is forming 4 bonds. 4 bonds. So all the 4 valence electrons are utilized to form 4 bonds over here. So lone pair 0. Steric number 2 plus 0 is 2. Hybridization has to be sp. The geometry predicted through hybridization, that has to be linear. Point number 1. Point number 2. Look at the configuration of carbon. The ground state configuration is 2s2, 2p2. The ground state configuration is 2s2, 2p2. This is the ground state configuration of carbon. This is the ground state configuration of carbon. Now, what about the excited state of the carbon? So first of all, let me mention the ground state configuration of carbon. This is the ground state configuration of carbon. Let's write the excited state configuration of carbon. This is the excited state configuration of carbon, right? So this is the excited state. Perfect. Now, my dear students, which hybridization is involved over here? sp. If sp hybridization is involved, that means one of the s orbital and one of the p orbital, they have intermixed. Number of atomic orbitals intermixing is equal to number of hybrid orbitals formed. So 2 hybrid orbitals are being formed over here, right? 1 hybrid orbital, 1 more hybrid orbital. And apart from these 2 hybrid orbitals, there are 2 pure p orbitals as well. This is 1 pure p orbital. This is 1 more pure p orbital. So sp hybrid orbital, sp hybrid orbital, pure p orbital, right? Perfect. Now, guys, understand. These two hybrid orbitals, they'll arrange themselves in such a way that there are many more repulsions between them. So this is one of the hybrid orbital. This is one more hybrid orbital containing one electron. And apart from these 2 hybrid orbitals, we have got 2 pure p orbitals as well. So this is 1 pure p orbital of carbon containing 1 electron, right? And at the same time, this is 1 more p orbital of carbon containing 1 more electron. Perfect. So this is the carbon which I'm showing over. sp, pure p, pure p. Perfect. Now, when you talk about oxygen, since carbon is forming bonds with oxygen atoms, right? What about the configuration of oxygen? It is 2s2, 2p4. It is 2p4 basically, right? So how do you represent this 2p4? 1, 2, 3, and 4. Perfect. This one is completely filled. This one is half filled. This one is half filled, right? So I must say, let's call this as pz. Let's call this as py. Let's call this as px. Okay. And I'm considering this particular axis as z-axis. This axis I'm considering as the z-axis. So, my dear students, I will say simply one thing. I'll say one of the pz orbital, this pz orbital of oxygen will come from this side and will do the overlap. So this particular overlap with one oxygen atom. Similarly, one more oxygen atom will come from this side and its pz will also overlap like this. So these 2 overlaps, these are basically sp, and pure p. sp, pure p. So sp and pure p. And you know, these are the overlaps in which hybrid orbitals are involved. So they are supposed to be sigma 1. So this is sigma and this is sigma. Well, apart from this, as you can see, since I've utilized one of the p orbital of oxygen over here, similarly, there is one more oxygen atom whose p orbital I've utilized. So that means there will be two more orbitals over here as such, right? There will be two more orbitals over here as such. So let's assume that this is the py orbital of oxygen, right? This is py orbital of oxygen, and at the same time, let's assume that this is pz orbital of oxygen containing two electrons. My dear students, do you see this particular p orbital of carbon and this particular p orbital of oxygen? Are they parallel? Yes, they are parallel. So they can show the overlapping. So this is parallel overlapping, which leads to the formation of pi bond. And which pi bond gets formed over here? This is p, this is p. So it's p pi bond. So it's basically p pi bond which got formed on one side. Similarly, look at this particular oxygen. Look at another oxygen, I mean. Another oxygen has got the same configuration. One of the p orbital is already utilized. Now, one p orbital is half filled, one p orbital is completely filled, right? Let's assume this p orbital is half filled. Okay, this p orbital is half filled. And, for example, this p orbital is completely filled. Now, my dear students, can you just imagine one thing? This particular p orbital and this particular p orbital, they are parallel. So, again, they can do the parallel overlapping. And parallel overlapping leads to the formation of pi bond. So, again, over here, p pi bond got formed. So this is p pi bond again. Perfect. So how do I represent finally? This is carbon. First, it formed two sigma bonds with oxygen. Then it formed two pi bonds with oxygen. And which pi bonds are involved over here? These are p pi bonds which got formed over here. Let me know once in the chats quickly if all these things are clear to you. This is the structure of your carbon dioxide basically. I hope you exactly got to know how carbon dioxide formation exactly is explained through hybridization. Quickly in the charts. Quickly in the charts, everyone. Yes or no? Perfect. All right, so this was your concept of hybridization and its involvement in different molecules, right? And now, guys, we are going to move into one more important topic, that is valence shell electron pair repulsion theory. After this topic, I can give you the break. After this particular topic, right? First, this has to be complete. Valence shell electron pair, valence shell electron pair, repulsion theory. Valence shell electron pair repulsion theory. Right? Let's try to understand this now. Let's try to understand this particular theory now. My dear students, few points which you have to remember. Few important crux over. Then we'll see its application. Application is important actually, right? So important things, postulates you have to remember. Then you should be able to apply those postulates in the example. Then only you can say your concepts have got cleared. So valence shell electron pair repulsion theory. Dear students, this valence shell electron pair repulsion theory, it gives the idea about the actual shape of the molecule. It gives the idea about the actual shape of the molecule. How exactly? You'll get the idea in some time. Just wait for that. It gives the idea about the actual shape of the molecule. Point number one, which you'll remember right now. Point number two. For example, if I talk about NH3, this is the structure of NH3. If you talk about nitrogen, nitrogen has got 5 valence electrons. This is 1, 2, 3, 4, 5. Perfect. Right? My dear students, those electrons of nitrogen which have participated in the bonding, those electrons of nitrogen which have participated in the bonding, Those are called as bonding electrons. Those are called as bonding electrons. And those electrons which are from the valence shell, but are not participating in the bonding, those are called as non-bonding electrons. Those are called as non-bonding electrons. Okay. So basically, over here, nitrogen, it has got bonding electrons as well as non-bonding. Right? My dear students, do remember, a molecule tries to acquire that shape. Molecule tries to acquire that shape in which repulsions between valence shell electron pairs, are minimized. These bonding electrons as well as non-bonding electrons, these are called as valence shell electrons. Bonding plus non-bonding. Valence shell electrons, right? So basically, a molecule tries to acquire that shape in which the repulsions between these bonding and non-bonding electrons, they should be minimized. This is the only factor, only thing in which this VSEPR is completely based upon. A molecule is going to acquire that particular shape in which the repulsions between these valence shell electron pairs are minimized, right? And you know, lesser the repulsions, lesser the energy, more the stability. So molecule tries to acquire that shape in which the repulsions between these electron pairs are minimized. Therefore, energy is minimized and stability is maximum. Okay? Point number one. Point number two. Do remember this particular thing as well. Whenever in a molecule, the central atom does not have any lone pair. Whenever in a molecule, the central atom does not have any lone pair. Do remember, whenever you'll be having a molecule in which the central atom does not have any lone pair, remember, the geometry which is predicted through hybridization will be same as that of actual shape of the molecule. The geometry which is predicted through hybridization, that will be same as that of actual shape of the molecule. Point number one, important. Number two, if the central atom will be having lone pair, if the central atom has lone pair, then at that point of time, whatever geometry we will predict through hybridization, that won't be same as that of the actual shape of the molecule. These are the two most important things which you should know, my dear student. Right? Whenever the central atom in the molecule has zero lone pairs, that means whatever geometry you have predicted through hybridization, that will be the actual shape. And if there is a lone pair on the central atom, whatever geometry you have predicted through hybridization, that is not going to be the actual. Okay? Now we have to discuss basically the actual shapes of different molecules. That's amazing here. That's important at the same time from which question. Okay? So three things which I would want you guys to remember for now. There are other things as well, bond angles, etc., which I'll be dealing with separately, right? First thing, it gives me the idea about the actual shape. How exactly you'll get the idea in some time, right? If you talk about the central atom has got two types of electrons: bonding electrons, non-bonding electrons. Yeah, perfect. Bonding electrons are the ones which belong to the valence shell and participate in the bonding. Non-bonding, they do not participate. Now, between these bonding and non-bonding, there will be repulsions because eventually, finally, they are electrons only, right? Like charges repel, you know. Perfect. And you know, molecule always tries to acquire that shape in which the repulsions between these electron pairs, they are minimized. And if the repulsions are minimized, energy of the molecule is minimized, so stability is maximized, right? Because energy is inversely proportional to what? Stability. At the same time, do remember, lone pair repulsions are considered to be maximum, followed by lone pair bond pair, followed by bond pair repulsion. Lone pair repulsions are maximum, followed by lone pair bond pair, followed by bond pair. This is the order of repulsions as well, right? This is something which is very simple and I'm sure you already must be knowing about. Okay, this is the order of repulsions between valence shell electron pairs. Perfect. Now guys, we are going to apply all these things in the molecules basically. I'm going to give you the application part now. Let's try to understand what kind of questions can be asked from VSCPR and how do we do all these things. Yeah? See. First of all, let me talk about those molecules in which the central atom has got the steric number of 3. This is my case 1. I'm talking about those molecules wherein the central atom has got the steric number of 3. And you already know, if the central atom has got the steric number of 3, the hybridization involved is sp2, right? And the geometry which is predicted through hybridization, that has to be trigonal planar. Right? So this is our first case over here. Mention it as case number 1. I'm going to talk about those molecules which have got steric number 3. Right? Now, my dear students, there are 2 cases which can arise over here. The first case, steric number can be 3 if sigma bonds found by the central atom is 3 and lone pair of the central atom is 0. This can be one possible case wherein 3 plus 0 makes it 3, wherein steric number can be 3. What can be one more case? One more case over here can be like this. Sigma bonds are 2 and lone pairs of the central atom is equal to 1. Again, 2 plus 1 makes it 3. So these are the 2 cases which are included in steric number 3. Okay. Now, my dear students, one important thing. Any such molecule wherein the central atom will be forming 3 sigma bonds, there will be no lone pair on the central atom. How do you represent this particular molecule? This is how you represent it. Let's assume A is the central atom. How many sigma bonds it's forming? How many bond pairs it has? It has got 3 bond pairs. How many lone pairs A has? 0 lone pair. So this is how you represent this particular molecule. The molecule comes under the category of AB3L0. Okay. Now, already I have mentioned, if the central atom does not have any lone pair, whatever geometry you have predicted through hybridization, that's going to be the shape, right? So tell me, what is the geometry predicted through hybridization? That's trigonal bipyramidal. So I must say the geometry of this molecule is same as that of the shape of the molecule, and that is trigonal planar. And how do you make it? The type of the molecule is AB3L0. A is the central atom. This is one of the B. This is one more B. This is one more B, right? And there is no lone pair on A. Perfect. This is your trigonal planar geometry. Wherein already you know what is the bond angle? Bond angle is 120. Which is already discussed. Perfect. This is case number 1. Over here, the next case. Sigma bonds 2, lone pair 1. Steric number comes out to be 2 plus 1, 3. 2 plus 1, 3. sp2 hybridization. So what is the type of the molecule first of all? If A is the central atom, sigma bonds are 2. So it's going to be B2, 2 bond pairs, lone pair 1. The type of the molecule is AB2L1. It is AB2L1. Now, my dear students, since the steric number is 3, hybridization is sp2. So the geometry which is predicted through hybridization, will be equal to trigonal planar. But what about shape? Right now, shape will be different. The actual shape of the molecule will be different because the central atom has got the lone pair. So shape won't be equal to geometry. So how you will make its shape? First of all, make it a geometry. The geometry is trigonal planar. So it was supposed to be like this. This is trigonal planar, right? This is trigonal planar. It was supposed to be like this. But over here, there are 3 sigma bonds. But right now, I just need 2 sigma bonds and 1 lone pair. So just remove one of the sigma bond. Instead of that, put a lone pair. Perfect. Now, if you want to comment on the actual shape, just hide this lone pair. How does it look like now? Hide this lone pair. How does it look like now? It looks like bent. So the shape of the molecule is bent over here. It is bent shaped. It is V-shaped. I hope this is clear. So this was category number 1, in which the steric number is going to be 3, right? Steric number is 3 can be due to these two possibilities. Yeah? Perfecto? All right. Moving on to steric number 4. Now, I'm going to talk about those molecules wherein the central atom has got the steric number of 4. First of all, steric number 4, what does that mean? That means the geometry which is predicted through hybridization, that has to be tetrahedral. The geometry which is predicted through hybridization, that has to be tetrahedral. Correct? And in case of tetrahedral things, the bond angle has to be 109. You know it already. Now let's try to break it. When can be steric number 4? The first possibilities, if the central atom is forming 4 sigma bonds and it has 0 lone pair. This is the first possibility. The second possibility is if there are 3 sigma bonds, lone pair is 1, right? Third possibility, if there are 2 sigma bonds and 2 lone pairs. These are the 3 possibilities which arise in steric number 4 category, right? 4 plus 0, 4, 3 plus 1, 4, 2 plus 2, 4. Correct? What should be the type of the first molecule? You just tell me that. Type of the first molecule will be AB4L0. This is the type of the molecule. What is the type of this molecule? It has to be AB3L1, right? What is the type of the next molecule? It has to be AB2L2. It has to be AB2L2, correct? Now, my dear students, understand properly what I'm going to say. AB4L0. Look at this particular molecule. Steric number is 4 plus 0 is 4. Hybridization is sp3. Right? Hybridization is sp3. The geometry which is predicted through hybridization, I'll say the geometry which is predicted through hybridization is same as that of shape, and both are tetrahedral. Why is that? Because the central atom does not have any lone pair. And you know, when the central atom does not have any lone pair, whatever geometry is predicted through hybridization, that is same of your shape. I mean, the shape is same. Yeah? So how does it look like now? AB4L0, you know it already. This is A, this is B, this is B, one more B, one more B. This is your tetrahedral geometry shape, whatever you want to say. And the bond angle in this case is 109 degree, 28 minutes. I hope this is clear. So all the molecules of the type AB4L0, they are going to be tetrahedral in shape as well as geometry. Yeah. Look at the next one, AB3L1. There is one lone pair. So shape won't be same as geometry. What about the geometry first of all? Since steric number is 3 plus 1, 4. Hybridization sp3. Geometry, you know already. That's tetrahedral. That is tetrahedral. But what about the shape? Well, in order to make its actual shape, we'll be making its geometry. Make it its geometry. Geometry is tetrahedral, like this. Geometry is tetrahedral. Tetrahedral is something like this, right? Tetrahedral is something like this. But over here, there are 4 sigma bonds. But how many do I need? 3. Just remove one of the sigma bond. And instead of that, put a lone pair. Remove one of the sigma bond. And instead of that, put a lone pair. Let's assume I'm removing this particular sigma bond. And instead of that, I'm putting a lone pair over here. Now, if you want to comment on the actual shape, do one thing. Hide this lone pair. Hide this lone pair. Now see how this exactly looks like. How it exactly looks like. It looks like a pyramid, right? So the shape over here is pyramidal. The shape over here is pyramidal. As in case of NH3. If you remember NH3, right? NH3, 3 sigma bonds, 1 lone pair. That means NH3 is of the type AB3L1. Its geometry of NH3 will be tetrahedral, but its shape will be pyramidal. And you know, the bond angle in case of NH3, that is 107 degree. Right? Perfecto. Look at the next one. 2 sigma, 2 lone pairs. Type of the molecule already you know. Steric number is 4. If steric number is 4, hybridization is going to be sp3. The geometry predicted through hybridization, that is tetrahedral, you already know. But will the shape be also tetrahedral? No. Because central atom has got 2 lone pairs. Right? So what will be the shape? In order to make the shape, make the geometry first of all. The geometry is tetrahedral. This is B. This is B. This is B. This is B. This is the geometry tetrahedral. Now, how many sigma bonds? 4. But do I need 4 or 2? I need only 2 sigma bonds. So do one thing. remove two of the sigma bonds. Remove two of the sigma bonds. And instead of that, put two lone pairs. Put two lone pairs over here. Now, if you want to comment on its actual shape, do one thing. Hide these lone pairs and have a look on the molecule. Is it looking like V-shaped, inverted V? Yeah, bent. Right? Its actual shape is bent. It's inverted V type. Perfect. Clear? So this was the steric number 4 category. Now comes your steric number 5 category. Steric number 5 category, wherein hybridization is going to be sp3d. Geometry is going to be trigonal bipyramidal. Geometry is going to be trigonal bipyramidal. Geometry is going to be trigonal bipyramidal. Now guys, let's exactly see what all cases arise in this particular geometry, that is sp3d. Case number 1. When can be steric number 5? First possibility, if sigma bonds are 5, lone pair on the central atom is 0. This is the first possibility. Second possibility, if the sigma bonds are 4, lone pair on the central atom is 1. Third possibility, if sigma bonds are 3, lone pairs are 2. Fourth possibility, if sigma bonds are 2 and lone pairs are 3. These are the possibilities wherein the steric number followed by the central atom will be 5. Right? Now, dear students, in the first case, sigma are 5, lone pairs are 0. So first tell me the type of the molecule. Isn't it going to be AB5L0? Absolutely, it's going to be AB5L0. A is the central atom, 5 bond pairs, 0 lone pair on the central atom. Now, the central atom does not have any lone pair. That means whatever geometry is predicted through hybridization, and geometry predicted through hybridization, you already know, right? Whatever geometry is predicted through hybridization, that's going to be the shape of the molecule. And it's going to be trigonal bipyramidal. Clear? How do we show it? It's AB5L0. This is A. This is B. One more B. One more B. Right? These are present at the equatorial positions. Already we have discussed this. Right? And this is one more B at the actual position. One more B at the actual position. So this is your trigonal bipyramidal geometry and shape of the molecule of the type AB5L0. Yeah? Right? Sanjay, always sigma bond is formed first, followed by pi bond. Now, you're saying, can sigma bonds be 0? There is one example wherein sigma bonds are 0. That is C2 molecule, which I'll teach you in molecular orbital theory. In molecular orbital theory, between two carbon atoms, 2 bonds are formed. Bond order is 2. Okay? And both the bonds are pi bonds. There is no sigma bond in that. That's something which I'll tell you. Okay? All right, look at one more example now. 4 sigma bonds, 1 lone pair. Type of the molecule will be AB4L1. AB4L1, right? Now, my dear students, if the type of the molecule is AB4L1, central atom has got the lone pair. Geometry will be the same, which is predicted through hybridization. What is that? Trigonal bipyramidal. But what about the shape? Shape right now will be different now. Shape will be different. Shape will be different, right? And in order to make the shape, I'll make the geometry first. A, this is B, this is B, this is B. This is one more B, and this one more B. This is the trigonal bipyramidal geometry. But over here, how many bonds are found? 5. How many do I need? 4. So remove one of the bond pair. Remove one of the bond pair. Remove one of the bond pair. And instead of this bond pair, put a lone pair. Right? Now, if you want to commit on its actual shape, do one thing. Do one thing. Just hide this lone pair. Now, look at this particular molecule. Look at this particular molecule. Is it looking like a seesaw shape? Isn't this shape, just remove this lone pair aside, leave this lone pair aside. Is it looking like a seesaw shape? Right? So all the AB4L1 molecules are seesaw shaped. So shape of the molecule is seesaw. So this is seesaw shape. I hope this is clear. Sigma bonds 3, lone pairs 2. The type of the molecule, AB3L2. AB3L2. Geometry, predicted through hybridization is going to be trigonal bipyramidal. What about shape? In order to make it the shape, what do we need? We need to make the geometry first. So I'll be making geometry first to make the shape. The geometry is trigonal bipyramidal. Okay, this is trigonal bipyramidal. Now, how many sigma bonds we have? 5. But how many do we need? 3. So we have to remove 2. We have to remove 2. Right? Now, my dear students, what do you think will be the actual shape? What do you think will be the actual shape? Remove 2 of the bond pairs. Remove 2 of the bond pairs. One from here and one from here. And instead of that, put 2 lone pairs. This one lone pair. This is one more lone pair. Perfect. Now, if you want to comment on the actual shape, hide these lone pairs. Now look at the molecule. It looks like a T-shaped. So shape of this particular molecule is T. Is T-shaped molecule. So all the molecules of the type AB3L2, they'll be T-shaped. They will be T-shaped. Right? Similarly, sigma 2 lone pair 3. So the type of the molecule is AB2L3. The type of the molecule is AB2L3. The geometry is predicted through hybridization. That is trigonal bipyramidal. What about the actual shape? In order to make the actual shape, make it geometry. Geometry is AB5 type. So this is AB5 geometry. This is AB5 geometry. Perfect. This is AB5 geometry. Now, how many sigma bonds are there? 5. How many do we need? Only 2. So remove 3 sigma bonds here. Remove 3 sigma bonds over here. Okay. Remove 3 sigma bonds. One here, and one here. I've removed 3 sigma bonds. And instead of these sigma bonds, I've placed 3 lone pairs. Now, what is the shape of this particular molecule? So hide these 3 lone pairs. Look at it now. It is linear. When you hide the molecules, when you hide the lone pairs, the shape of the molecule looks linear. This is the actual shape of the molecule. So this is the case wherein the steric number is 5. Yeah? Perfect. Now similarly, you have got steric number 6. This is one more category, steric number 6. Steric number 6 means hybridization is sp3d2. The geometry which is predicted through hybridization, that is octahedral. Geometry predicted through hybridization is octahedral. Okay, now understand. What all cases arise over here? First possibility is there can be 6 sigma bonds and 0 lone pair on the central atom. This is one possibility, right? 5 sigma bonds, 1 lone pair on the central atom. Steric number again 6. 4 sigma bonds, 2 lone pairs on the central atom. Again 6, right? Again 6. Now let's exactly see the shape of different molecules. So first of all, the first type of the molecule is going to be AB6L0. The type of the molecule over here is going to be AB5L1. The type of the molecule over here is going to be AB4L2. Perfect. Geometry of all these molecules which is predicted through hybridization, that is same octahedral, right? So first of all, the geometry of this particular molecule which is predicted through hybridization is same as that of shape, right? Both the things are same because the central atom does not have any lone pair. So geometry, shape, same. What is it? It's going to be octahedral. It's going to be octahedral. Perfect. And how does it look like? This is A. This is B. This is one more B. One more B. One more B. All these 5 atoms over here, they are present in one plane. They are present in one plane, and perpendicular to it, there is one. Perpendicular to it, there is one more. And it looks like basically octahedral, wherein 4 bonds are present in equatorial plane and 2 bonds are present in axial plane. Okay. Number 1. Number 2. AB5L1. So first of all, the geometry of this particular type, which is predicted through hybridization, that is octahedral. Now what about shape? In order to make the shape, make its geometry first of all. Make it geometry first of all. This is 1B. This is 1B. This is the geometry which is predicted through hybridization. But over here, if you have a look, there are 6 bonds. But how many do I need? 5. So remove 1. Let's remove this one. And instead of it, put a lone pair. When you want to talk about its actual shape, just hide this lone pair. When you hide this lone pair, how does it look like? It looks like a square and the pyramid at the top. So the shape of this particular molecule will be square pyramidal. It will be square pyramidal. It will be square pyramidal, right? Yeah. Now guys, 4-2. 4-2. AB4L2. Geometry predicted through hybridization is octahedral. What about the shape? First of all, it's AB4L2. So first thing, in order to talk about its actual shape, exact shape, what I'll be doing? I'll be making its geometry. This is octahedral geometry. This is how your octahedral geometry looks like. 6 sigma bonds. But how many do I need to show? I need to show 4 only, right? So remove 2. Remove 2. One from here, for example, one from here. Perfect. And instead of them, put 2 lone pairs. Put 2 lone pairs. Now you tell me, what is the shape of this molecule? Just hide the 2 lone pairs. What is the shape exactly? It's square planar shape. The shape is square planar. I hope all these things are clear to you, right? Now there is only one case, that is sp3d3, right? Let me show that here only. sp3d3, steric number 5. Geometry is pentagonal bipyramidal predicted through hybridization. Now there can be 2 possibilities. Bond pair 7, lone pair 0. Type of the molecule AB7L0. AB7L0, right? Shape and geometry both are same. Pentagonal bipyramidal. Pentagonal bipyramidal, you already know it. But there is one more possibility. If bond pairs are 6, lone pairs are 1. Bond pair 6, lone pairs 1. Right? Geometry no doubt will be pentagonal bipyramidal. Shape will be different. And what about the shape? What about the shape? This is the shape, how it looks like. Distorted octahedral. Distorted octahedral. Look at this particular bond, this one, and this one. Right? They are present in one plane. They are present in one plane. This is above the plane. This is below the plane. Right? And there is a lone pair here. The lone pair, where is it? See, this is the equatorial plane wherein you have got xenon, including xenon, you have got 4 bonds, right? This is axial bond, this axial bond. Over here will be somewhere lone pair. Over here. The lone pair is not present on the equatorial plane. It is present somewhere here. I hope you're able to visualize it. Let me again tell you. This is xenon, right? Fluorine, this fluorine, this fluorine, this fluorine. They are present in the same plane. One is above the plane, one is below the plane. And right here somewhere, there will be a lone pair. Right? So this lone pair is not present in the equatorial plane. Right? And this particular shape is something which you call as distorted octahedral. It is what you call as distorted octahedral. So let me exactly see what were concepts I told you till now. Let me see if you can utilize these concepts in the questions or not. Tell me everything about these molecules. Everything means everything. Can you do that? We can do it. First of all, hybridization or steric number. Steric number is 2. The type of the molecule. Type of the molecule, when you check it, AB2L2. Right? Geometry predicted through hybridization. That is tetrahedral because steric number is 4. Sorry. Tetrahedral. It is linear. It is linear. Why am I telling you AB2L2? This AB2L0, right? This is AB2L0. Geometry is linear. If I ask you what about the shape? Since the central atom does not have any lone pair, so its shape has to be same. It's linear. Perfect. Or let me give you one example in detail. Let's take one example in detail. XCF4. Look at the valence electrons of xenon. 8. Look at the valence electrons of xenon. 8. How many surrounding atoms? 4. That means sigma bonds 4. Out of 8 valence electrons, 4 are utilized. So 4 are left as such in the form of 2 lone pairs. So 2 lone pairs. If I ask you the steric number, 4 plus 2 is 6. If I ask you the type of the molecule, it's going to be AB4L2. If I ask you about the geometry predicted through hybridization, that's octahedral. If I ask you about the shape, AB4L2 is square planar in shape. Is square planar in shape, right? This is the shape, this is the geometry. Yeah? Perfect. Nowadays, students talk about I3 negative. Talk about I3 negative. This is one common example which is asked in many examinations. I3 negative. How do you write this I3 negative? It is I2 negative basically. This is how you mention it. Now, dear students, this iodine is a central atom. So how many valence electrons it has? 7. There is a negative charge, so 7 plus 1 makes it 8. How many surrounding atoms? 2. Number of surrounding atoms is equal to number of sigma bonds. So 2 sigma bonds. So out of 8, 2 are used. So 6 will be left as such in the form of 3 lone pairs. So there are 3 lone pairs. Steric number 3 plus 2, 5. The type of the molecule is going to be Ab2L3. Is going to be Ab2L3. Geometry predicted through hybridization, that is trigonal bipyramid, right? What about the shape? What about the shape? Ab2L3 type. 3 lone pairs, 2 sigma bonds. If you remember a few minutes back only I have shown you, it's going to be linear. Yeah? Perfect? Absolutely done. Right, people? Now, there are 2 topics which are left. I would want everyone to let me know once in the chats quickly. Yeah? Quickly, let me know in the chats. Everyone. Now is the time for the most important topic of the chapter. That is molecular orbital theory, right? I hope all the concepts which I have given you till now from the chapter chemical bonding, I hope all the concepts are absolutely damn clear to you. Yeah? Perfect, guys. So let's get going. Let's get started with something which is an amazing theory. That is the molecular orbital theory. Majority of the times whenever a question is asked from the chapter chemical bonding, this is the topic which is given the priority. Molecular orbital theory, from which questions are asked regarding the bond orders, bond lengths, bond strengths, bond dissociation energy, right? Stability, etc., etc. A lot of things can be asked. Okay? So exactly from the basics, I'll be starting this particular theory as well. So my dear students, understand one by one what exactly I'm going to talk about. Dear students, the first and the most important point of this MOT, what is that? Let me tell you, this molecular orbital theory, it is the extension basically. It is the extension of VBT. It is the extension of valence bond theory. Point number 1. It is the extension of VBT. Point number 2. As per this molecular orbital theory is concerned, the atomic orbitals of the bonding atoms, right? The atomic orbitals of the bonding atoms, they are going to combine. As per this particular theory is concerned, the atomic orbitals of the bonding atoms, they are going to combine and they will lead to the formation of molecular orbital. So atomic orbitals of the bonding atoms, they combine to form what? To form molecular orbital. This is one more important point. My dear students, first of all, I'm going to write the same statement. As I told you, atomic orbitals of the bonding atoms. Atomic orbitals of the bonding atoms. They combine to form what? To form the molecular orbitals. To form the molecular orbital. At the same time, let me tell you, number of atomic orbitals combined is always equal to the number of molecular orbitals formed. Number of atomic orbitals combined is always equal to the number of molecular orbitals formed. For example, one of the atomic orbital of one atom and another atomic orbital of one more atom, right? Let's say they are combined. So 2 atomic orbitals are combining over. They will lead to the formation of 2 molecular orbitals. One is going to be the bonding molecular orbital. One is going to be the anti-bonding molecular orbital. One is going to be the bonding molecular orbital. One is going to be the anti-bonding molecular orbital. Right? Let me tell you, energy of the bonding molecular orbital is comparatively less than that of the energy of the anti-bonding molecule. Energy of the bonding molecular orbital, that will be comparatively less than that of energy of anti-bond. And you know, stability, that is inversely proportional to energy, right? if the energy of bonding molecular orbital is less, that means the stability of bonding molecular orbital comparatively is going to be more than that of the stability of anti-bonding molecular. This is the first and the most important point which I would want you guys to remember. I'll let you know after some time how these molecular orbitals exactly are formed. That's something which we have to discuss in detail. First of all, I'm giving you the important crux of this theory. Number one, it is the extension of valence bond theory. Number two, as per this theory, atomic orbitals of bonding atoms, they combine and they lead to the formation of molecular orbitals, right? Number of atomic orbitals combined is always equal to the number of molecular orbitals formed. Let's assume two atomic orbitals are combined, so they will lead to the formation of two molecular orbitals, out of which one will be called as bonding molecular orbital, one more will be called as anti-bonding molecular orbital. Energy of bonding molecular orbital is less as compared to energy of anti-bond. And lesser the energy, more the stability. So stability of bonding molecular orbital will be definitely greater than that of stability of anti-bonding molecular orbital, right? Let me give you one example. One simple example I'm going to give you. Okay? For example, let's say this is the s orbital of one atom. Let's say this is the s orbital of one atom. Perfect. Let's say this is 1s. Similarly, we have got one more 1s orbital of another atom. So these two atoms I'm taking into consideration. This is one of the atomic orbital of one atom. This is one more atomic orbital of one more atom. Perfect. Now, my dear students, as per molecular orbital theories concerned, these atomic orbitals, they will combine. They will lead to the formation of molecular orbitals, out of which one will be bonding molecular orbital, one will be anti-bonding molecular orbital. Perfect. Now, my dear students, imagine and remember, in VBT, have we discussed that when s orbital of one atom and s orbital of another atom, how do they overlap? Do they overlap actually or parallelly? Two s orbitals, they do head-on overlap. They do axial overlap, due to which bond gets formed? Sigma bond gets formed. So this is your s, this is your s. Perfect. So these two s orbitals are combining. They lead to the formation of two molecular orbitals. One will be bonding, one will be anti-bonding. The bonding over here, it will be represented by sigma 1s. And anti-bonding over here, it will be represented by sigma star 1s. Okay? And if I ask you, which molecular orbital is more stable among the two? You will say sigma 1s is comparatively more stable than that of sigma star 1. Reason being? Reason, the energy of this sigma 1s will be less than that of energy of sigma star. Now you must be thinking, why is it so? Why energy of sigma 1s is less than that of sigma star 1s, right? All these things we'll be discussing now in detail. Okay, first tell me whether whatever points I've discussed till now, all these points are clear or not. Yes or no in the chats, everyone. Then only I'll show you exactly what happens, how these molecular orbitals are formed. Quickly in the chats, yes or no? Yes or no? Quickly in the chats, every one of you. Right? Okay. Before talking about how these molecular orbitals exactly are formed, let me tell you one more thing. Since as I told you, atomic orbitals of the bonding atoms, they combine to form molecular orbitals. Once molecular orbitals are formed, which can be of this type, sigma 1s, sigma star 1s, right? Similarly, there are a lot of molecular orbitals, which we are going to discuss afterwards. My dear students, once atomic orbitals combine and lead to the formation of molecular orbitals, right? Those molecular orbitals which are formed when atomic orbitals combine with each other. My dear students, in those molecular orbitals, what we'll exactly do? We will fill the electrons. We will fill the electrons in those molecular orbitals which get generated basically. We will fill molecular orbitals with the electrons. And we will fill the molecular orbitals with the electrons as per Abbas principle. As per Abbas principle, as per Hund's rule, as per Pauli's exclusion principle, right? So once atomic orbitals combine, they will lead to the formation of molecular orbitals. Once molecular orbitals are generated, then we'll start filling electrons in those molecular orbitals as per these three rules. As per these three rules. And my dear students, once you are done with the filling of molecular orbitals with the electrons, then automatically we can calculate the bond order of a particular species. What is bond order? Number of bonds between two atoms. How do we do it as far as MOT is concerned? It is equal to half number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. NB stands for number of electrons in bonding. Na stands for number of electrons in anti-bonding. Perfect? Right? We have to talk about this particular relation in detail, but after. Okay? One more thing. Let me tell you, if the bond order of a molecule, if it comes out to be less or equal to 0, what does that mean? That means the molecule does not exist. That means the molecule does not exist. Bond order gives us the idea about the number of bonds between two atoms, basically. So if the bond order is less or equal to 0, that means molecule does not exist at all. My dear students, if the bond order comes out to be 1, that means there is a single bond between two atoms. There is a single bond between two atoms. Similarly, if the bond order comes out to be 2, that means there is a double bond between two atoms. And in the similar way, if the bond order comes out to be 3, that means there is a triple bond between two atoms. There is a triple bond between two atoms, right? And you must be knowing, more the bonds between two atoms, stronger is the attraction. Stronger is the attraction. Stronger the attraction, that means more is the stability, right? More is the bond dissociation energy. More bond dissociation energy, more stability, more attraction. That means the atoms will be close. Lesser will be the bond length. So do remember one important result. Bond order, it is directly proportional to bond strength. Because more the bonds, more the bond strength. Bond strength, it is directly proportional to bond dissociation energy, which is inversely proportional to bond length. Any question can be asked out of this particular relation. Sometimes a question is asked on bond order, sometimes on bond dissociation energy, sometimes on bond length, right? You would have seen all those. And we'll see its application in detail in some time. Apart from that, do remember a few more things. Since I told you atomic orbitals, they are going to combine. They lead to the formation of molecular orbitals. And then these molecular orbitals are to be filled with electrons, right? Do remember, more the electrons present in anti-bonding molecular orbitals. More the electrons present in anti-bonding molecular orbitals, lesser is going to be the stability of the molecule. Lesser is going to be the stability of the molecule. And similarly, lesser the electrons, or let me write it like this. More the electrons present in bonding molecular orbital, more is going to be the stability. More is going to be the stability. And this particular rule, when we are going to follow it, we'll follow it in those species which have got same bond order. There will be some species which will be having same bond order, right? How do we compare the stability of those species which have got same bond order? This is the rule which we'll be following. So those species which will be having same bond order, how we will compare their stability. My dear students, this is something which you need to remember. More the electrons in anti-bonding, lesser the stability. More the electrons in bonding, more the stability. I hope this point is also clear. Now the point is how these molecular orbitals exactly are formed, right? So first of all, let's see exactly the formation of molecular orbitals. Let's see exactly the formation of molecular orbitals, and then my dear students, we'll see how this bond order, etc. is calculated. Okay, just give me a second. So you mark the heading as formation of molecular orbitals. Formation of molecular orbitals. How these molecular orbitals are formed. My dear students, formation of molecular orbitals is explained by LCAO. Formation of molecular orbitals is explained by LCAO. And what this LCAO is all about? It is the linear combination. It is the linear combination of atomic orbitals. It is the linear combination of atomic orbitals. So basically, let me tell you the formation. Let me tell you the formation of atomic orbitals. It is explained. The formation of atomic orbitals is explained by LCAO, that is linear combination of atomic orbitals. Now, what is that linear combination of atomic orbitals? Let's try to understand that. My dear students, have proper eye on what exactly I'm going to talk about now. This is something which is very important, which you cannot understand normally from the books also. Okay. See guys. For example, imagine that this is the atomic orbital of one atom and this is the atomic orbital of one more atom. As per MOT, these atomic orbitals, they'll combine. They will lead to the formation of molecular orbitals. One will be bonding, one will be anti-bonding. My dear students, this linear combination of atomic orbitals, it predominantly considers the atomic orbital to be a wave. So as per LCAO is concerned, what is the atomic orbital? It is a wave. And for example, this is the wave which is corresponding to this particular atomic orbital. Similarly, there will be one more wave which will be corresponding to this particular atomic orbital as well. Right? So I have shown two waves over here. Right? This particular wave corresponds to this particular atomic orbital. This particular wave corresponds to this particular atomic orbital. Now, my dear students, since I'm telling you atomic orbitals are going to combine, that means the waves corresponding to these atomic orbitals, they are going to combine. And do you know when waves combine, what do? They show interference, my dear student. So over here, two possibilities arise. I hope you would have studied in physics. There are two types of interferences. One is constructive, one is destructive. So when these two waves will combine, either they will show constructive interference, and they can show destructive interference as well. So one by one, I'm showing you constructive and destructive over. Okay. So first of all, how do I represent the constructive interference? Just give the signs. Let's say this is positive, this is negative. These are not charges, right? These are the signs. Just to tell you that the waves are going to show the constructive interference. Whenever you have to show the constructive interference, do remember, same sign should be on same side. Positive on the top, positive on the top. Negative on the top, negative on the top. That means these waves are going to right now show the constructive interference. Or you can show these two waves are in phase right now. When the waves are in phase, then only they show what? Then only they show constructive interference. And let me tell you one thing. Due to constructive interference, let me tell you, bonding molecular orbital is always formed. So basically, over here, there will be constructive interference. And due to constructive interference, the resulting wave which I'll get, its amplitude will be maximum. So this resulting wave, it corresponds to what? It corresponds to that molecular orbital which is formed due to constructive interference. And which molecular orbital is formed due to constructive interference? It is the bonding molecular orbital. So do remember, when two waves are in phase, they'll show constructive interference, right? Due to which amplitude of the resulting wave is maximized. And which molecular orbital is formed? It is the bonding molecular orbital which gets formed. Okay. Now, for example, the two waves are going to show the destructive interference. How exactly you are going to show destructive interference? How you are going to show that? Let's say this is positive, this is negative. In order to show the destructive interference, opposite sign should be on same side. Positive, this is negative. Negative, this is positive. Check. Opposite sign on same side. So it will represent destructive interference, my dear students. It will represent destructive interference. So, can I say these two waves right now, are they in phase or out of phase? They are out of phase. They are out of phase. And due to destructive interference, my dear students, what will happen to the amplitude of the resulting wave? Amplitude of the resulting wave gets minimized. This is how your resulting wave looks like. Amplitude of the resulting wave has got minimized. And my dear students, this particular resulting wave, it corresponds to one more molecular orbital which got formed due to destructive interference, and that molecular orbital which gets formed due to destructive interference, that's always going to be your anti-bonding molecular orbital. That's always going to be your anti-bonding molecular orbital. So basically, do remember, bonding molecular orbital is formed due to constructive interference, anti-bonding molecular orbital is formed due to destructive interference. In phase, out of phase. I hope this point is clear to everyone. Let me know once in the chat quickly if this is clear. Then only I can talk about it a bit more in detail. Quickly in the chats. Quickly in the chats. Quickly in the chats. Everyone. Quickly. Yeah. Now guys, understand what I'm going to tell you now. Now it's going to be important. As I told you, due to constructive interference, molecular orbital. Which molecular orbital? Bonding molecular orbital is formed. Right? And I told you its energy is minimum and stability is maximum. Now why is that? Why energy of bonding molecular orbital is minimum, stability is maximum? There is a logic for that. Right? So first of all, this BMO is formed due to constructive interference. So let me show the constructive interference over here. Let's say this is the wave which corresponds to this particular atomic orbital, right? Let's assume its amplitude is represented by psi A. Psi A represents the amplitude of this wave over here. Similarly, we have got one more wave corresponding to one more atomic orbital, right? And I'm assuming that amplitude of this particular wave is psi B. Perfect. Now let me give you the signs. I need to show the constructive interference. This is positive, this is negative. So this has to be positive, this is negative. So which interference is happening between the waves? It's constructive interference, right? And due to constructive interference, which kind of molecular orbital is formed? Bonding molecular orbital. And due to constructive interference, what happens? Due to constructive interference or in-phase interference, this is the resulting wave which got generated, right? Whose amplitude is maximum. If I ask you, what is the amplitude of the resulting wave? You will say it is psi A plus psi B. This is the amplitude of the resulting wave. Okay? And this resulting wave, it corresponds to bonding molecular orbital. Now guys, tell me one thing. If I take square of this, psi A square, what kind of information psi square gives us? What kind of information psi square gives us? Psi square gives us the idea about the probability of finding the electron. This psi square, it gives me the idea about the probability of finding the electron around the nucleus in the atomic orbital A. Psi B square, probability of finding the electron around the nucleus in the atomic orbital B. Right? Or in short, psi A square, it gives you basically the electron density around the nucleus. It gives you the idea about the electron density around the nucleus of the atomic orbital of atom A. Right? Psi B square, it gives me the idea about the electron density around the nucleus of the atomic orbital of atom B, for example. Okay? So psi square gives me the probability of finding the electron. Now you tell me. The electron density around the nucleus of A is psi A square. The electron density around the nucleus of B is psi B square. Right? Perfect. What should be the electron density around the nuclei? Around the nuclei in this molecular orbital. Imagine it like this. Imagine it like this. The probability of finding the electron in atomic orbital first, it is psi A square. The probability of finding the electron around the nucleus in atomic orbital B, it is psi B square. So now these two atomic orbitals are combining right? They are forming the molecular orbital. What should be the probability of finding the electron in the molecular orbital? If it was psi a square, it was psi b square. It should be psi a square plus psi b square. It should be psi a square plus psi b square. But my dear students, if you take square of this amplitude, it becomes psi a square plus psi b square plus 2 times psi a psi b. Correct? It becomes psi a square plus psi b square plus 2 times psi a psi b. Right? Normal addition I'm doing. Correct? The probability of finding the electron in atomic orbital first was supposed to be psi a square. In atomic orbital second was supposed to be psi b square. Now these atomic orbitals are showing interference. They are combining. They lead to the formation of a resulting wave, which corresponds to bonding molecular orbital, which corresponds to molecular orbital. Now what should be normally the probability of finding the electron in the molecular orbital? It should be psi a square plus psi b square. But over here, do you see that it is not psi a square plus psi b square. It is psi a square plus psi b square plus 2 times psi a psi b. So has the electron density in the molecular orbital between the nuclei increased or decreased? You tell me. It was supposed to be psi a square plus psi b square, but it's coming out to be 2. It's coming out to be psi square plus psi b square plus 2 times psi a psi b. As the electron density. As the electron density in the molecular orbital increased or decreased? It has increased. By how much of amount? By this much of amount. Now you tell me, you imagine it like this. This was atomic orbital 1. This was atomic orbital 2. Perfect. Now they were showing the constructive interference. This was, for example, the nucleus. This was, for example, the nucleus of this. Right? Now, my dear students, I am telling you, when they show the constructive interference, the molecular orbital which we get in that molecular orbital, electron density is increased. By how much of amount? By this much of amount. How do I show it? Imagine as if, see, this is the electron cloud basically. This is the electron cloud. Imagine as if this part of the electron cloud will shift this side. Imagine as if, just to remember, this part of electron cloud has shifted this side. What will happen due to that? Due to that, the shape of the resulting molecular orbital will be like this. Due to that, the shape of the resulting molecular orbital will be like this. This is the nucleus. So let's say this is the nucleus. This one more nucleus, for example. Let's say this one more nucleus. Right? Now understand, in between, as the electron density increased or decreased, electron density in between has increased. Electron density in between has increased. By how much amount? By 2 times psi a psi b amount. Now, my dear students, if electron density in between the nuclei has increased, what will happen to the repulsion between the nuclei? Repulsion between the nuclei will decrease. And if repulsion decreases, what does that mean? Energy of the system would have decreased and stability would have increased. Perfect. So due to constructive interference, we get a molecular orbital in which the electron density between the nuclei that gets increased, due to which energy of the system that gets decreased, due to which the stability over here of this molecular orbital that gets increased. Hope you got to know how come the energy of your bonding molecular orbital is less and stability is quickly in the chat. Quickly in the chats, everyone. Quickly in the chats, everyone. Yeah? Right? Now let's see exactly. This was something in which I told you how this bonding molecular orbital is formed, why its energy is less and stability is more. Because the electron density, it gets increased, right? Due to which repulsions are decreased between the nuclei. And if repulsion decreases, that means energy of the system decreases, stability increases, right? Now, my dear students, there is one more type of interference, that is destructive interference. Let's assume these two atomic orbitals now are showing the destructive interference. They are showing now the destructive interference, out of phase interference. Out of phase interference, due to which anti-bonding molecular orbital gets formed, whose energy is comparatively more, stability is comparatively less, right? Why is that? Now you should be able to answer this question on your own. See, let's assume this is the wave corresponding to atomic orbital 1 and this is the wave corresponding to atomic orbital 2. I need to show destructive interference. In order to show destructive interference, opposite sign on same side. Opposite sign on same side. So it represents out of phase interference. It represents destructive interference, due to which the amplitude of the resulting wave, it gets minimized. So if the amplitude of the first wave was psi A, amplitude of the second wave was psi B. So what should be the amplitude of this wave? It has to be psi A minus psi B. It has to be psi A minus psi B, right? But psi itself, it does not have any significance. It is psi square which has significance, right? Psi square, probability of finding the electron in the atomic orbital, which I'm representing over here. Psi b square, probability of finding the electron in the atomic orbital, which I'm representing over here. So when these two atomic orbitals are combining, when they are showing the destructive interference, right? When they are showing the destructive interference, what will be the probability of finding the electron in the resulting wave? In the resulting wave, it should be psi a square plus psi b square. See, basically, psi a square, it is the probability of finding the electron. It is the electron density around the nucleus of the atom whose atomic orbital I'm mentioning over here, right? Psi b square, electron density, probability, electron density around the nucleus of the atom whose atomic orbital I'm mentioning over here. Or you can consider it like this: probability of finding the electron around the nucleus in the first atomic orbital, probability of finding the electron around the nucleus in the second atomic orbital. Now these two are combining. So what should be the probability of finding the electron? Probability of finding the electron in the resulting molecular orbital should be normally psi a square plus psi b square. But is it actually coming out to be psi a square plus psi b square? No. It's coming out to be psi a square plus psi b square minus 2 times psi a psi b. Right? This is the probability of finding the electron around the nucleus in the molecular orbital which got formed due to destructive interference. Now you tell me, has the electron density between the nuclei increased or decreased? It was supposed to be psi a square plus psi b square, but it is psi a square plus psi b square minus 2 times psi a psi b. Has it increased or decreased? It has decreased. Now you tell me, if the probability of finding the electron between the nuclei has decreased, how it would have looked like? For example, this was the atomic orbital. This was the atomic orbital. Let's say they are showing the destructive interference. For example, this is the nucleus, this is the nucleus. For example, just to represent. Okay. Now, if I need to show the destructive interference, what should happen? The electron density between the nuclei should decrease. It should decrease. That means this part of electron cloud, just to remember, it would have shifted this side. And this part of electron cloud, it should have shifted this side. So, how the molecular orbital would have looked like? The molecular orbital would have looked like this. The molecular orbital would have looked like this. Okay? This is the nucleus, and this is the nucleus of one more. I hope this is clear. Now tell me, between the nuclei, has the electron density increased or decreased? It has decreased. If the electron density has decreased, the repulsion between the nuclei would have increased. If the repulsion between the nuclei would have increased, what would have happened due to that? Energy of the system would have increased. And if energy would have increased, stability would have decreased. Energy have increased, that means stability have decreased. Right? This molecular orbital got formed due to destructive interference. And due to destructive interference, which bonding molecular is formed? Which molecular orbital is formed? It is the anti-bonding molecular orbital which gets formed. Right? So I hope you got to know why the energy of bonding molecular orbital is less, why the energy of anti-bonding molecular orbital is more. Now we are going to discuss this a bit more in detail. This was just the idea. Okay? This was just the idea. Now guys, have a look. I'll show you all the bonding molecular orbitals which get formed due to constructive interference. Okay, let me show you that. See, formation of molecular orbital is explained by LCAO, right? Either the waves will show constructive interference or the waves will show destructive interference. Due to constructive interference or in-phase interference, the electron density around the nucleus that increases. Due to which molecular orbital is formed? Bonding molecular orbital. So first of all, I'm going to show you the constructive interference. Let's say these are the atomic orbitals which are going to combine and they are going to show constructive interference. In phase, right? How do I show exactly whether they are showing the constructive interference or not? Same sign should be on same side. It represents that there is constructive interference. Due to constructive interference, the electron density that increases, right? The electron density around the nuclei in the molecular orbital that increases. So how it will look like? Imagine as if this part of electron cloud comes this side and this part of electron cloud comes this side. So how the resulting molecular orbital will look like? This is your resulting molecular orbital, which I showed a few minutes back also, right? So have a look exactly. This is negative, so make it negative. This is positive, so make it positive, right? And this part is negative, so make it negative. Perfect. This is the molecular orbital which got formed due to constructive interference. So I would say this is the bonding molecular orbital. This is the bonding molecular orbital. Now you tell me one thing. Now you tell me one thing. My dear students, if you remember VBT, SS was always the axial overlap or parallel overlap. SS overlap. Was it axial overlap or parallel overlap? Axial leads to the formation of sigma. So what should be the name of this particular molecular orbital? Is it supposed to be sigma or sigma star? It's supposed to be sigma. And I'll be calling this as sigma 1s. So this is the first molecular orbital which got created due to constructive interference. Okay. Similarly, let's have a look on one more. I'm right now showing constructive interference. Let's say 2p atomic orbital of one atom and 2p atomic orbital of one more atom. Let's say they are combining. But right now I'm showing only the constructive interference. Right? In phase, constructive interference. And during the constructive interference, the electron density between the nuclei that increases. Right? That increases. So imagine as if this lobe, the electron density in this lobe, imagine as if this got shifted this side, the electron density in this lobe, it got shifted this side. See, first of all, same sign, same side. So it's constructive, right? And due to constructive interference, which orbital is formed? Which molecular orbital is formed? Bonding molecular orbital. So bonding molecular orbital is going to get formed. And in the bonding molecular orbital, the electron density between the nuclei, that should increase, right? That should increase. So imagine as if, this electron cloud, it got shifted this side, this electron cloud got shifted this side. So how the resulting molecular orbital will look like? The resulting molecular orbital will look like this. This is how your resulting molecular orbital will look like. This is negative here, so make it negative. This is negative, so make it negative. And in between, what is the sign? Positive sign. Right? Okay, 2p and 2p along the axis, will they show axial overlap or parallel overlap? They show the axial overlap, which leads to the formation of sigma bond, right? So what should be the name of this molecular orbital? Is it going to be sigma or pi? This is going to be sigma. I'll be calling this a sigma and 2pz. This is sigma 2pz molecular orbital. Perfect. Right? I hope this is clear. Guys, at the same time, one more thing. Okay, leave that part aside. I'm going to let you know afterwards. Okay, one more thing. Do you see any nodal plane here in this molecular orbital? Nodal plane, imagine it like this. Can you draw a plane in this molecular orbital in any direction on which the electron density won't lie at all? I can draw a plane in the middle, but the plane which I'm drawing in the middle, on the plane, some electron density will lie, right? If you draw the plane in this direction, in every plane, electron density will lie, right? So there is no plane as such which I can draw on which electron density won't lie. Electron density won't touch. Yeah? Right? So that means in this molecular orbital, is there any nodal plane? There is no nodal plane in this molecular orbital. And which molecular orbital this is? Is this bonding or anti-bonding? This is bonding molecular orbital, which got formed due to constructive interference. Similarly, my dear students, let's say this is 2p, this is 2p. Now this is 2py, this is 2py. Okay? So first of all, same sign, same side. What is it going to be? Constructive. It will lead to the formation of bonding molecular orbital, right? Electron density should increase between the nuclei. Now they are parallel basically. They are parallel. Perfect. Now tell me one thing. The electron density between should increase, correct? So what will happen in the constructive interference? Imagine as if this lobe bends in this direction, this lobe bends in this direction, this lobe bends in this direction, this lobe bends in this direction. So the resulting molecular orbital, how it looks like? This is how it looks like. This is how it looks like. So positive, positive, make this positive and make this negative. So first of all, remember your VBT. Was it supposed to be, in VBT, was it supposed to be axial overlap or parallel overlap? It was supposed to be parallel overlap, which leads to the formation of pi bonds, if you remember. So should I be calling this molecular orbital as sigma molecular orbital or pi? It is going to be pi molecular orbital. This is going to be pi 2py. Pi 2py. My dear students, you tell me one thing. Do you see any plane? Can you draw any plane in this molecular orbital in such a way that no electron density lies on it? I can draw one plane. Exactly in the middle, I can draw a plane. If I draw a plane, on that plane, there will be no electron density because the electron density is above the plane and below the plane. That means that I can draw one plane on which electron density won't lie at all. And that plane is something which I call as nodal plane. So nodal plane in this molecular orbital is 1. There is one nodal plane. In 2py, bonding molecular orbital. This is the bonding molecular orbital. Perfect. Right? Similarly, my dear students, let's see one more. This is how it looks like exactly. This is how it looks like exactly. This is the nodal plane. Electron density, electron density. This is pi 2py molecular orbital. Now, similarly, let's see how d orbitals combine and show constructive interference. My dear students, have a look. Positive, positive, negative, negative. Same sign, same sign. So constructive interference is going to happen. In phase interference is going to happen. Due to which bonding molecular orbital is going to get formed. And in the bonding molecular orbital, the electron density between the nuclei, that should increase. So what should happen? You can remember it like this. Imagine as if this particular lobe, the electron density in this lobe has shifted, for example, in this direction. Electron density in this lobe has shifted in this direction, for example. Similarly in this direction, similarly in this direction. So how it looks like finally? How it looks like finally? It looks like this. It looks like this. You can give the signs. Say, this electron density is shifting in this direction, right? And this electron density is shifting in this direction. Similarly, this electron density is shifting in this direction. This electron density is shifting in this direction, right? So which molecular orbital this is? First of all, in VBT, what do we call this overlap as? In VBT, parallel, which leads to the formation of pi. So the molecular orbital which got formed, what should I be calling this as? This is going to be your pi dxy. Let's say this is your 3dxy. Let's say this is your, for example, 3dxy. So this is going to be 3 pi dxy, molecular orbital. Okay? Yeah? Now you tell me one thing. Is there any nodal plane? You can draw one plane in the middle exactly, on which electron density won't lie. So that plane is the nodal plane. So one nodal plane you have got in this molecular orbital, which is the bonding molecular orbital basically. I hope this is also clear. I hope this is also clear, right? Yeah? Perfect. Is it clear, guys? Quickly. So first of all, this lobe, its electron density got shifted. So this lobe, it will shrink. So this will be positive, right? This will be positive. And this will be positive. This will be positive. This is negative. This is negative. This is negative. This is how you are going to represent. I hope you are getting it properly. All right. Now let's have a look exactly. Now let's have a look exactly how anti-bonding. This is how, I mean, this is what we saw. What we saw exactly is how bonding molecular orbitals are formed, right? Now let's see how anti-bonding molecular orbitals are formed, right? Due to destructive interference. So now we are going to talk about the destructive interference. Let's see exactly how they are formed. See guys, for example, this is 1s and this is 1. I need to show destructive interference between the two. Check opposite sign on same side. Destructive. It will lead to the formation of anti-bonding molecular orbital. And in the anti-bonding molecular orbital, the electron density between the nucleus that decreases. So imagine as if this part of electron density goes on this side, this part of electron density, for example, goes on this side, just to make you understand. So that the resulting molecular orbital, it looks like this, right? This will be negative, this will be positive, right? And this will be negative, this will be positive. Perfect. Right? Now, first of all, this is SS. In VBT, SS used to be axial overlap, leads to the formation of sigma. So should I be calling this as sigma or pi? It's going to be sigma. Now, has the electron density between the nucleus increased or decreased? It has decreased. That means which bond got formed? Which molecular orbital is formed? Anti-bond. And anti-bondings are represented by star. So it is sigma star. Which sigma star it is? It is sigma star 1s. It is sigma star 1s. Do you see any plane in this molecular orbital on which electron density won't lie? If I cut it in the middle, this plane which goes into this, right? On this plane, there'll be no electron density. So nodal plane is 1. There is one plane as such on which there'll be no electron density. Okay? I hope this is clear. Similarly, my dear students, let's have a look on few more things. Tell me whether this is constructive or destructive. Positive, negative, opposite sign on same side. Destructive, right? Destructive. They lead to the formation of antibonding molecular orbital. And in the antibonding molecular orbitals, the electron density between the nuclei, that will decrease. So imagine as if this lobe electron density got shifted in this direction. This lobe electron density, for example, got shifted in this direction. So what is the shape of the resulting molecular orbital? See, this electron density is shifting in the other side. So this particular lobe will shrink, right? Similarly, this particular lobe will shrink, right? So how it looks like finally. This is how it will look like, right? This is how it will look like. This is minus. So let me call this as minus. This is plus, right? This is minus and this is plus. Okay, you tell me one thing. Should I be calling this as, okay, you tell me whether this is, if this was in VBT, tell me, was it axial overlap or parallel overlap? It was axial, which leads to the formation of sigma. So this molecular orbital which I got over here, should I be calling it as sigma or pi? It is sigma. Should I be calling it as sigma or sigma star? Electron density between the nuclei that has decreased. So I'll be calling it as sigma star. Sigma star what? Sigma star 2px. And tell me, do you see any plane over here? Do you see any plane over here on which zero electron density will lie? This is the plane in the middle, which you can draw. And on this plane, you'll find no electron density. That means there is one plane as such which you can draw on which there is no electron density. It has got one nodal plane, right? Clear? So antibonding molecular orbital got formed. Similarly, one more. Tell me whether this is going to be constructive or destructive, positive, negative, destructive. Electron density between the nucleus will decrease, right? So this is destructive. Which molecular orbital? Anti-bonding molecular orbital gets formed, right? Electron density between the nucleus should decrease. So this lobe will shift in this direction. This lobe will shift in this direction. This in this direction. This is this in this direction, right? So how exactly it's going to look like? It's going to look like this. Give the signs. This is positive. This is negative. This is negative. This is positive. Correct? So tell me, if this was the overlap happening in VBT, was it supposed to be axial or parallel? It was supposed to be parallel, right? It was supposed to be parallel. And due to parallel overlapping, which bond used to get formed? Pi. So this molecular orbital, should I be calling this as sigma or pi? This is pi. Should I be calling this as pi or pi star? This is pi star because anti-bonding molecular orbital got formed. Should I be calling this as pi star 2py? Absolutely, this is pi star 2py, right? It's pi star 2py. Electron density between the nuclei has decreased. Now tell me how many planes you can draw over here on which no electron density will lie, zero electron density will lie. This is one plane and this is one more plane. So over here, these are the two nodal planes on which you find zero electron density. So two nodal planes in pi star 2py. I hope this is also clear, right? I hope this is also clear. Similarly, my dear students, tell me one more thing. Is this again going to be constructive or destructive? This is, for example, d orbital. This is d orbital. Positive, negative, negative, positive. Opposite sign on same side. Opposite sign on same side. So what is it going to be? It is going to be again the destructive interference, out of phase interference, which leads to the formation of anti-bonding molecular orbital. And in the anti-bonding molecular orbital, the electron density between the nuclei that decreases. By how much amount? 2 times size. Yeah, right? So imagine as if this particular lobe, the electron density in this lobe, for example, got shifted in this direction. It got shifted in this direction. This is getting shifted in this direction. This is getting shifted in this direction. So how it exactly looks like? This is how exactly it's going to look like. This is how exactly it's going to look like. Now tell me one thing, whether this is going to be your sigma star or pi star. Tell me quickly. Absolute humor, you're right. I mean, whenever two atomic orbitals will combine, they'll form two molecular orbitals. One will be bonding, one will be anti-bonding. Is it going to be sigma star or pi star? It's going to be pi star, right? Which pi star? For example, this is, let's say 3dxy. This is again 3dxy. So this is supposed to be 3d pi star 3dxy, right? This is supposed to be pi star 3dxy. Pi star 3dxy. Now you tell me, how many nodal planes do we have in this one? How many nodal planes? How many nodal planes in this one? Quickly. This is one nodal plane and this is one more nodal. So there are two nodal planes in this particular molecule. So I hope you got to know exactly how exactly your bonding and anti-bonding molecular orbitals are formed, right? I hope you got to know exactly how your bonding and anti-bonding molecular orbitals are formed, right? Perfect. And you saw exactly how do we calculate the nodal planes in bonding and anti-bonding molecular orbitals. Now, my dear students, since you know, for example, two atoms I have. Let's say these are the two bonding atoms. They have to form a bond, right? What will happen? They'll come closer. What will happen? Their atomic orbitals, they'll combine. They will lead to the formation of molecular orbitals. Oneness of this, oneness of this will combine to form two molecular orbitals. Similarly, 2s of this, they'll combine to form two more molecular orbitals. One bonding, one anti-bonding. Similarly, a lot of molecular orbitals are getting formed, out of which few will be bonding, few will be anti-bonding. Right? Out of which few will be bonding, few will be anti-bonding. Correct? Now, my dear students, once the combination of atomic orbitals is done, once the formation of molecular orbitals is done, after that, we are supposed to fill these molecular orbitals with the electrons as per a Bose principle, as per Hund's rule, and as per Pauli's exclusion principle, right? And how we are going to do that? My dear students, these are all the molecular orbitals. Which are arranged as per their increasing order of the energy. These are the molecular orbitals which are arranged as per their increasing order of energy. And this energy order you have to remember. And this energy order you will follow only up to those molecules wherein the total number of electrons are till 40. Now have a look what I'm going to talk about. This is the energy order of the molecular orbitals, right? Every molecular orbital can accommodate a maximum of 2 electrons. Every molecular orbital can accommodate a maximum of 2 electrons. Now see what all things I can conclude from it. Understand. For example, I have got H2 molecule. How many electrons are there in total? 2 electrons. Now fill those 2 electrons. 1, 2. Correct? If I ask you, what is the bond order of H2? It is going to be half of number of electrons in bonding. The configuration, the molecular orbital configuration of H2 is sigma 1s2. It is sigma 1s2, right? So there are 2 electrons in bonding molecular orbital. Is there any electron in anti-bonding? No. 0 electron in anti-bonding. So the value comes out to be 1. That means between 2 hydrogen atoms, you'll find a single bond. Between 2 hydrogen atoms, you'll find a single bond. Point number 1. Point number 2. The molecular orbital configuration of H2 is basically sigma 1s2. Is there any unpaired electron? There is no unpaired electron. If there is no unpaired electron, that means this particular species is going to be diamagnetic in nature. It is going to be diamagnetic in nature. How do you calculate magnetic moment? Magnetic moment is calculated as under root of n into n plus 2 Bohr magnetrons. N represents number of unpaired electrons. Number of unpaired electrons here are 0. So the magnetic moment has to be 0 in case of what? In case of H2. In case of H2. I hope you're getting it. Right? Now, let's talk about one more. He2. He2. One helium atom has got 2 electrons in total. So 2 helium atoms, 4 electrons. So fill that 4 electrons, 2 here and 2 here. So configuration becomes sigma 1s2, sigma star 1s2. Calculate the bond order is equal to half of number of electrons in bonding, 2 electrons in bonding, minus number of electrons in anti-bonding, 2 electrons in anti-bonding, the value comes out to be 0. So what does that mean? The bond order is coming out to be 0 for He2. That means He2 does not exist. He2 does not exist. Similarly, Li2, total 6 electrons, 2, 4 and 6. Calculate the bond order. Half of number of electrons in bonding, 2. 2 plus 2 is 4, minus anti-bonding, that is 2. The value comes out to be 1. So that means between 2 lithium atoms, what you will find? Between 2 lithium atoms, you will find a single bond. Do you see any unpaired electron? There is no unpaired electron right now. If there is no unpaired electron, what does that mean? That means the magnetic moment will be 0. And the species is going to be diamagnetic in nature. Right? Perfect. Talk about Be2. 1 beryllium. It's 1 beryllium atom. Its atomic number is 4. So 4 electrons, 4, 4, 8. 8 electrons in total. So 2, 4, 6, right? 7 and 8. So calculate the bond order. It is half of number of electrons in bonding, 2, 4, minus number of electrons in anti-bonding, 2 and 4. The value comes out to be 0. So this particular species, it does not exist. It does not exist. I hope it is clear to everyone. Yeah. Now similarly, my dear students, 2 more examples. Have a look. B2. Total 10 electrons. One boron has got 5 electrons, so B2 will have 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. These are degenerate. 9 and 10. So the molecular orbital configuration of B2 is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x1, pi 2p y. This is the molecular orbital configuration of your B2. Now tell me its bond order. It's going to be half of number of electrons in bonding, 2, 4, 5, 6, minus number of electrons in anti-bonding, 2, 4, right? The value comes out to be 1. If the value comes out to be 1, that means between 2 boron atoms, there is a single bond. Between these boron atoms, there is a single bond, right? Perfect. Now tell me, is there any unpaired electron? Do you see any unpaired electron here? Do you see any unpaired electron? There are 2 unpaired electrons because every molecular orbital can accommodate 2 electrons. This has only 1. This is only 1. So there are 2 unpaired electrons, right? 2, 4, 6, 8, 9, 10, right? There are 2 unpaired electrons. If there are unpaired electrons, how do we calculate magnetic moment? Under root of n into n plus 2. Root of 2 into 2 plus 2, right? So 4, 4, 2s are 8. So root of 8 Bohr magnetrons. So I would say this particular species, is it going to be diamagnetic or paramagnetic? This is going to be paramagnetic in nature. Those species which have got magnetic moment non-zero, those are paramagnetic, right? Those species which have got magnetic moment 0, they'll be diamagnetic. Talk about C2. Calculate the bond order. Bond order will be half of number of electrons in bonding. So write the molecular orbital configuration of C2. Total 12 electrons. So 10 we have filled, 11 and 12, right? So how many electrons in bonding? 2, 4, 6, 8, minus anti-bonding 4. The value comes out to be 2. So between 2 carbon atoms, there is a double bond. There is a double bond. Do you see any unpaired electron? There is no unpaired electron. So it is supposed to be diamagnetic. It is supposed to be diamagnetic. Its magnetic moment has to be 0. Its magnetic moment has to be 0. I hope this is clear also, right? Do remember at the same time, both the bonds in C2 molecule, these are both the bonds pi. Otherwise, what VBT told, if you remember, VBT told the first bond that gets formed between 2 atoms, that's always sigma, followed by pi. But this is the molecule wherein both the bonds are pi. Explained by VBT. If you see the outermost configuration, outermost molecular configuration, right? This particular bond, it forms 1 pi bond. This forms 1 more pi bond. So both the bonds over here are pi. So in case of C2, both the bonds are pi. There are 2 pi bonds in case of C2 molecule. Right? Rest of the things I'm sure you can easily do now. Bond N2. N2. Calculate its bond order. You can do. It will come out to be 3. It will come out to be 3. Right? N2 positive. N2 positive. How much it's going to be? Or let me show you N2 first of all. Then there is one important thing which I have to tell you over here. Understand properly. N2, there are total 7, 7, 14 electrons. So 2, 4, 6, 8, 10, 12. 12 to 14. Correct? So calculate the bond order over here. It's going to be half of number of electrons in bonding. So 2, 4, 6, 8, 10 minus number of electrons in anti-bonding. 2, 4, right? The value comes out to be 6 by 2. That comes out to be 3. So between two nitrogen atoms, there is a triple bond. Perfect. There is a triple bond. Perfect. Triple bond means 1 sigma and 2 pi. Check. This is 1 sigma bond and this is 1 pi, this 1 more pi. Perfect. 1 sigma and 2 pi. Now tell me one thing. Is there any unpaired electron? There is no unpaired electron. So this has to be diamagnetic, number 1. Right? Okay. N2 positive. N2 positive. So total N2 had 14 electrons. N2 positive will have 13 electrons. Right? So remove 1 electron from here. Remove 1 electron from here. If you remove 1 electron from here, what will be the bond order? It's going to be half of. Number of electrons in bonding now are going to be 9. 9 minus 4, the value is 2.5. Similarly, in this particular case, the value also comes out to be 2.5. Perfect. Now understand one important thing. Understand one important thing over here. N2 has got the bond order of 3. We have got N2, we have got N2 positive, we have got N2 negative. What about the bond order? Bond order of N2 is 3. This is 2.5. This is 2.5. Right? More the bond order, more the stability. If I ask you, what about the stability order? What about the stability order? N2 should be maximum stable because its bond order is maximum. N2 positive, N2 negative, their bond order is same, right? So their stability should be same. But I told you one thing in the beginning. Whenever two species will have same bond order, calculate the anti-bonding electrons. More the anti-bonding electrons, lesser the stability. Lesser the stability. N2 positive. In N2 positive, how many how many anti-bonding electrons were there? In case of your N2 positive, there were 2 to 4. 4 anti-bonding electrons were there in N2 positive. In N2 negative, what you will find? In N2 negative, you will find additional anti-bonding electron. Is that? Or we can check it out too. We can check it out too. Just a second. 2, 4, 6, 8, 10, 12. Right? 10, 12. And this is 13. So this is N2 positive. So in N2 positive, how many anti-bonding electrons are there? There are 4 anti-bonding electrons. Now N2 negative, total 15 electrons. So 13 till here, 14 and 15. Now in N2 negative, there are 2, 4 and 5. Right? So in this particular species, there were only 4 anti-bonding electrons and here there are 5 anti-bonding electrons. And I told you already, more the anti-bonding electrons, lesser the stability. More the anti-bonding electrons, lesser the stability. So anti-bonding electrons are more here. So its stability should be less. So stability order should be this. This has to be the stability order. I hope this is clear. I hope this is clear. And my dear students, those species which have got total number of electrons more than 14, for them, this is the order which you are going to follow. In this order, you are going to fill the electrons. In this order, you are going to fill the electrons. I'm going to show you a few cases. For example, O2, in total 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16, right? They generate orbitals, these are, correct? Luke, there you have to use N2 negative, it comes into the category of first because its parent atom has got 14 electrons. See, you must be confused like this. See, N2 is a 14 electron species, right? But N2 negative is the 15 electron species. You must be thinking till 14 electron species, we have to follow the other order. But more than 14 electron species, we have to follow this order. But my dear students, this N2, it has got 14 electrons. N2 negative has got 15 electrons. So as per something which I told you a few minutes back, any species which has more than 14 electrons should follow this energy order. But if its parent atom comes in the earlier category, then this has to be also in the earlier category. Right? This has to be also in the earlier category. All right. Now understand. So 2, 4, 6, 8, 10, 12, 14, 15, 16. Correct? So write the bond order for O2. It's going to be equal to half of number of electrons in bonding. 2, 4, 6, 8, 10. Minus number of electrons in anti-bonding. 2, 4, 5, 6. The value comes out to be 2. Right? So between two oxygen atoms, there will be a double bond. there will be a double bond. Perfect. And my dear students, at the same time, if I ask you whether this is paramagnetic or diamagnetic, look at the unpaired electrons. There are unpaired electrons, so it is supposed to be paramagnetic. If I ask you, what about its magnetic moment? You can calculate it. Magnetic moment is equal to under root of n into n plus 2. N into n plus 2. So it's going to be a root of 8 Bohr magnetrons. This is the magnetic moment of your O2. Now talking about O2 positive. Talking about O2 positive, right? O2 positive. O2 positive will have 15 electrons. So remove one from here. Remove one from here. If one is removed, calculate the bond order now. It's going to be equal to half of number of electrons in bonding are 10 minus anti-bonding now are 5. So the value comes out to be 2.5, right? Again, one unpaired electron, so it has to be paramagnetic. If you want to calculate its magnetic moment, it's under root of n into n plus 2. So 2 plus 1 is 3. So root of 3 Bohr magnetrons is the magnetic moment of this particular species. Okay? Right? O2 negative. O2 negative. 17 electrons in total. Right? 17 electrons in total. So 2, 4, 6, 8, 10, 12, 14, 15. 16, 17. So 17 electrons in total. So calculate the bond order now. The bond order has to be half of number of electrons in bonding. Number of electrons in bonding are going to be same, 10 minus number of electrons in anti-bonding, 2, 4, 6, 7, right? So 10 minus 7 is 3, 3 by 2 is 1.5. Perfect, O2 negative has got 1.5. But I think we did some mistake here. O2 is, okay, yeah, it's correct. O2 is 2, it's 1.5. Similarly, when you talk about O2 di-negative, its bond order will come out to be 1. Right? O2 di-negative means 18 electron species. Okay, its bond order will be 1. And similarly, you can talk about their paramagnetism, you can talk about their diamagnetism. In short, do remember, if there are unpaired electrons, it's going to be paramagnetic. If there are no unpaired electrons in the molecular orbitals, it's going to be diamagnetic. As simple as that. Okay, as simple as that. At the same time, there is one more thing. Whenever you see the isoelectronic species, isoelectronic species will have same bond. For example, you have got N2 and you have got CO. Both are 14 electron species. And all the 14 electron species will always have the bond order of 3. Right? Perfect. So bond order of this particular species is 3. Even bond order of this particular species. All the isoelectronic species, the ones which have got same number of electrons. The ones which have got same number of electrons, they are isoelectronic, and isoelectronic species will be always having the same bond order. Right? This is one more thing which you need to know. Okay, tell me one thing. This is O2. This is, for example, O2 negative. This is O2 di-negative. First of all, talk about their bond order. This is 2, right? This is 1.5 and this is 1, right? Talk about their bond energy, bond dissociation energy. More the bond order, this is the bond order, right? This is the bond order. What about the bond dissociation order? So more the bond order, more the bond dissociation energy. So this has to be the bond dissociation energy. What about the bond length? Inversely proportional, right? This has to be the bond length order. Perfect. So anything out of these things can be asked. Either you will have to compare the bond orders, or you will have to compare the bond dissociation energy, or you will have to compare the bond strength. Bond strength is more when the bond order is more. So bond strength order will be this. This is the bond strength order. Anything can be asked out of these things. I hope all these things are clear to you. Okay? These two species, their bond orders, you are going to let me know in the comment section of the video. These are simple, right? NO positive, CN negative. Do tell me about their bond orders. Do tell me about their bond orders in the comment section, right? Now, my dear students, if you don't want to calculate bond order like this, there is one trick as well. There is one trick as well. Do remember, whenever you have a 14 electron species, 14 electron species always will have bond order of 3. 15 electron species will have bond order of 2.5. 16 electron species always will have bond order of 2. 17 electron species will have bond order of 1.5. 18 electron species will have the bond order of 1. Similarly, 13 electron species, they will have bond order of 2.5. Similarly, 12 electron species, they'll always have the bond order of 2. 11 electron species, 1.5. 10 electron species, 1. This is one trick which you can remember directly. Then you don't have to use the formula as well. Yeah. Right? Is it clear, people? Is that clear till here? This is something 14 electron species, bond order 3. Increase the electron, decrease by 0.5. Increase the electron, decrease by 0.5. Increase the electron, decrease by 0.5. Right? Similarly, decrease the electron, decrease by 0.5. Decrease the electron, decrease by 0.5. It gets decreased by 0.5 or, right? This is something which you can remember directly. Perfect. So this was about your molecular orbital theory, from which these sort of questions can be asked. 1. Bond order, bond dissociation energy, bond strength, nodal planes, etc., etc. Now, my dear students, there is one more small topic. There is one more small topic in which you are supposed to compare. What you are supposed to compare? You are supposed to compare basically the bond angles, right? You are supposed to compare the bond angles. Perfect. And I'm going to give you one trick which you guys are going to remember so that you can solve all the questions based on bond angle, right? And that too easily. So whenever a question is asked from the bond angle, you have to compare the bond angle. The first thing which you will see always, you'll give priority to VSCPR theory. You'll give priority to VSCPR theory. Any species of the type AB2L0 or AB2L3, any species of the type AB2L0 or AB2L3, they'll have the maximum bond angle because they are linear ones. They'll have bond angle of 180, and 180 is the maximum which we can have. So whenever you are given with 2, 3, 4 molecules and you have to arrange them on the basis of bond angle. So first of all, you will check through VSCPR. If there is any molecule of this type AB2L0 or AB2L3, their bond angle will be maximum, that's 180. If you are unable to solve a question with the help of VSCPR, let's say there is no molecule of the category AB2L0 and AB2L3, right? That means you are not able to solve the question with VSCPR. Then you can consult hybridization. If the hybridization of the central atom comes out to be different, right? For example, one central atom got sp in the other molecule. In the another central atom got sp2. In the third molecule, one more central atom got sp3. And you know, in case of sp, the bond angle is 180. In case of sp2, the bond angle is 120. In case of sp3, the bond angle is 109 degree 28 minutes. Then you will answer as per hybridization. First, you will check VSCPR, right? First, you will check VSCPR. If there is AB2L0 or AB2L3, maximum bond angle. After VSCPR, you will go to hybridization, right? Let's say you are given with 3 molecules. The central atom of the first molecule, for example, that is sp hybridized. The central atom of the second molecule, for example, that is sp2. Similarly, the third molecule, that's sp3. Then this has to be the order of the bond angle because it's 180, 120, 109. Now, if the hybridization of the central atom is also same, then 2 cases arise. If the hybridization of central atoms is same, then 2 cases arise. First case, if lone pair is absent on the central atom, then you will give your answer according to hybridization. For example, you have got BF3, you have got BCl3, you have got BBr3, you have got BI3. First thing, hybridization of the central atom. The central atom does not have any lone pair. 3 sigma bond, 0 lone pair. sp2, sp2, sp2 everywhere. sp2, sp2, sp2. Correct? Hybridization is same. Hybridization of the central atom is same. Lone pair is absent. Right? If the hybridization is same, that means their bond angles will be same. So you'll be giving your answer as per your hybridization. Perfect? Their bond angles will be same. Now, for example, if lone pair is present on the central atom, if hybridization of the central atom is same, at the same time, there is lone pair present on the central atom, then do remember, number of lone pairs present on central atom is inversely proportional to bond angle at that time. Okay, if the hybridization is same and the central atom contains a lone pair, then do remember number of lone pairs more, that means bond angle less. Okay, one more case arises here. if hybridization and number of lone pairs both are same, if hybridization as well as number of lone pairs both are same, then you have to check on the basis of size of surrounding atom and size of central atom. If size of surrounding atom is same, bond angle, if size of surrounding atom is more, bond angle will be more. If the size of surrounding atom is more, bond angle will be more. And if the size of central atom is more, bond angle will be less. Let's try to use this particular chart in the question so that you can understand it properly, right? The first set of questions. I hope you got to know how this diagram is used. First, check through VSEPR. If not, hybridization different. If hybridization same, then there are two cases, right? If lone pair is absent on the central atom, give your answer as per hybridization. If lone pair is present on the central atom, right? If lone pair is present on the central atom, then number of lone pairs more, bond angle less. And if hybridization as well as number of lone pairs are same, then decide on the basis of size of surrounding atom and size of central atom. More the size of surrounding atom, more the bond angle. More the size of central atom, lesser the bond angle, right? In the first case, size of surrounding atom is directly proportional to size of surrounding atom is directly proportional to bond angle, right? And similarly, size of central atom is inversely proportional to bond angle. Perfect. Now let's try to do certain examples so that you can understand it properly. Okay. The first question, which is on the screen, what do you think about this one? CO2, NO2 positive, XCF2. Look at the type of the molecule. VSTPR. First priority VSTPR. Look at the type of the molecule. This particular first molecule is of the type AB2L0. Second molecule is of the type AB2L0. Third molecule is of the type AB2L3. Right? And AB2L0, AB2L3. They're all linear. Their bond angle will be 180. So their bond angles are equal. Done? Their bond angles are equal. If you want to check it also, for example, NO2 positive is there, right? NO2 positive is there. Nitrogen is the central atom. 5 valence electron. Positive charge, matlab subtract 1. So value comes out to be 4. Sigma bonds are 2. Number of surrounding atoms. Oxygen is divalent. So out of 4 valence electrons, all the 4 valence electrons utilized. So lone pair on nitrogen is 0. Steric number is 2. Type of the molecule is AB2L0. That's what I mentioned here, right? I told you already, if you find a molecule of the type AB2L0 or AB2L3, they are going to be linear. Their bond angle has to be 180. So prioritize that first. Okay. Second, my dear students. First of all, this is AB2L0. This is AB3L0. This is AB4L0. Right? So you cannot decide on the basis of VSEPR. After VSEPR, you have to go for hybridization. Hybridization here is SP. Here it is SP2. Here it is SP3. Hybridization of the central atom, hybridization of the central atom is different. SP, SP2, SP3. So give your answer as per hybridization. As per SP, the bond angle has to be 180. SP2, 120. SP3, 109 degree, 28 minutes. So this has to be the bond angle order. Right? There's something which I told you in the table a few minutes back. Look at this particular case. First of all, the type is different. Leave the type aside. So this is SP3. This is also SP3 because nitrogen has got a lone pair. This is also SP3. Oxygen has got 2 lone pairs. Now, no doubt the hybridization is same. No doubt hybridization is same over here. No doubt hybridization is same. But over here, central atom, it does not have a lone pair. Over here, the central atom has got 1 lone pair. Central atom has got 2 lone pairs. Now, which rule you are going to follow here in this particular case? Which rule you are going to follow here in this case? Hybridization is same, but lone pairs are present. Hybridization is same. Hybridization is same, but lone pairs are present at the central atom. More the lone pairs, lesser the bond angle. More the lone pairs, lesser the bond angle. More the lone pairs, lesser the bond angle. So among these two, bond angle of NH3 will be greater than that of bond angle of H2O. Perfect? Right? And this has to be the order. More the lone pair, lesser the bond angle. Perfect? Look at the next one. First thing, look at the type of the molecule. AB3, AB3, AB3. Right? So there is no one which is either AB3, AB2L0 or AB2L3 type. So you cannot decide on the basis of that. Go for hybridization. Hybridization of this particular molecule is sp2. This one is sp2. This one is sp2. Hybridization of the central atom is same. And at the same time, there is no lone pair on the central atom. Hybridization is same, no lone pair on the central atom. Give your answer as per hybridization. So their bond angles have to be equal. Right? This particular statement which I told you. This particular statement which I gave you. Right, people? Perfect. All right, so this is the solution of it. Okay. Look at this one. Look at this one. What do you think now? What do you think now? First of all, the type of the molecule is AB4, AB4. So from type, I can get nothing. Look at the hybridization. This is sp3, this is sp3, this is sp3. sp3, right? Central atom does not have any lone pair. Give your answer as per hybridization. Bond angle same, right? Bond angle is same. Look at the next one. Look at the next one. All the species over here are sp3 hybridized. And there is lone pair on the central atom. And amazing part is the central atom everywhere has got same number of lone pairs. First of all, hybridization everywhere is same. sp3, sp3, sp3 everywhere. Hybridization is same. Lone pairs are also same. Hybridization is same and lone pairs are also same. That means this particular one. Hybridization as well as lone pairs are same. Right? Now, which atoms are different? Check the atoms. Check the atoms. Which atoms are different? Central atom is different. Central atom is different. Surrounding atom is same. So you'll give your answer as per your central atom. Now, as per central atom, size of central atom is inversely proportional to bond angle. Size of central atom is inversely proportional to bond angle. Size of central atom is inversely proportional to what? Is inversely proportional to bond angle. So where do you see the central atom has got maximum size? Maximum the size of central atom, lesser is going to be the bond angle. Because bond angle is inversely proportional to the size of central atom. Perfect. So this has to be the bond angle order. Okay. Perfect. Right, people? NF3, NCl3, NBr3. What do you think? Hybridization, sp3. Hybridization, sp3. Hybridization, sp3. Central atom has got one lone pair. Everywhere one lone pair. Central atom has got one lone pair as well as hybridization is same. Right? Now central atom is same, but surrounding atom is different. Bond angle is directly proportional to size of surrounding. Right? Bond angle is directly proportional to what? Size of surrounding atom. Right? So more the size of surrounding atom, more the bond angle. More the size of surrounding atom, more the bond angle. And this is your homework question. This is your homework question. I hope you exactly got to know how to deal with the questions based on bond angles as well. And my dear students, with this, your chapter chemical bonding is done and dusted. There is one topic which I did not touch, which is the easiest of all, which I would want you guys to do on your own. Hydrogen bonding. Hydrogen bonding, right? Just consult NCERT. There is one paragraph given. Just read it. That's more than sufficient. That's complete theoretical one. There is no exceptions, nothing there, right? That is the easiest of all. That's something which I would want you guys to do on your own. Is that cool? And my dear students, one more important thing. Day after tomorrow, we are starting the chapter thermodynamics. We are starting the chapter thermodynamics. Day after tomorrow at 5 p.m., I'll have a session on thermodynamics, and this chapter I'll be doing in 2 parts, right? This chapter I'll be doing in 2 parts. So right now, the thumbnail is already there on the channel. The thumbnail is already uploaded on the channel, right? I would want you guys to click on notify me right now, okay? So that all of you must get the notification of that particular session, which is thermodynamics, because that is one amazing chapter which people find difficult basically, but I'll try my level best to make it easy for all, okay? With the proper quality content. Perfect? Done? And at the same time, the PDF of this particular session, I'll be providing you on this Telegram, t.me/WASSIM SIRCHEM. This is the Telegram channel on which I'll be providing you exactly the handwritten PDF of this particular. And do let me know in the comment section of this particular video, did you enjoy the session? And whatever homeworks I've given you in the today's session, please and please do let me know the answer of those particular questions. There are almost like 2 questions which I've given you. Okay, and I would want you guys to revise this chapter again at 2x speed. You can revise it so that all the concepts which I've told you in this chapter, those will be properly there. Okay, perfect. So with this, I'll be taking a leave. Let me have my dinner now. You guys also have it. See you day after tomorrow. Okay, bye bye. God bless you all.
Unacademy. Let's crack it.